Hi everyone. In this lecture, we will see how we can use BFS to form a single source shortest path algorithm. Okay, so what is the meaning of single source shortest path? So let us first see what is this. Okay, so single source shortest path means starting from a single source. Let's say any node can be a source. Let's assume that this zeroth node is the source. You want to find out the shortest path or the distance to all other nodes in the graph. Okay, so I'm interested in learning what is the shortest path from 0 to some other node, that is, let's say, destination. Okay, so or you can just call this as a source node. So this destination can be all other nodes in the graph. So I may ask, okay, what is the shortest path from 0 to 5? So one path is, okay, from 0 you go to 1, and from 1 you go to 2, from 2 you go to 3, and from 3 you go to 4, and from 4 you go to 5. But a shortest path would give you something like this: you go from 0 to 3, and from 3 to 4, and from 4 to 5. So obviously this is the shortest path. So now if you see this carefully, we have discussed that BFS gives us the level order traversal. That means we are going to visit all these nodes level by level. And also, if you observe carefully, the distance calculated by the level order traversal is the shortest. Okay, so I'm making a statement: distance calculated by level order traversal is the shortest. Okay, this is actually the shortest distance if the graph is a unweighted graph. Okay, so here we have an unweighted graph. That means all edges have the same cost, or all edges have the unit cost. Okay, so this might not be the case if you have weights in the graph. For example, this edge is having a different weight than this edge. In that case, we use a different algorithm that's called a Dijkstra's algorithm. But in this case, since this all edges have the same weight, so what you can see this, if I just modify this graph little bit, or if I just change the way this graph looks like. So we have 1, we have this 2 which is connected here, and here we have 4, and here we have 5. So if you carefully see, so how does BFS proceed? So it starts from the root node and it tries to cover all the nodes that are in the next level. Okay, from 0 we go to 2 nodes that are 1 and 3. And if you see, if you just treat it like a fire that is spreading across these ropes, so you will find that 1 will discover 2, or 3 will discover 2. Okay, so at t equal to 1, or at level equal to 1, you will discover the nodes 1 and 3, and at t equal to 2, or the level equal to 2, you will discover the next node, that is 2. And since 2 is already discovered, so 3 may not discover this node, but in the same time 3 can discover another node, that is 4. So 3 can go to 4, and at this also we will reach and t equal to 2. Okay, so what happens is from 0 you go to 3, and from 3 you go to 4, and from 4 you can easily discover 5, and you can say t equal to 5. So this is what we have seen. Okay, so what actually happens is, if you talk about 5, who discovered 5? We know 4 discovered 5. And who discovered 4? We know 3 discovered 4. And if we know the shortest path to 3, we also know the shortest path to 4, and we also know the shortest path to 5. So what happens is, you are basically interested in finding out now what is the shortest path to 3. So one way is, you can come via this path, and another way is you can come via this path. So obviously the path that is smaller will be discovered first in level order traversal. This we can say because this is a uh, unweighted graph, and this will be true in this case. Okay, so what you need to do, if you need to find the shortest path to any other node, you need to, um, when you are visiting any node. Okay, so the very first time when you are visiting any node, that path is going to be the shortest, because if you come via some other path, maybe little later on, to this particular node, it will obviously take more time. So if I do a BFS from this node to, let's say, discover this node, in the first step I will discover this, in the next step I will discover this, and similarly if this goes on parallelly, in the first step I will discover this, and in the second step I will discover this, in the third step I will discover this, and in the fourth step I will discover this. So obviously the very first time a node is discovered, that will be the shortest path to that particular node. So this is what I am trying to say, or I can say the level of that node is basically the distance of that node from the source. So this we can do for all the nodes. So we can run a BFS and the level of that particular node will be the shortest distance. So what changes we need to make in this code is we just need to update distance of a node. For example, if you go from a node X to node Y, and if you see this X has a distance D, then Y will have a distance of D plus 1. That's it. Okay. And if a node is already discovered, if a node, let's say there is some other node, and for this node the distance is already known, let's say this distance is D dash, then from Y to this particular node, if there is an edge, you do not need to update this particular distance. So that distance is smallest when the node is discovered for the first time. So that's it. Okay, so let's try to make some changes in the code, and then we will try to print out the distances as well. Okay, so I will also dry run the code so that things become more clear to you. So we have 0, we have 1, we have 2, we have 3, and we have 4, and we have 5. So what now I'm going to do is I'm going to say distance of source node from itself is going to be 0, and for all other nodes which are not discovered, I'm going to say this distance is going to be infinity. Okay, so what I will do here, I also need to maintain two things. One is whether that node is visited or not, and second, what is the distance of that particular node. So what I can do is I can just maintain one hash map that basically stores that whether that node is visited or not. So I will make a map of t comma int. Okay, so earlier this could be a boolean value also, but I just made it an integer. So instead of storing true or false, I can actually store distance. Okay, so visited of source will be 0. In the beginning, the source node will have a distance of 0, and all other nodes will have infinity distance. Okay, so that is int max. So I can just iterate over all the nodes in the graph. So for auto, t node that is there in the adjacency list. Okay, so adjacency list will give me pair, that is the key and the values. So node pair that lies in the list L. So I can say okay, so my node will be, so let me say this will be auto. So node will be of the type T, and this node will be equal to node pair dot first. Okay, and I can say visited of node equals to int max, or let me just call this as distance array. So distance of that particular node is int max. That means that node is having infinite distance. Okay, so that's what we do. We basically in your adjacency list, okay, you have something of this form. You have 0 followed by a list, 1 followed by a list, and 2 followed by a list, and so on. So I say okay, node pair. So node pair contains these two things. Okay, so if you just want to get the name of the node, that is node pair dot first. So this is the first component. Okay, so similarly we iterate over all the nodes, and we say okay, distance of that particular node is infinity, and actually we should do this step here. Okay, except for the source node, all other nodes should have infinity, and then we override the distance of the source node as 0. Okay, and that source node is added to queue, and in this case, at this particular point, we can check if distance of neighbor is not equal to int max or is equal to int max. That means you are visiting that node for first time, so you push that node into the queue, and you also update the distance of that particular node. Okay, so distance of neighbor will be equal to distance of parent, the node that discovered this. So it's a child of node plus 1. That's it, and that's the only change we need to make in the algorithm. So let me try run this code so that things are more clear to you, and this will actually help us to find the shortest distance to every node. So here I just remove the cout statement. I'm not going to print the traversal, but what I can do is I can print the distance to every node. Okay, so I can say, okay, for auto node pair in L, I can say, okay, my node is of the type T, that is node pair dot first, and the distance to that node is, let's say, int d, that is equal to distance of node. And I can just see out node is node, and this is at a distance d from the source. Okay, so that distance is going to be d. So that I do for all the nodes in the graph. Okay, so let's first try to run this code. Okay, so it says node 0 is at a distance 0, that's fine. Then we have node 1 that is at a distance 1, fine. We have node 2 at a distance 2, fine. Node 3 at a distance 1, fine. Node 4 at a distance 2, that is fine. And node 5 at a distance 3. So that means this is correct. Okay, so now let me give you a quick recap of what we have done in this problem. Okay, so we are doing the same BFS operation, but this time we are saying, okay, in the queue first I will add the source node, that is 0, and I say, okay, 0 has a distance of 0. So then from 0 I know I can go to 1 and 3, so I put them in the queue. And I also know distance of 1 and 3 is initially infinity. Okay, so what I do, I mark this as visited and I set this as distance as 0. So this distance will not be int max again, and it won't be added back to the queue ever again. Okay, so I add 1 and 3, and at the same time I update distance of 1 as distance of parent. Okay, so distance of child is updated as distance of parent node, that is 0 node plus 1. So this distance becomes 1, and similarly this distance becomes 1. Okay, so you can say you from 0 you are able to traverse to 3, and you are also able to traverse to 1. So that's how. Okay, so you treat it like a fire that is spreading from 0 to the neighboring nodes. So you have reached 3 and you have reached 1, and both of these nodes took a distance of 1. Okay, so 3 has a distance 1, and you pop out 0 from the queue and you pick the next node. So next node is 1, and you pop out 1 and you try to reach the neighboring nodes. So from 1 you now you can only reach 2, and you say, okay, distance of 2 is distance of parent plus 1, so this distance now becomes 2 instead of infinity, and 2 is now added to the queue. So 2 has a distance of 2. Okay, so now next node that you pop is going to be 3, so you remove 3 from the queue, and you see, okay, from 3 you can go to 2, but 2 is already visited. 2 does not have a int max distance, so you do not go to 2. Now you pick the next neighbor of 3, that is 4. You go to 4 and you say, okay, from 3 I am coming to 4, and this distance should be equal to, it should not be infinity, it should be distance of 3 plus 1, that's 2. Okay, so this distance is updated as 2, and 4 is added to the queue. Okay, next you pop 2, and from 2 you cannot go to any other nodes, you go to the next node now, and from 4 you can go to 5. Okay, and you say, okay, distance of 5 is now not infinity but it is 3. That's what you do, and you add it to the queue and you pop 4 in the, okay, so 4 is already popped and 5 is added to the queue. So you know distance of 4 is 2 and distance of 5 is 3. So finally 5 is popped, and from 5 we cannot go to any other location. So this is how we get all the distances. Hi guys, we are discussing the Dijkstra's shortest path algorithm. So it is an algorithm that helps us to find shortest path between any two nodes on a weighted graph. So it is also called single source shortest path algorithm. It means it can find out the shortest path starting from a single source to all other nodes, right? So from single source to all other nodes in the graph, right? So, and the special thing is it works for the weighted graphs. For the unweighted graphs, we have seen the BFS algorithm, right? So it is a algorithm for the weighted graphs with no negative weight cycle, right? So this is an example of a weighted graph. So where here we have a set of nodes which are connected by some edges, and these edges have some weights, right? So these edges can be either bidirectional or they can be unidirectional, right? So you can have a two-way edges or you can have a one-way edges, right? And an example of this algorithm could be you have various cities in India or maybe some various nodes, and there are some roads connecting them, and you want to find out what is the minimum distance that you need to travel from Amritsar to some city, let's say Bhopal or maybe to Mumbai, right? So we can use this algorithm as it works on the weighted graph. So here you can say roads are the edges and these edges have some weights, right? Now there are various ways to implement a graph. We have seen there is a adjacency matrix, right? There is a adjacency list and there is a edge list also, right? So I'm going to use adjacency list to implement this graph, and we are going to see how this algorithm is being implemented, right, on the adjacency list implementation, right? Because we are using adjacency list because it is the most efficient method of. So for this graph you can say the adjacency list will be nothing but like this, right? So here you can see Amritsar is connected to Jaipur and Delhi. So Amritsar is connected to these cities, Jaipur and Delhi, at a distance of 4 and 1. So in my adjacency list, I will map Amritsar with Delhi and Jaipur. So you can say this is a key, and this whole thing is a list, right? So this thing is a list of pairs, right? And pairs are of the type string and integer. Key is also a string, right? Key is also a string. So what you can do, you can maintain a hash map of key value pairs and store every key and its value. So Bhopal is the key, this list is the value, this Delhi is the key, this whole thing is a value. So in the code I will show you how you can implement a hash map. So if you want to make a generic hash map, if you want to make it work for any kind, so you can say there will be a hash map in which key will be of the type T and value will be a list of pairs, and in the pair the first data member is of the type T and second data member is of the type int, which represents the distance or the cost. So this is the hash map. This is how you can implement a, right? So this is a hash map, maybe a map or a unordered map, whatever you want to take in C++. So this was about storing of the graph. Now let us discuss how this algorithm works. So algorithm says, firstly you have a one source node and you make the distance of the source node is equal to 0, and initially all the nodes are not visited and their distance is infinity, right? So all these nodes are at a distance infinity from the source node, and now you pick the node which is having the minimum distance. So out of all these nodes, you know the source node is having the minimum distance, so you pick it, right? So now the question arises, how do we pick up the node with the minimum distance, right? So you want to find out node with the minimum distance. So there are multiple options. So one option is you can use a linear array, linearly search over all nodes, right? So this is a time consuming operation and it takes linear time. Second is to use something like priority queue or a set, or you can use a set. So basically in set you can find out the node with minimum distance in O1 and remove it in log n time, right? So this is a better way, right? Because we will find out that node from the set which is having minimum distance and we will remove it, right? We are not going to use priority queue here. You will come to know about the reason also, right? So now see, you are starting from this node 1 and you are going to update the neighbors. So neighbor is 2, the neighbor is 3 and the neighbor is 4. So distance of 2 is going to be nothing but the distance of parent plus 1. So it is going to be distance of parent plus h that we are traveling, right? So this distance is going to be, earlier it was infinity, earlier this distance was infinity, now this distance becomes 1. So since the distance is getting reduced, I will update it, right? For this node, the distance is going, earlier was infinity, now it is nothing but 0 plus 4, which is 4. And for this node, this distance is going to be nothing but 7, right? Now I know that the distance has been updated, right? In the second step, this was in the first step, right? The first node which we have picked. Now in the second step, I will pick that node which has the minimum distance, right? So the node with the minimum distance. So for now initially I had only one in my set. So there was a set, and set, you know, it stores elements in a sorted manner, right? So the nodes are sorted according to their distance. So set is of pairs, right? So there is a node 1 and initially it was having 0 distance. I removed this node from the set, right? And I updated all its neighbors. So these neighbors 1, 2 and 3, these neighbors will go into the set, right? So in the set I will have a node called 2, I will have a node called 3 and I will have a node called 4. And distances of these nodes, 2 is having a distance of 1, 3 is having a distance of 4 and 4th node is having a distance of 7, right? So there is a set of pairs. So this represents the node and this represents the distance, right? And this is sorted according to the distances. Now out of these nodes, I will pick that node which is having the minimum distance. Why? Because, and I will freeze it, right? So 1 ka distance we have finalized. So 1 has been marked that its distance has been finalized. Now I will pick this node. It has been finalized because there is no other way to reach 2 in which distance of 2 is less than 1, because all other nodes, let's see this node or this node, if there is a route to 2 via 3 or 4, they cannot be of shorter length because distance of 3 and 4 is already larger than 1, right? So this distance has been finalized. So we remove this node and we try to find out what all neighbors are there. From 2 you can visit this node, you can visit this node. Earlier the distance was 4, but now the distance is going to be 2, right? So now the distance is going to be 2. So what do? You just update the distance, right? So in set there is a no operation like update. In priority queue you do not have an option to update a node, right? You can only remove the topmost node from the heap and you can insert data and you can find out the minimum. So that's why we are not using priority queue, we are using set. In set you do not have an option to update, but what you can do, you can remove the node and insert the new node, right? So you will remove and then insert into the set. This is what you have to do. So first we have to you have to remove this node 3 and then you have to insert a new pair, right? So you will remove this pair and then you will insert a new pair which is for the node 3 and it is having distance as 2. So since it is sorted, so it will come to the front in the set, right? So this is what I have done. So we have updated this node by removing it from the set and inserting the new pair into the set, right? And you know, for 2 there is no other pair which was not visited. 1 was already visited, it has been marked true, and 2 has been marked true. Now you will pick out one node which is not has been finalized or visited, right? So you will pick 3 from the set. This node will be picked from the set. You will just finalize it. It has been marked now, and you will remove it. This has been removed because its distance cannot be minimized more. Now you will find out if there is a neighbor of 3 which has not been finalized. So 2 is finalized, 1 is finalized, but 4 is not finalized. So you can try to update the distance of 4 via 3. So you can say distance of 4 is now nothing but distance of 3 plus 2. So this distance is going to be 2 plus 2, 4. So you will see in the set that the old distance was 7. Now you will remove the old pair and you will insert the new pair. So in the new pair the node is 4 and the distance is also 4, and you will, that's it, right? Now from the set you will pop up this node, right, and you will finalize its distance, and this pair will also get removed. So finally the set is empty and your algorithm is now finished. So finally you will have the distance of 1 as 0, the distance of 2 as 1, the distance of 3 as 2, the distance of 4 as 4. So these are the shortest distances from source to all other nodes. From source to all other nodes. Alright. Now let us see in the coding part how we can implement this algorithm. Now let us see the coding part of this algorithm. So I have a graph and I'm going to use templates to implement this algorithm because I want my algorithm to work for integers, strings and all other data types, right? So I'm going to make a templated graph, right? So hash map will be a templated graph. So I am going to use a templated hash map to store this graph. So we have a unordered map of type T and value is a list of pairs of type T and integers. And here is a hash map. Let's name it as, let's say M. So when the user says you want to add an edge to your graph, you can say, and this edge starts from a node called U and ends at V. So if there is an edge from, let's say, U to V, and you are given 4 things. Let's say there is an edge from Delhi to Mumbai and it is having a distance of 5. So what I will do is, in my map for the given key Delhi, I will insert a pair called Mumbai and value of distance is 5. And let's say if there is edge from Delhi to Agra, distance is 2. So I will insert one more edge to Agra and the distance is 2. So this whole thing is a list and this is the key, right? So this is the key and this is the value which is of this type. So you can say m of u dot pushback a pair which can be made using this function
v and the distance, right? And if it is specified the edge is a bidirectional, then you have to do the reverse also. So in Mumbai you will push back Delhi as well. So if bidirectional is true, then m of v dot push back make pair of u and distance. So this is how you store this graph. Now let us talk about how to print the adjacency list. So let us try to print the adjacency list. So first thing is you can iterate over all the rows in the map, right? All the key value pairs in the map. In your map. So I'm going to use a for each loop for this. So you can say for auto j belongs to your map, right? Now what is j here? Let us try to see through this diagram. So you can say j is a kind of an iterator which will refer to each object. So j will refer to this, j will refer to this. So if you write j dot first, it means Amritsar, it refers to the key, and j dot second refers to the list, right? So j dot first refers to your city, and j dot second refers to the list of cities that the city corresponds to. So you can write cout j dot first, I am talking about this city, and followed by a arrow. Then you can print the list, right? So let's iterate over the list of cities, right? So you can take another iterator for auto L belonging to j dot second, because j dot second is the list of cities. So here you can print out what is the city and its distance. So L dot first will give you the city name, and L dot second will give you the city distance. And followed by a handle. So let me tell you once again that if you have something like this, if Delhi is connected with, let's say, city 1 Agra at a distance of 5 and city 2 Jaipur at a distance of 10. So basically your j points to whole j is this object, right? J is this thing, right? J dot first is this and j dot second is this list, right? And what is L? So L is this thing, L dot first is Agra, L dot second is 5. Then L becomes this, L dot first is Jaipur and L dot second is 10. So this is how this thing works, right? So let us try to print it. So I'm just going to test this if this is working. So I construct a graph called India and I just try to print its adjacency list. India dot print adjacency list. Alright, so let me just check it out. Alright, so we have missed one bracket here. It should be like this, and we can use the unordered map, right? right? So you can see this is a unordered map, so that's why the cities are not ordered in a particular fashion, right? So these keys are not ordered in a fashion, but if you use a map, then the keys will be sorted, right? So you can see Agra, Amritsar, Bhopal, Delhi, Jaipur, Mumbai. So map keys the elements in a sorted order, so you can use both of them, either of them, right? So I'm going with the unordered map, right? Now it's time to implement the Dijkstra's algorithm now. So let us try to implement this algorithm. So the first thing I need to maintain in this algorithm is the distance of a node, right? So for every node, I'm going to maintain a distance array or a distance map, right? That what is the current distance. So initially for source node it is 0, for all other nodes it is infinity. And so this distance which we have stored here will now be stored in a map called distance, in which the key is a city and the value is the distance, integer distance, right? So let us make this a distance map. So we have a unordered map again, in which t type is mapped with the integer type, and let's call it distance. Now for initially I can set all distances to infinity. So I can say for auto j belonging to m, and we know j dot first denotes the city, so you can say distance of j dot first is going to be int max. So all distances have been set to infinity. Then we are going to make a set, right? So we are going to make a set to find out a node with the minimum distance. So there is a set of pairs in which the first parameter is a distance and the second parameter is that city. So set is named as S. So why I have kept the first parameter as distance? Because set में जो sorting होती है, sorting is according to the first parameter, right? So by default set sorts according to the first parameter, and I want to sort according to the distance. So that's why I have kept. Now we can say the distance of our starting node is going to be 0, whatever the source node is given in the problem, and we have to insert that node into our set. So you can say s dot insert, and we will make one pair of distance which is 0 for the source node, and we will push the source node, right? And we have to do some work while this set is not empty. So while the set is not empty, you will find out one node, right? So find the pair at the front, right? At the front. So this will be given by, let's say there is a pair and it is given by star of s dot begin, because s dot begin is a pointer and star of s dot begin will give you the pair. So here in this algorithm we had seen that we were picking the pair from here, right? So in the starting you have a pair like this 1 and 0. So this is the pair which you are finding out, the pair with the minimum distance. So this gives you the pair, and you want to find out what is the name of that node. So it will be given by p dot second, because the second parameter here, this parameter denotes the node and the first parameter denotes the distance. Now you can find out what is the distance, what is the node distance, which is given by p dot first, right? And we have to erase this node. We have to erase this node also from the set, because the distance has been finalized. So you can call s dot erase. So it is like popping in the queue. So s dot erase, and I give erase the beginning node. Right. So this node has been erased. Now you have to iterate over neighbors of the current node, right? So you can say they are the neighbors or the children of the current node, right? So you can say neighbors or the children of the current node. So you can use a for loop for auto. Every child pair belonging to the adjacency list of the current node, right? And you will see from 1 you can go to 2, from 1 you can go to 3, 1 you can go to 4. So you are going to iterate over these neighbors, because in the adjacency list of 1 you have pairs like this: 2 comma 1, 3 comma 4, and you have something like this: 4 comma 7. So what you are going to do, you are traveling from 1 to 2, and the distance of 2 is now going to be, earlier it was infinity, now it is going to be distance of 1, which is 0, plus this distance, which is 1. So if this distance is minimum, we are going to update it. So if node distance, which is basically the distance of the parent, plus the distance contained in child pair dot second, basically this distance, we are talking about this distance, 2 comma 1, right? This, right? This is child pair dot second. If this distance is less than the distance of that node, which is child pair dot first, then we are going to update it. So now during updation we have to see, so in the set updation is not possible in the set or in the priority queue, right? But here we are using the set. Updation of a particular node is not possible, so we have to remove the old pair and insert the new pair to simulate updation. So how do we remove the old pair? First we will search, if that pair is present, then we will remove it, right? So I can say auto f s dot find, we have to find the old pair. So what is the old pair? You can say there is a pair in which the distance is same as the distance of the child pair dot first, or you can write here destination also, right? जिस पे हम जा रहे हैं, and the node is child pair dot first, or you can simply write, let's say t destination equals to child pair dot first. जिस भी node पे हम जा रहे हैं, that is the destination node, right? So distance of destination and destination. So if that node exists, we will remove it. So if f is not equal to s dot end, so f is basically an iterator, and if it is not pointing to the end of the set, it means that node has been found. So we will erase that node. So s dot erase f. So if the node is found, we will erase it and we will insert the new pair. So let us insert the new pair. So you can say distance of child is now going to be updated as, or you can say distance of destination is going to be the distance of parent, node distance, plus this distance, child pair dot second, right? This is the distance, and you are going to insert this distance into your set. So s dot insert make pair, the first value is going to be distance of your destination, and the second value is going to be your node which is your destination. So in this way, this algorithm will continue and the while loop will terminate when your set becomes empty. So I will just dry run this part. What is happening is, so here we had seen that suppose if there is a node called 2 and there is a node called 3 and suppose these distances are 1. So in the starting this distance is 0. It updates its neighbors as 1. It updates this as, initially it was infinity, then it becomes 1. It was infinity, then it becomes 2. Now in the set you have these nodes. There is a node 2 at a distance of 1. There is a node 3 at a distance of 2. So you will now pop out this node from the set and you will see that it will try to visit this node. So this node is now going to have a distance of 2. Sorry, earlier it was 2, now it is also 2. Let's say earlier it was 3. Let's say earlier it was having a distance 3, now it is going to have a distance of 2. So I'm going to remove this node from the set and I'm going to insert a new pair called 3, 2. This is what I have done. So I try to search for that node. If it is present, I erase it and I insert the new pair. Now let us try to test it on our code. So this is the graph which we had made. So this is for the graph which we had made and let's try to run it. And we have to print, let's print distances to all other nodes from source. So you can say for auto distance we are going to auto d belonging to the distance array, distance map. So d dot first gives you the city and d dot second gives you the distance, right? So you can say is located at a distance of distance from the source, right? From the source, and this distance is going to be d dot second. So there is a small error here. Int max, yeah, it should be like this. So it says 2 is located at a distance of 1, 1 is having distance 0, 4 is 4 and 3 is located at a distance of 2, which is perfectly fine for this example. Now let us try to dry run it for this case also. So suppose this is a map of India and I have this graph and we are going to run the Dijkstra's algorithm starting from the source node as Amritsar. So it says Delhi is located at a distance 1, Amritsar 0, Jaipur 3, Mumbai 7. So Amritsar is having a distance of 0, Delhi is having 1, Jaipur is having a distance of what? 3, right? So you can see there was a distance 4, but there is a shortest distance 3 via Delhi if you come via Delhi, and you have a Mumbai at a distance of 7. Alright, so for Mumbai you can have this path 1, 2, 4 and 3, 7. So this is the shortest path for the Mumbai, right? And similarly for Agra it is 2 and Bhopal it is 4. So Agra is having a distance 2, which is fine, and Bhopal is having a distance of 4, which is also fine. So for Bhopal you are having this path, right? So since we have made a distance array, similarly you can make a parent map and you can print the path also, right? So what you can do is you can make a parent hash map. So you can store the parent of the node, whatever the parent is, and you can print the path also when you are updating the distance, right? So this is very easy. I think you can do it. So I hope this algorithm is clear to you, and I hope you enjoyed it. So thanks for watching.
Hi guys, so in this lecture we are going to talk about another interesting algorithm that is called as Bellman-Ford algorithm. Okay, so let's talk about uh, Bellman-Ford algorithm, but before that let us have a quick recap of different shortest path algorithms that we have seen so far. Okay, so typically there are four popular algorithms in graph theory, out of which three algorithms uh, are single source shortest path. Okay, so in the short form we also call them as SSSP, single source shortest path algorithms. So these are three algorithms. The very first one is BFS, okay, and the next one is Dijkstra, and the third one in the category is Bellman-Ford. Now you may ask, why do we need different algorithms? The answer is very simple. Depending upon the problem statement, depending upon the type of graph, we need to have different type of algorithms. Okay. So the special thing about BFS was that all the edges, that if they're in the graph, they are unweighted, and you're given one source vertex from which you need to find out the shortest path to all other nodes. Then you can simply do a level order traversal or a breadth first search that will give you the shortest path to all other nodes. Okay, so when do you use BFS? When you have a unweighted graph, right? When you have a unweighted graph. Okay, so each edge is equal, then simply you can use BFS to find the shortest path to every other node if from a given source node. Okay, so that's why it's called as single source shortest path algorithm. The next algorithm in the that we have studied is Dijkstra's algorithm. So this algorithm basically finds the shortest path if you're given something like this. Let's say this edge is having a weight 3, this is having a weight 2, and maybe this is a weight 1, and you need to find out the shortest path to all other vertices in the graph given the edges are weighted. Okay, so this is useful when you have a weighted graph, and another condition is the edges should be positive. Okay, so weighted edges, and those edges should have positive weights. Okay, so Dijkstra is going to fail if you are going to have a graph in which you will have negative edges. Okay, for example, if I give you this particular graph, let's say uh, this is node 1, and from here you have an edge of weight 2 that is going to a node 2, and from here you have an edge of weight 4 that is going to a node 3. So if you remember the logic of Dijkstra, and let us say we also have a edge of negative weight, and let's call this as -3. So if you try to recall what happens in Dijkstra's algorithm is, you start from, let's say, this node. You say, okay, this is at infinite distance, this is at 0 distance, and this is also at infinite distance. Then you try to explore the neighbors of 1. Okay, neighbor of 1 is 2. So you say, okay, 1 is having 0 distance, we put this in priority queue or in the set. Then we pop this node out, so this is covered, and we push the neighbors in the set. So neighbor is 2 comma 2. There is a node at a distance 2, whose distance will be now updated as 0 plus 2, that is 2. Okay, and similarly there is a node at a distance 4. We will say, okay, 3 is going to have a distance 4, and then you're going to pop this thing out. Okay, and you do not update anything. So this distance is now 2, and this distance is now 4. And next time you will pop this node out, and you can see
2 is already covered. 2 is already covered, so you do not update the distance of 2. Okay. So what I'm saying is, if you go by Dijkstra's algorithm, you will get the minimum distance of 2 as 2 and the minimum distance of 3 as 4. But in actual, what should happen? So the shortest path to 2 should go via 3. Okay, this should be the shortest path. So this distance is 4 and 4 minus 3 is 1. So the shortest path to reach 2 should be 1. So this is where the Bellman-Ford algorithm comes into picture. So it's going to handle the case of a weighted graph. Okay, and we are going to say this weighted graph is going to be a directed graph. I will explain the reason briefly why it should be a directed graph. And let me also give you one comparison based upon the time complexity of different algorithms. Okay, so complexity wise, BFS is linear. It traverses all the vertices and edges at most once. And Dijkstra is something like a E log V algorithm. Okay, it's like E log V or E log E. So it's kind of a n log n algorithm. It's kind of a linear algorithm. Okay, so you can say it's kind of a order of n algorithm, and this is kind of a order of n log n algorithm. Okay, and Bellman-Ford is kind of a quadratic algorithm. So although it takes more time, but it is more powerful because it can also handle the case when you have negative weights inside your graph. So it's kind of like a quadratic algorithm, maybe a kind of an n square algorithm. Okay. So this is what I wanted to say about these three algorithms. Okay, so one more algorithm you will study later, that's called as Floyd-Warshall. That is somewhat different from these algorithms because it's not a single source shortest algorithm, it's a all pair shortest path algorithm. Okay, so you need to find out shortest path between all pairs of vertices, then you will use this algorithm that we will study later. Okay, so basically I wanted that you should have a basic understanding. You should be able to differentiate between these three algorithms. And if I talk about interviews, BFS and Dijkstra's are the most common ones. Okay, and most of the times the problem would be around BFS or DFS, right? So it's fine if you skip this algorithm, but I'm not expecting that it would come in lot of interviews. Okay, so I've personally seen lot of interview questions. It's very less likely to be asked. So BFS and Dijkstra is something that you must know, but still it's good to know about this algorithm. Okay. Now let us see how does this algorithm work, right? So for that we will start with a very simple graph. I will give you a graph kind of a structure, and we will discuss few important concepts involved in this particular algorithm. Okay, so let me first write the pseudocode of this algorithm, or let me say basic steps involved in this algorithm. Okay, because this is something, it's not very intuitive. If you know the algorithm, then you can easily understand it and implement it. Okay, so the algorithm says you need to initialize uh, distances of all vertices as infinity. Okay, maybe put them as int max except source vertex, and distance of source vertex should be 0. So that is the first step. Okay, so something like a distance map that you maintain. Okay, this vertex is at this particular distance. So in the beginning we do not know every vertex is at infinite distance. In the second step, the algorithm says you need to relax all edges p minus 1 times. So this step is the most important step. We will spend most of our time to understand this particular step. And third step is, again, it's easy. Third step is an optional step. It basically detects whether a graph contains negative weight cycle, right? So we will talk about this step little later on. Now let us take one example of a graph. Okay, let me just take a very simple graph, and let's say uh, This is the graph that we have seen in the previous example. So this edge is 2, this edge is 4, and this edge is minus. Now what this algorithm says is, in the beginning you put all the distances as infinity, okay, except for the source vertex, which is going to be 0. Let us assume this is the source vertex. Source vertex will be given to you in the problem. Then it says relax all edges v minus 1 times. Okay, this step is something that we need to focus. So what all edges are there in the graph? Okay, so let us first make list of edges. So there is an edge from 3 to 2. Okay, let us pick the edges, and these edges can be in any order. So there is an edge from 3 to 2. You just maintain a kind of an edge list. Okay, there is an edge from 1 to 3, and there is an edge from 1 to 2. Okay, so what is the meaning of relaxing an edge? Okay, so let us first discuss what is the meaning of relaxation. So relaxation is a term that basically defines, so if you have a node u and it has an edge to node v, and let us say the distance of node u that you have computed is, let's say, distance of u. Okay, let us say this distance to reach this node is given by distance of u, and what is the current distance to reach this vertex v, that is denoted by distance of v. So if I talk about this graph, I make a map like this. So to reach 1 I need 0 distance, to reach 2 I need infinite distance, and to reach 3 I also need infinite distance. So this is the kind of map that I have. So relaxation basically means this condition. It says if distance of v is greater than distance of u plus the weight of the edge from u to v. Okay, so let's say this weight is the weight u to v, right? So that means if you are standing at this particular vertex, okay, and if you're coming via vertex u, which reduces the distance to reach this particular vertex, then you update it. Okay, so in that case you can say, okay, distance of v is going to be now distance of u plus weight. That's it. Okay, so that's what the relaxation step is. So let me give you one more example. Let us say we have a vertex v. So in the beginning, let's say this weight is infinity, but suppose there is a vertex a, there is a vertex b, and there is a vertex c. Let us say this edge is having a distance 1, this edge is having a distance minus 2, and this edge is having a distance 3, and let us assume the distance to reach a b c is already computed. Okay, let us assume let's say the distance to reach a is 5, distance to reach b is, let's say, 3, and distance to reach c is, let's say, 6. So what it says, so if I relax this edge a to v, okay, so that basically means, okay, from a, if you go to the vertex v, then what would be the distance? So it would be 5 plus 1, that is 6, that is less than infinity, so you make this distance as 6. From b, if you go to v, what would be the distance? It would be distance of b, that is 3, minus 2, that is going to be 1. This is less than 6, so you make this as 1. So you did another relaxation step. And similarly here, the distance to reach c is 6 plus 3, that is 9, that is not less than the current distance, that is 1, so you just make it as 1. So this way we consider all edges that are ending up at v, and we pick that edge that gives the minimum distance to the v. So this is one step that is part of the algorithm. Okay, so I hope you understand this step. Very simple, just an if condition, something you have done in the extras also. Okay, something similar, but yeah, this is like an update condition. Okay, so how do you update the distance of a particular node? Now let us try to understand the algorithm. So first step is clear. So first step is easy. So we, in this example, we have done with the first step. Now it says relax all edges v minus 1 times. So all edges. So when I say all edges, that means you make an edge list and you can keep all edges in any order. Okay, so any random order you can pick for the edges. In this case, I pick this edge 3 comma 2, 1 comma 2 and 1 comma 4, and it says relax them. So let us first try to relax this edge. So if I go from 3 to 2, so distance to reach 3 is infinity, distance to 2 is also infinity, so this condition will not be true. Okay, so that means infinity minus 3 is not going to be less than infinity. Okay, so we just say, okay, this is going to be infinity or infinity minus 3. So maybe you can do it, but it would be still would be the order of infinity. Okay, so maybe we can say, okay, distance to reach 3 is infinity, distance to reach 2 is infinity minus 3. So I say, okay, this distance is going to be infinity minus 3. We can do this because this condition is going to be true. So let us say distance of 2 is going to be greater than distance of 3 plus the edge weight, that is minus infinity. So this means infinity is greater than infinity minus 3. So I say, okay, distance of 2 is nothing but infinity minus 3. So that is what happens when you take the first edge. Okay, so I'm just talking about the first iteration. So v minus 1 times means v minus 1 iterations, and we need to iterate through all edges in each iteration. Okay, so this completes the first iteration. So this completes the first step of the first iteration. Then you go to this edge 1 to 3. So what is the distance of 3? That is infinity. What is the distance of 1? That is 0. And if you try to relax this edge, what would be the distance of 3 now? It would be, of course, 4. Okay, so you make this distance as 4. Then you pick the next edge. Okay, what is the distance of uh, 2? That is infinity minus 3. So what if you reach, if you relax this edge 1 to 2, so it would be 0 plus 2, that is 2. So this is less than infinity minus 3, so you make it as 2. Okay, so what happens after the first iteration is you have these three nodes 0 1 and 2, that is, sorry, 1 2 and 3, 1 2 and 3. So distance of 1 is 0, distance of 2 is 2, and distance of 3 is 4, right? Now you can see out of these distances, the distance of 2 is not correct. Okay, the distance of 2 is not correct because we did not consider this path. Okay, we have not considered this path in which we are going from 1 to 3 and then we are going from 3 to 2. So what this step says, you have to relax all edges v minus 1 times. So we have only done iteration 1. So what is v here? We have 3 number of nodes. That means this relaxation step in which we are relaxing all edges, we have to do it 2 times. Okay, so now let us again iterate through the edges. So we need to iterate through the edges, but we have to keep the same order that we kept in the first iteration. Okay, so if you pick this edge, okay, so some of you might not find this as intuitive. Okay, so don't worry, I'm going to explain it further. Okay, and I hope you guys will definitely understand it. It is going to take little more time so that you get a feel of this algorithm, how it's going to work. Now you pick 3 comma 2 edge and you see distance of 3 is 4, distance of 2 is 2, but if you do 4 minus 3, that is 1, so that basically reduces this distance, so you update this distance as 1. Okay, so you have covered this edge. Then you go to 1 comma 3. So 1 is 0, 3 is 4. If you pick this edge, so this distance still remains 4, so you do not do anything. Then you pick this edge 1 comma 2. So this distance is now 1, but if you pick this edge 0 to 2, this if condition is false, so you do not update this distance, so this distance still remains 1 and this distance remains 0. And you can see this is the shortest distance that you can get.
Okay, so now what you have got is you got a very high level idea about the working of the algorithm. Okay, but you might not have got an intuition why we are doing this relaxation b minus 1 times, and how does the ordering of edges matter. Okay, so to explain this concept further or give you a more in-depth insight into the algorithm, I'm going to take another example, and I hope you had made the notes of this example till now. So I'm just going to erase everything, and let us take a more complex algorithm, a more complex example now. So let us say we have lot of vertices, like let's say vertex A that's pointing to B, and we have C here, B here, E here, and F. Okay, let me give some weights. So let's say this is 3, this is so you can see this is the graph that I have created. So what I will do, I will try to run Bellman Ford algorithm on this example. Okay, so first of all we need to initialize distance of all vertices as infinity, and for one vertex it's going to be, for vertex A it's going to be 0. Let us assume this is the source vertex. Okay, and so I'm going to write all the distances here. Okay, so let's say A, B, C, D, E, F, and we also need to create edge list. Okay, so now there can be multiple ways to select edges. Okay, so if you have, let's say, E edges, you can permute them in E factorial ways. Okay, so you can pick any order. So the order that I'm going to pick now is, it's a 1, 2, 3, 4, 5, 6, and 7. Okay, so I'm going to pick the edges in this particular order, but you can take any order. Okay, so the order of edges will not matter. I will explain you why. Okay, so it will matter, and it will basically uh right, so if you perform these two steps, then the order of edges will not matter. But if the order is good, then your algorithm can converge early. Okay, so it can give you good results early, but in the worst case, after running v minus 1 times, it will definitely give you the correct result. So that we are going to see how it's going to happen. So let me just write the list of edges that I have edge from A to B, I have edge from B to C, and I have edge from A to C, and then I will pick the edge from C to D, then I will pick the edge from D to E, and then I will pick the edge from E to F, and finally I will pick the edge from E to F. Now you may ask, why this order? So as I said, you can pick any order. I will give you one more example in which we will take the different order, okay, than this one. So what you do in the beginning, this distance is 0, rest everything is infinity. So I say, okay, A is 0, B is infinity, C is infinity, D is infinity, E is infinity, and F is also infinity. Now it says, okay, relax all edges V minus 1 times. So this is, now my first iteration is going to start. So I need to iterate over all the edges. So go from A to B, relax it. So B is infinity, relax it. So it will make this distance as 2. Okay, so from A to B, if you go, distance was infinity, and A to B is distance is 0 plus 2, that is 2. It's less than infinity, so you make this distance as 2. Similarly, you go from B to C, this distance was infinity, and you say, okay, 2 plus 2 is 4, so you make it as 4. So this distance is going to be 4. Then you pick this edge, A to C. So A to C, if you see now, what happens? So C is already at 4. Now you get another path to reach C. So you see this path is giving you a lesser distance than the current distance. So you make this distance as 3. Okay, so this distance is now 3. Then from C you go to D. Okay, so
from C you go to D. So what will happen is 3 plus 5, that is 8. So this distance becomes 8. Earlier it was infinity, now it is 8. Then from D you go to E. So 8 plus 6 is 14. So it was earlier infinity, now it is 14. So this distance becomes 14. And from E to F, right? So you can say this distance was infinity, now it is 14 plus 7, that is 21. And then you pick this edge D to E, D to F. So it was 18, it would be 8 plus 10, that would be 18. So it is less than 21, so you make this distance as 18. Okay, so this is what you get after the first iteration. Okay, and if you carefully analyze this graph, and you will see this is the best possible distance, right? So why it is so that we got the best distances in the first iteration? Because we chose the edges in such an order such that we are able to minimize all the distance. Okay, but in most graphs this order will not be known to you. Okay, so you will not know the order. Okay, so this is the best possible order to do the relaxations, but in any graph you will be given any random order of edges. You do not know in which order we need to pick the edges. So let us try to move towards the worst case. Okay, so you can have a reverse order of the edges. So you can have something like this in the edge list. Maybe you will have edges in the reverse order. Okay, so you have, let's say, D to F, then you have E to F, then you have D to E, then you have C to D, then you have A to C, B to C, and A to B. Let us consider this particular order and let us see what happens in such a. Okay, so now have a look at this. So what we will do, I've taken the edges in the reverse order. Okay, so it doesn't matter, you can take any order. So what will change, it will basically the number of iterations. Okay, so the maximum number of iterations that you need to take is going to be v minus 1, and we will discuss why it's going to be v minus 1. Now we have taken the edges in a different order and I basically reversed the order. Okay, so now it says, okay, in the beginning you have this distance as 0 and rest every distance is going to be infinity. Okay, and it says, okay, go and relax D to F. So if you basically pick this edge D to F, so D is at infinity, F is at infinity. So if you do the relaxation, you will still get infinity. Okay, so I'm writing the results after the first iteration through all the edges. Okay, then it says, okay, relax E and F. E is at infinity, F is also at infinity, so it is again going to be infinity. D to E, both are infinity, it's going to be infinity. C to D, C is at infinity, D is at infinity, it's going to be infinity. B to C, it's going to be again infinity, right? Now you get this edge A to C. So A is at a distance 0 and C is at a distance infinity, but A to C edge is having a weight 3. So you update this and you make it as 3. So now C is going to have a weight of 3. Okay, and then you see the edge A to B. So A to B is going to be was infinity earlier, now it's going to be 2. So you make this update as 2 and A remains 0. So what is the most important observation here? Okay, so after the first iteration you will always update all the paths from the source that have one edge in between them. Okay, one edge in between them, right? So this is actually a dynamic programming algorithm. So in DP, what you do in bottom up DP, you start with the smallest instance. Okay, so you're solving a shortest path problem. So what can happen? So if given any graph in which you have, let's say, v vertices, okay, and what is the largest length of the path that you can have in this particular graph containing v nodes. Obviously, largest path will have v minus 1 edges. Okay, so that's a reason we are going to run this graph, run this relaxation step v minus 1 times. Okay, let us do it for the next iteration. The next iteration will give you all the shortest paths in which you have uh, two edges. Okay, so let us see what happens. So if you relax d to f, d is infinity, f is infinity, nothing happens, so f remains infinity. E to f, e is infinity, f is infinity, nothing happens, it remains infinity. D to e, d is infinity, e is infinity, nothing happens, it still remains infinity. C to d, c is 3, okay, d is infinity, but c to d edge is 5, so 3 plus 5 is 8. So you make this update of d as 3 plus 5, that is going to be 8. Okay, so now you can carefully see in the first step, a got connected with b and a got connected with c. So c had a distance 3 and b had a distance 2. Okay, in the next step, when we took an edge from c to some other node, okay, we took an edge from c to d, you can see distance of d is updated, and you can see there are two edges in the path. Okay, from a to d, you can see there are two edges. So you will get all the shortest paths in which the number of edges from source to any other node is 2. Okay, so d is going to have a distance 8 here. So this distance is 8. Now if you pick this edge b to c, b is 2, c is 2, c is 3, so nothing happens, c remains at 3. And then you pick this edge a to c, that does not change the value of c. A to b, so b is 2 and it will still remain 2 and it will still remain 0. So you can see we got this particular output. So in the third step, what we will have, we will add all those paths, all the shortest paths in which we have three edges. Okay, so let us try to run it again. So from okay, so d to f, now we have already updated the path to reach d, and via this we can relax other edges that are going from d to some other nodes. Okay, so that will help us to reduce the path. So in the next iteration, what we do, we say okay, let's start from d and go to some other node. So d to f, f is infinity, d is 8, 8 plus 10 is 18, so we say okay, f is going to be 18. E to f, e is infinity, f is 18, so we do not update it, so doesn't change. D to e, so uh, d is we have seen a path from d to f, but we have not seen a path in which we go from d to e and then from e to f. So that will come in the next iteration because it involves four edges. Okay, so this path a to c, c to d, d to e, e to f, so this is not going to come now, it's going to come in the next iteration. Okay, so let's see this edge d to e. So d is 8, this edge is 6 and e is infinity, so 8 plus 6 is 14, so it's going to be 14. Then what next? C to d, c to d, 3 plus 5, that is 8, so 8 is not less than 8, so we just retain the old value, and similarly we return 0 2 3 here. Okay, what happens in the next iteration? So you again go through all the edges. Okay, so d to f, d to f already minimum, so it's going to be 18. E to f, now e to f, now this is going to come now, so this path now contains 1 2 3 4 edges, and you can see it's coming in the fourth iteration. So now e plus f, so distance of e is now 14. 14 plus 7 is 21, so we do not update the distance of f. But suppose this was minus 7, then what we have done, we have done 14 minus 7 equal to 7, so we had made it as 7, right? So I hope you're getting the intuition of Bellman-Ford algorithm, and it's like a bottom up DP. Bottom up
CP. In the first part, you update all the nodes that are one distance away. Okay. The next path, you in the next iteration, you generate those paths in which two edges are involved, and that distance is minimized. In the next iteration, you generate paths in which three edges are involved and all the distances are minimized using three edges, and 4, 5, 6, and 7. So how many times you need to run this algorithm, okay, given any order of edges. Okay, so if you have v number of nodes, the largest path in the graph can have v minus 1 edges. So that is why you need to run this algorithm v minus 1. So I hope this algorithm is now clear to you. And one last step is left, that is checking for a negative weight cycle. Now let us see how we can do that. So what will happen is negative weight cycle, right? So for this I will pick a simple example. Let us say you have 1 that is pointing to 2, and you have 2 pointing to, let's say, 3, and let's say this weight is minus 4. Okay, and let's say this weight is 1. Okay, now you can see this graph contains a cycle. Okay, and this cycle is a negative weight cycle. Okay, so if this distance would have been plus 4, no issues. But what will happen from 1, if you go to 2, this distance becomes 2, and from 2 you go to 3, this distance becomes minus 2, and from minus 2 if you go here, this distance becomes minus 1. So initially this distance was 0, so it would be now minus 2 plus 1, that is going to be minus 1. Again, from if you go from here to here, minus 1 plus 2, that's going to be 1. So this distance becomes 1, and 1 minus 4, so this distance becomes minus 3. So you can see you can reduce your distance infinitely. Okay, so if you just cycle through this graph infinite number of times, you will end up getting a minus infinity distance. So that is something not very practical. So we say, okay, if you have something like this in the graph, you just say, okay, this graph contains negative weight cycle and it is not feasible to calculate the shortest distances in such a graph. So what will happen if you run the Bellman-Ford algorithm v minus 1 times? Okay, you will get the shortest distances. And let me give you one more example. Let's say this is 1, 2, 2. Let's say this distance is minus 1 and this distance is 3. So this graph does not contain a negative weight cycle. So it's 2 minus 1, 1. So this distance would be 1, this distance would be 2, and this distance would be 0. Okay, so let me just write with a different color. So final distance, it's going to get 0, it's going to get 2, and it's going to get 1. But in this case, we are just going to we are going to reduce, we are able to reduce the distance with every iteration. Okay, so in every iteration, what do, you basically iterate over all the edges. So let's say this is 1, 2, and 3. In the first iteration, this is 0, this is infinity, this is infinity, and 3 edges, we need 2 iterations. So in the first iteration, let's say you pick this edge 1 to 2, distance of 2 is 2. Then you pick this edge 2 to 3, so that's 2 minus 4, that's minus 2. And then you pick this edge uh 3 to 1. Okay, so this is minus 2 plus 1, so this distance becomes uh minus 1, right? In the second iteration, okay, so we will do v minus 1 iterations. In the second iteration, you say, okay, minus 1 plus 2, that's going to be plus 1, so this distance becomes 1. 1 minus 4, it becomes minus 3. And from here, okay, so minus 3 plus 1, so it's going to be minus 2. Okay. Now if you do a third iteration, okay, so that's for, and if the distances change, So if you do the vth iteration and if the distances change, that means the graph contains a negative weight cycle. Otherwise, these distances should not change, because uh, at most, if the graph does not contain a negative weight cycle, then v minus 1 iterations are enough to relax all the edges and up get the minimum distance. Okay, so third time if you're going to do it, you will see, okay, minus 2 plus 2, it's going to be 0. So this distance is going getting changed. That means there is a negative weight edge cycle in the graph. And similarly, if you run this algorithm for this graph, you will get the same distances in the third iteration. Okay, and these distances will not change. So I hope you got the idea, and in the next video we will see the implementation of Bellman-Ford algorithm. Hi everyone, so in this video we would be writing the code for the Bellman-Ford algorithm. Okay, so let us discuss how we can write the code. So the very first thing that we need about this algorithm is we need the graph, and we would prefer to have edgeless representation. Okay, so what I can do is I can create a vector of triplets. Okay, so in which I have edge of the form, there is an edge from u to v, and it is having a given weight. So I can store that information in the form of a vector of integers, and let's call that as edges. Okay, so if you want to take user input, you can take input the number of edges and the number of vertices, or let's say n is the number of vertices and m is the number of edges that we have. So yeah, so what we will do, let's see. So what we need to do, let's take input the number of vertices and edges, and then we have created a vector of edges. For example, there is an edge from a to b of weight 3, there is an edge from c to d of weight 5. So we will store this information in the form of a vector of vector. So we have n vertices and m number of edges, and after that we need to take input all the m edges. Okay, so let's say there is an edge from u to v having a weight, so we take in these values, and we can say, okay, uh, edges dot push back. So edges is a vector and we can push another vector inside it. Okay, so you can create vector using curly brackets, so u v and now we have created the graph. Okay, so that's what we need to do in the graph, and now we need to make a call to the Bellman-Ford algorithm function that we are going to define. So if you can recall, we have three steps. So first step is we need to create a distance vector or distance array. So in this case I will create a distance vector. So we will get the number of nodes we have, the starting node, and the vector of edges. Okay, so we get everything in the function. So what you can do, you can create a vector and set all distances to infinity. So you can say vector of int, let's call this object as distance, and you can call in the constructor, you can give, okay, I have n number of, I have nodes numbered from 1 to n. So in that case you will need n plus 1 size in the vector, and everything is initialized with int max. Okay, and you can say distance of source is going to be 0, and here we can say, okay, we need to relax all edges v minus 1 times. So this n is nothing but v. Let's make it as capital. So put a for loop here for int I equals to 0, I less than v minus 1, I plus plus, and what we need to do, go to every edge and relax it. Okay, so for auto edge that is there in edges, so you need to get the extract the elements. So u is going to be this element, so you can say edge of 0, it's on the 0th index, v is going to be edge of 1, and weight is going to be edge of 2. So what is the relaxation formula? So if distance of u plus weight is less than distance of v, then you update distance of v as distance of u plus weight. That's it. So this is the relaxation step. So if the graph does not contain a negative weight cycle, then you are done and you can return distance here. But maybe a negative weight cycle could be present, so we need to write some more code for the negative weight cycle as well. Okay, so one thing that you can do here is you can check if distance of u is not infinity, because distance of u plus weight, it can lead to overflow. Okay, so this can become negative. So you have to check if this distance is not infinity, then it makes sense to compute this value. Okay, otherwise, so this condition we are adding because of a possible overflow. Okay, so you have, if you add something to int max, then the number becomes negative. So that is something we can't do here. So what we will do to check negative weight cycle, so we will say, okay, for auto x, that, or for auto edge that is there in edges, so something similar. Okay, so we have to run one more iteration of this for loop, and if there is a change in weight, so if this condition is true, then that means we can reduce the distance of a node infinite times, and it contains a negative weight cycle. So you simply say negative weight cycle found and you exit the program. Otherwise, you return the distance vector. That's it. So I'm assuming my nodes are numbered from 1 to n. So what you can do, you can say, okay, vector of int distances, that's given by Bellman Ford. Here give n source. Let us say the source vertex is always 1, or you can take it as a user input and you give the list of it. And here you can say, okay, for int I equal to 1, I less than equal to n, I plus plus, cout node I is at distance of I handle. Right, so this should be v here. And another thing I should add here is this uv and weight, right? Yeah, so this is distances of I. So let's run our code now. Okay, so let's test our code. So 3 nodes and 3 edges, and let us draw the graph. So I'm going to consider a graph like this. So 1, 2 and 3. So let's say this edge is 3, 4, and let's say this is -10, and a similar graph but with a different edge. So let's say this is like this, -10, 3, and this should be 4. So you can see same graph, but one of the edges is reversed. Okay, so in this case we should get a negative weight cycle, and here we should get this distance as -10 and this distance as 3 and this distance. So let's see what we get. So 1 to 2 there is an edge 3, 2 to 3 there is an edge 4, and 3 to 1 there is edge -10. So it says, okay, there is a negative weight cycle in the first graph. All right, let's run the code again. So 1 to 2 3, and 2 to 3 4, and 1 to 3 -10. So it says, okay, node 3 is at -10, node 2 is at distance 3, and node 1 is at distance 0. So that means the algorithm is working fine, and That's all for this video, guys. And the code is very simple, right? So if you understood the algorithm, you can easily understand this code. So only this part. So what we did, so this is a relaxation step and this is the loop, right? Hi everyone. So in this lecture we are going to discuss another popular algorithm that is called as Floyd-Warshall algorithm. And what this algorithm does, it basically helps you to find out all pair shortest paths. So what does it mean? So all pair shortest path basically means you can find the shortest path starting from any node, okay? So you can find the shortest path from 1 to all other nodes, that is 2 3 4. You can find the shortest path from 2 to all other nodes that are 1 3 4. You can find the shortest path from 3 to 1 2 4, and similarly from 4 to 1 2 3. Okay, now is there any other algorithm that you can use to find this? Obviously you can use Dijkstra's algorithm if you have positive edges, and you can use Bellman-Ford algorithm if you have negative edges, but that algorithm will only give you the shortest path starting from a single source. So single source would mean either the vertex 1 or the vertex 2 or the vertex 3 or the vertex 4. So what you can do, you can actually run Dijkstra's or Bellman-Ford algorithm by uh, on each vertex as the source vertex. Okay, so you would be running Dijkstra's algorithm v number of times, or you would be running Bellman-Ford algorithm v number of times to find all pair shortest paths. So that is one particular option, and we also know that Dijkstra's is a greedy algorithm and Bellman-Ford is a DP based algorithm. So Floyd-Warshall is another algorithm that we can actually use, that is most commonly used to solve such a problem, and some of the concepts are quite related with the Bellman-Ford algorithm. Okay, so it's a DP based algorithm, and uh, it's going to take order of n cube time. Okay, the good thing about this algorithm is it can work with negative edges, and it can also detect negative cycles too with one extra step. So we will see this complexity once we finish the code, but I've given you an idea. Okay, so n is number of vertices. So n stands for number of vertices in the graph, or you can say O of v cube time, where v is the number of vertices. But I hope you got the idea why what we are trying to achieve with this particular algorithm. So we are trying to find shortest distance from each vertex to every other vertex in the given graph. Now let us first talk about how do we represent this graph. Okay, so clearly you can see this problem involves a 2D structure, because you need to compute the shortest path from each node to every other node. It would be better to represent this graph in the form of a adjacent matrix. So what I will do, I will create a matrix like this. So let me say I have a box like this. So I will fill the weights in this particular matrix. Okay, so that those weights are given in this particular graph. So distance of 1 to 1, that is 0. Distance of 1 to 2, so is there an edge from 1 to 2? No, there is no such edge, so we put this as infinity. Similarly, distance of 1 to 3, so 1 2 3, that is minus 2, so I put it here. Similarly, this is infinity, and you can verify the remaining distance are like this, and this is infinity, infinity, 0 and 2, infinity, minus 1, infinity, and 0. So you can see all the diagonal elements are 0, because distance of each vertex from itself is going to be 0. So this is what we have in the beginning. So let's call this as a distance matrix, or whatever you want to call it as. So let's say this is distance matrix in the beginning, or in the 0th step before starting of the algorithm. So what we will do, so the basic idea of this algorithm is like this. Okay guys, let us see. So in this 0th step, what we have uh, edges that are connecting two vertices. Okay, so if I just draw all the edges in the graph here, it would look something like this. So let me draw these edges. So we have an edge from 1 to 3, we have an edge from 2 to 1, we have an edge from 2 to 3, and we have an edge from 3 to 4, and we have an edge from 4 to 2, that is actually -1. So this is what we have represented in this particular matrix. Now in the next step basically says what you will do. You will try to find out the paths in which you're including one as an intermediate vertex. Okay, so if you want to go from, let's say, I to j, let's say you want to find the shortest path from I to j, the algorithm says at each step or at each phase. So this algorithm is going to proceed in multiple phases. Okay, so in the first phase, so this is the first phase, what we will do in the first phase, we will try to put one as an intermediate vertex. We will say, okay, if you want to go from I to j and if you go via 1, then try to update the shortest path. Okay, that is what we are trying to say. So let us see what will happen in this case. Okay, so in this case you're filling this distance matrix, and if you want to go from 1 to some other node, then you cannot include 1 in that. Okay, because 1 is equal to I. So in this case I will just leave the first row and first column as it is. So what is first row? So it is 0, infinity, -2, infinity, and leave the first column as it is, 4, infinity, infinity, and also the diagonal elements will remain 0. Now we have to fill the remaining cells of this particular matrix. By including 1, we have to see if we can minimize the distance. So this coming to this 2 to 3, can we go from 2 to 3 by including the vertex 1 in between? Of course yes. Why? Because if you see, uh, if you want to calculate the distance of 2 to 3, it would be the current distance, that is 3, or the distance from, let's say, 2 to 1 plus the distance from 1 to 3. Okay, so this distance is going to be 4 minus 2, so it is going to be 2, and you can see 2, this distance is actually less than the distance that we currently have. So we update this distance and we make this distance as 2 in this particular step. So you can see this is actually the updated distance. So what we have done is we have done something like this: d of ij is minimum of whatever distance we had earlier, d of ij, or if we are going through a vertex k, that is the distance from the node I to k plus distance of the vertex, distance you need to travel from vertex k to j. So we take minimum of these two and we put this value here. Okay, that is what we do, and then we come to 2 to 4. Can we go to 4 via 1? Okay, so in that would mean you go from 2 to 1 and then you go from 1 to 4. So 1 to 4 is infinity, so this distance remains infinity. Okay, so we do not update this particular distance. And similarly, can we go from 3 to 2? So via 1. So 3 to 1, so what is the distance from 3 to 1? So 3 to 1 is infinity, so this distance will not get updated, it will still remain infinity. Can we go from 3 to 4 via 1? So for that you need to go from 3 to 1. Okay, so if you want to go from 3 to 4 via 1, so what is this distance? 3 to 1. So 3 to 1, so this distance is infinity. Here you can see, so we cannot go via 1, so this distance still remains 2, right? So it was earlier 2, so we just put this as 2. Okay, similarly here we can say, okay, from 4 to 2, so that distance was -1. Can we go from 4 to 1? So 4 to 1, this distance is infinity, so we cannot update, so it still remains -1, and similarly this distance remains infinity. So you can see in this particular step we have updated only one vertex here. Okay, Okay guys, let us see the next step. Okay, so what we learned in this step is that we can use 1 as an intermediate vertex to create some new paths that do not exist. So let us see what new paths we have created in this particular grid. So we created only one new path. Okay, so in the first phase we got this new path in which we updated this particular box. So this path is from 2 to 3, and it says if you want to go from 2 to 3, you should use 1 as an intermediate vertex. Okay, so that's what it says. So this distance is 4 and this distance is -2. So this is a new path that we got in this particular grid. Now let us move on to the next step. So we will do a second phase here. So in the second phase, what we will do, we will include all the vertices from 1 to 2 as an intermediate path. Okay, so in the second phase we will say, okay, if you try to go via 2, if you put 2 as an intermediate vertex, then what will happen? So this is what we are going to see. Okay guys, let's see what happens here. So now we are talking about k equal to 2. So that means if I want to go from I to j, okay, and any path from I to j can include 2 as an intermediate vertex. Okay, so when we talk about 2, that means in order to get the shortest paths via 2, we have already considered the case in which 1 was also included. Okay, so if I just talk about the k should be an intermediate vertex, so I'm just uh, making it more clear, so don't feel confused. So this is like a bottom up DP solution. Okay, so when you talk about if you include the kth vertex, so when we form the answer for k equal to 1, so basically uh, 1 was also included. Now we are going for k equal to 2. So we will see that that does not mean that only 2 will be included. It can also mean that the vertex 1 is also included. Okay, we are trying to find out a path that can include all the vertices up to 2, right? So from 1 to k it can include all these vertices in the second phase. So that is the whole idea. So these vertices can be the intermediate vertices. So it will become more clear as I run through this particular example. So let us see what will happen. So obviously when you're talking about the second phase and you're taking 2 as an intermediate vertex, then in that case this row, this row and this column will not change. So we just fill in these values as it is. So this is going to be infinity from this particular matrix, infinity, 0, infinity and -1, and copy this row here, 4, 0, 2 and infinity, because 2 is starting point here, so it cannot be a intermediate vertex. Okay, so let's try to fill other cells. Also the diagonal elements will still remain 0. Now we have to go from 1 to 3 via 2. So can we go from 1 to 3 via 2? So let's see if it is possible. So that would mean, okay, you go from 1 to 2, okay, and from 2 you go to 3. So 1 to 2, what is the distance? 1 to 2, this is infinity, right? So this distance is infinity, so this will not change. We cannot reduce this value further, so we copy the old value, that is -2. So this -2 comes here from here. Okay, and similarly 1 to 4. So can we go from 1 to 4 via 2? So that would mean uh, you need to go to 1 to 2, and then you need to go from 2 to 4. So is this thing possible? So 1 to 2 is still infinity, and 1 to 4, the old value, right, this is also infinity. So minimum of those two options. One option is you include 2 in the intermediate path, and other is you do not include 2 in the intermediate path. Okay, so by checking both the options we get the answer as infinity. Okay, so you can clearly see, if you take up this path or you take up this path, 1 to 4, a direct path, okay, that does not include 2, so both of them will give you infinity. So because the distance from 1 to 2, so 1 to 2, it is infinity, right? So this edge is infinity, the remaining edge you do not need to consider.
1 to 4. So what is 1 to 4? So 1 to 4 is also infinity. So both of them are infinity. Minimum of both of them is going to be infinity. So this does not change here. Now let us see the next row. Can we go from 3 to 1 via 2? So if you carefully look, okay, what is the distance of 3 to 2? If you put 2 as an intermediate node. So if you say, okay, from 3 to 2 and then from 2 to 1. So 3 to 2 is infinity, and the direct distance that we have earlier, that is also infinity. So this will still remain infinity. Okay, and then we have this thing. So similarly this value will be 2. Can we go from 3 to 4 via 2? So 3 to 2 is infinity. Okay, so this remains the original distance, that is the direct distance, 3 to 2. So this value does not change. Now let us come to the last row. Can we go from 4 to 1 via 2? So 4 to 1 via 2. So yes, it looks something that we can do. So the earlier distance was infinity, but if we say, okay, no, if from 4 I want to go to 2 and from 2 I want to go to 1, so what is this distance? So it is going to be -1 plus this edge 4. So this distance is 3. So earlier distance was infinity, the current distance is 3. So we have updated this particular cell here. So we got one path here. From 4 you want to go to 2, and from 2 you can go to 1. So this is what we have created in k equal to 2, k equal to 1, and this is what we have in k equal to 0. Let us talk about one more cell. Can we go from 4 to 2? So this is already filled, do not need to do anything here. Can we go from 4 to 3 via 2? So 4 to 3 via 2. So that would mean you need to get the shortest path from 4 to 2, and then you need to get the shortest path from 2 to 3. Okay, so this is where dp is going to come in picture. Okay, so if you just see this direct edge, so this is going to give you a distance of 3, but we know that we have already computed the shortest distance from 2 to 3. You can see earlier distance in the beginning, this distance was 3, but as we are updating this matrix, now we know the updated distance, that from 2 to 3 the shortest distance is 2, that is via 1. Okay, so that is via 1. So we have already considered uh, all nodes in which we consider 1 as an intermediate vertex. In the second phase, we are considering all the nodes in which we have both 1 and 2 as a intermediate. We could have both 1 and 2 as a intermediate vertices. So what is going to happen in this case? So if you want to go from 4 to 3, so you know this is given by dp. Okay, so this is given by this particular cell, and you know when we filled this particular cell, we said, okay, from 2 to 3, this is how the shortest distance was filled up. So I will just, if I want to write the path here, it would be look something like this. From 4 you go to 2, and from 2 to 3, this is how you got the path. So from 2 you went to 1, and from 1 you went to 3. So this value is already stored, this value is already stored here. So this distance is 2. So what is the distance from 4 to 2? 4 to 2, this distance is -1, so it is going to be -1 plus this memoized value. This is a sub problem. Okay, so this distance is going to become 1. So this is an update that we are doing here. Okay, so now you may ask how it is dynamic programming, or where do I see an overlapping sub problem. So clearly, if I show you this thing, you just see this sub problem is already computed. Okay, so in this particular path, this was a sub problem that was already computed earlier, and we used this particular value to build an answer for this. Okay, so that's why it is going to be dp. So in the second phase, you do consider all the paths that that include vertices up to 2, right? So it could mean that 2 is included, it could also mean that 2 is not included, it could mean that all vertices up to 2 are included, or some vertices up to 2 are included. Okay, so that means we will consider all paths in which 1 and 2 can be a part of the path. Okay, so let me just write this thing again here. So it is via 1,
and it is via 1 2, via 1 2. Okay, now we have to go to the next step, that is k equal to 3. Okay. Okay, now let us see two more phases, third phase and the fourth phase. Okay, so third phase would mean that in the intermediate path we can include the vertices up to 3. Okay, so since we are considering, okay, if we include 3, then can we reduce the path length? So for what we will do, we will first fill this one. So this will remain same, infinity 0 and 2. Okay, and similarly this column will remain same, so it is going to be -2 2 0 and 1, -2 2 0 and 1, and diagonal elements will still remain 0. So now we can see, okay, from 1 to 2, can we reduce this particular path if we include 3 in between? So from 1 to 2, okay, so that would mean, okay, the shortest distance from 1 to 3, that is -2. Okay, so 1 2 3, that is -2, plus 3 to 2, so 3 to 2, that is infinity. Okay, so this will still remain infinity because we are not able to minimize it. Okay, similarly from 1 to 4, can we go from 1 to 4 via 3? So the answer is yes. So what is the shortest distance from 1 to 3? That is -2. And what is the distance from 3 to 4? So 3 to 4, that we can look up here. So this distance is 2. So that would be minus 2 plus 2. So this distance, earlier it was infinity. Now this distance is going to be 0. So we got one more path. So I will just draw here. In k equal to 3, we got one path that passes through 3 and helps us to minimize the distance. So it is from 1 you go to 3, and from 3 you go to 4. This distance is -2 and this distance is +2. So 1 to 4 is going to be 0. That's fine. Then from 2 to 1. So can we go from 2 to 1 via 3? Obviously 2 to 1 via 3. So from 3 to 1 you can see this distance is infinity, so it's not possible. So it will still remain earlier. So we will have this old value 4, right? From 2 to 4. 2 to 4 via 3. So earlier distance was 2 to 4. So what was the earlier distance? It was infinity. Yes. But now we can say, okay, from 2 to 3 the distance is 3. So 2 to 3 the distance is actually 2, not 3, right? So if you look at 2 to 3, what is the shortest distance? It is via 1, and that is already stored here. That is 2. And if you go from 2 to 4 via 3, that would mean you already know the shortest distance from 2 to 3. So that is from 2 you go to 1, from 1 you go to 3, and you can see we are again making the use of this particular sub problem here. And from 3 to 4, what is the shortest distance from 3 to 4? That is same from the beginning, that is 2. So that means this particular edge, we are using this sub problem here. So we connect this, and you can see this is going to be 4 minus 2 and 2, right? So this distance was earlier infinity, now this distance is going to be 4. So by including 3 as an intermediate vertex, we are able to minimize our path to reach. Okay, so this is one more thing that we got. Similarly, if I just fill this row, you will get 3 minus 1 1 and 0. It will be same as the previous one, you won't be able to minimize it. Okay, now let us talk about the fourth phase. That basically means all the vertices up to 4 can be can lie in the intermediate path. Okay, so if you want to go from I to j, that could mean all vertices from 1 to 4, basically a subset of vertices, okay, from 1 to 4 will lie in the intermediate path. So that is the final matrix that we want to compute, because while going from any one vertex to any other vertex, we can pass through any number of vertices. Okay, and obviously we will exclude I and j from it. So let us see, in the fourth phase we are saying, okay, 4 would up to 4 vertices will be included in the intermediate vertex. So we do not change the fourth row
and the fourth column, so it remains as it is, 3 minus 1 1 0, and this is going to be 2 4 0. Okay, and here I will draw the paths which include k equal to 4, or the fourth vertex as a intermediate vertex, and also the diagonal elements would be 0 here. Okay, and let us see from 1 to 2. Okay, so 1 to 2 via 4, 1 to 2 via 4, that would mean, okay, so that would mean what is the shortest distance from 1 to 4 and 4 to 2? This is what we need to figure out. So 1 to 4, 1 to 4, the shortest distance is 0, that's fine, and 4 to 2, 4 to 2, the shortest distance is -1. So we get the total path length of -1, and earlier distance was infinity. So we put this as -1. So we updated this. Now if you want to see the path, okay, so 1 to 4. So 1 to 4 would mean you were going from via 3, right? So that would mean from 1 you went to 3, from 3 you went to 4, so 4 is an intermediate vertex, and from 4 you went to 2. Okay, so this is -2 plus 2, and this is -1. So you can see this total path length is -1, and we got this particular answer here, right? Similarly, this would remain -2, no changes here, and similarly this would remain 4, and it would remain 2, and two more updates that we will be doing here is from 3 to 1. If you want to go from 3 to 1 via 4, you can go via 4, right? So what is the shortest distance from 3 to 4? That is 2, from 3 to 4, and from 4 you see, okay, I want to go to 1. So from 4 to 1, you know this distance is computed as 3, and this was computed in the second phase. Okay, so that means 2 was an intermediate vertex, so you put a 2 here. So in the actual path you will have a 2 here. From 4 you go to 2, and from 2 you go to 1, and you have already computed this sub problem from 4 to 1, so that is nothing but 3. So this distance is 3, and 3 to 4 is 2, so it is 2 plus 3, that is 5, and earlier distance it was infinity, now it is going to be 5. So you got another path here. So from 3 you go to 4, from 4 you go to 2, and from 2 you go to 1. So you can see, using 4 as an intermediate vertex, you are able to minimize the path from 3 to 1. Okay, yeah. So this is another path you get, in which 4 is a intermediate vertex. Now one final cell is left, is this one. Can we go from 3 to 2 via 4? So the answer is yes. The answer is yes. So earlier distance what we have is from 3 to 2. So earlier distance is infinity. But if you take this path, from 3 you go to 4, that is 2. And from 4 to you go to -1, so that is 2 minus 1, 1. So you get this path. So in this path also you have 4 as an intermediate vertex. So this path is 3 to 4, and then to 1. And this path length is 1. So you made 3 updates in this particular matrix. Okay. So this is how the Floyd-Warshall algorithm works, and I hope you got an idea about this algorithm, and this is how we are going to minimize the uh, distances. Okay, so at every time what we are doing, we are saying, okay, if you include the kth vertex as an intermediate vertex while going from I to j, so you say, okay, d of ij will be nothing but minimum of whatever is the distance you have computed, either is infinity or it is 5 or 3, or the new distance that you are getting. So that is from I to k, okay, plus from k to j. And remember, you have already solved these sub problems. Okay, the way we are going to write the code, or we are doing a bottom up kind of a DP, these are smaller sub problems that you have already solved. So you already know the optimal distance from I to k and from k to j. So this is the main trick that we use in the Floyd-Warshall algorithm, and in the next video we will see the implementation. Hi guys, so in this video we are going to discuss the implementation of Floyd-Warshall algorithm. Okay, So what we understood in the concept video is you need to create a distance matrix and you need to update that matrix over n number of phases or v number of phases. Okay, so we will have this as an initial matrix that is given as an input, and we will do some updates over v number of phases. And in every phase, what we will try to go to every cell and we will try to update its shortest distance using this formula that we have discovered. Okay, and if we are able to minimize this distance, so we say okay, if d of ij is less than d of ik plus d of kj, then we update this particular distance. So the implementation is going to be really very simple. So what we will be doing, we will have a loop of over phases. So and in each loop we will be doing updates over all pairs of I and j. Okay, so for each I and for each j, so you can see we will have three nested kind of a loops that will help us to implement this particular algorithm, and that is from where the complexity would be derived as n cube. So let us see the code now. So guys, I'm going to create this function Floyd Warshall and we would be writing the code here. So I have initialized a graph with the given inputs, and the diagonal elements are 0, and the case where we don't have any direct edge, we initialize that as int max distance, and all other weights are initialized as it is. Okay, so we have the same graph that we took in the example, so it has 4 vertices. Okay, and it's a 4 cross 4 matrix. So what I will do, I will initialize a 2D vector and I say okay, this vector is distances and the values are same as the given graph. So what we will do here is we will use 3 loops as I discussed. The first loop is to iterate over different phases, in which say okay, we can in each phase or in kth phase we include vertices 1 2 3 up to k as intermediate vertices. Okay, as intermediate vertices. So what we do for int k equals to 0, k less than v, k plus plus, and for each phase we need to iterate over entire 2D matrix. So we say okay, for int I equals to 0, I less than v, I plus plus. For int j equals to 0, j less than v, j plus plus. What we need to do, we need to see if by including the kth vertex we are able to minimize the distance or not. So if vertex k is included, and can we minimize the distance by taking k as an intermediate vertex. Okay, so that we have to see. So if the old distance, that is distance of I to j, if this is greater than the current distance, so from distance from I to k plus distance of from k to j, and remember these two sub problems are already computed because of the way we are running this particular for loop, and that we have seen in the example as well. So in that case we can say okay, distance of ij is going to be nothing but distance of ik plus distance of k to j, right? That's it, and that actually finishes the code, right? So here you can just say return distance. That's it. So you can see just 3 nested for loops and 1 if condition, and we are done. So implementation wise, this is the most simplest shortest path, all pair shortest path algorithm, or even if you compare it with other algorithms like Dijkstra's or BFS or so this one is actually really very simple. If you understand the concept, then implementation is not at difficult at all, right? So one thing that we can do is, let us try to run this code. Okay, so I can say okay, vector of all, I can say auto result equal to, okay, one thing I missed is this v. So v is nothing but graph dot size or graph 0 dot size, whatever you want to write it as. Okay. So auto result equals to Floyd Warshall, and you give the graph here, and for int I equals to 0, I less than result dot size I plus plus, for int j equal to 0, j less than result dot size j plus plus, and I can just see out result of ij. So build is successful. Let us run the code. Okay, one small change I'm going to make is, instead of using int max here, I'm going to define infinity, and let me say, okay, this is a very large value such as 10,000, because using infinity and then you add something, it could lead to overflow. That could cause a problem in the result. So let us try to run our code, and you can see we are getting these shortest paths. So if we just compare with the matrix that we got in the concept, you will see this matrix is actually same, right? So I think it's correct. Yeah, so this is the same result that we got for this particular given graph, so you can verify it yourself. So we have this particular graph, and you can see the shortest path from, let's say, 4 to 1. Okay, so 4 to 1, so it's going to be uh, minus 1 plus 4, it's going to be 3. That's correct. Or if I say, okay, shortest path from 2 to 3, so 0 1 2, 2 to 3, so it says it is 2, so 2 to 3. The only change I have made is I have done the indexing 0 based. Okay, so in the code the indexing is done from 0, and in the example the indexing was done from 1, but that doesn't matter. You can anyway change the indexing, okay, because this is a 0 based indexing matrix. So you can see our result is correct, and this is how the Floyd Warshall algorithm works. So if you talk about the time complexity now, you can clearly see this is a O1 step, and these three loops together run in order of v cube time, and we are using this distance matrix as a extra space. So we can see we are taking order of v square space, and we are taking order of v cube time. So that's all for this video, guys, and one small thing that I've left for you to do at your own is, how do you check whether a graph contains a negative weight cycle or not? So that is something you have to think by yourself. Okay, use the idea that we have discussed in Bellman Ford and apply that idea here as well.
Hi everyone. So today in this video we will discuss a very simple project idea that is really useful in everyone's life. So this is inspired from an app called Splitwise that lot of college students use to divide expenses among themselves. Okay. So what this app does is, it suppose you have a group of friends and you are making some expenses, and there are some dependencies, like you owe 100 rupees to someone, he owes 50 rupees to someone else, and he owes 30 rupees to someone else. So if you have a lot of people in the group, it becomes a really complex network, and you want to make it simpler so that the total number of transactions you need to settle all the transactions is minimized. Okay, so this is what this problem is. It's about minimizing the total number of cash transactions that you need to do. So we will try to build up one algorithm using graphs to solve this problem, and you can also take this idea to implement a real life project. Okay, so let's discuss. So we have also built a mini project around this in JavaScript, and I will show you what this project is about. Okay, so let's say this is a graph, and this denotes how much money a single person owes to the other people in the group. Okay, so this is like a graph, and you can see in this, if you have three persons. Okay, so person 3 owes 65 rupees to person 1, person 2 owes 41 rupees to this guy, and he owes 28 rupees to this guy. So you actually can simplify this by using a graph algorithm. And if I solve this problem, you can see the network can be simplified if this person gives 37 rupees to person 1 and this person gives 69 rupees to person 1. Okay, so just to make the calculation easier, I will give you a very small example. Let's say you have three friends, and let's say A owes 100 rupees to B owes 50 rupees to C, and C owes, let's say, 40 rupees to A. Okay, so effectively B is gaining 50 rupees and C is gaining 10 rupees. Okay, so if you just see here, B is going to get he's getting 100 rupees and he is losing 50 rupees. Okay, so the net gain for B is 50 rupees. Similarly, C is getting 50 rupees and he is losing 40 rupees. So net gain for C is of 10 rupees, and for A, he is losing 100 rupees and he is getting 40 rupees. For the net loss for A is minus 60. Okay, so that's the net gain for A. So what you can do is you can say, okay, A will lose 60 rupees and A will give 50 rupees to B, and A will give 10 rupees to C. Okay, so earlier we were using three transactions. Now you can do the same thing using two transactions. Okay, so that's the whole idea of this problem. Okay, and maybe let me give you one more example. Let's say if A owns B 100 rupees and B owns C 50 rupees and C owns uh, A 50 rupees. Okay, if this is the graph, then you can simply say that the net gain for C is 0, so A will just give B 50 rupees, and you can see you will need only one transaction to settle all these three transactions. Okay, so you can see we are representing transactions using edges in the graph, and we are maintaining the nodes for the people who are involved in these transactions. Okay, so it's actually a graph problem that is very interesting, and it can be used to build a real life project like this. Okay, and as I told you, it is also used in the splitwise app, and let's see some more examples. So what can happen is your graphs can grow in complexity. You can have bigger graphs, and in that case it might be difficult to solve directly with the help of a pen. Okay, so if you click the solve button here, you will get the solution. Okay, so I will discuss the logic and the implementation behind the algorithm in the coming videos. Okay, so that's what we are going to see. So thanks a lot, see you guys in the next video. Hi guys, so we will now discuss the idea behind the algorithm. Okay, so let me give you a small example. Let's say you have three persons, A, B, and C, and let's say there is some amount that A owes B. So A owes B 100 rupees, and let's say B owes C 50 rupees, and let's say C owes A 40 rupees. Okay, so let's say this is the amount that we need to settle. So in order to simplify this, what we can do is, firstly, you can see each person will have certain debits and certain credits. Okay, maybe there is a person, he is giving 30 rupees to someone, he is giving 60 rupees to someone, and let's say he is taking 100 rupees to someone. Okay, so if you want to simplify the transactions for this person, so you first need to know what is the total net amount this person will have. Okay, so total net amount finally in the end this person will get is, he is getting 100 and he is losing 30 and he is also losing 60, so he will actually end up with a profit of rupees 10. Okay, so maybe if we can make some edge in which this person gets rupees 10, that will help us to minimize the transactions. Okay, or what we can do is, if it is not possible that someone is not ready to give rupees 10 to this person, maybe we may have two edges in which he is getting 8 rupees from someone and 2 rupees for someone. Okay, so this type of a situation may arise, and that's where we can do some work. So what I'm saying is, in the end, each person will be either giving money or he will be taking some money. That's what the idea is. Okay, so each person will be either in the debit mode or he will be in the credit mode. Okay, so keeping this idea in mind, so let us compute what should be the final net amount that a person will have. Okay, so A is getting 100, A is losing 100, and A is getting 40, so net amount will be minus 60. For B it will be plus 50, and for C it will be plus 10, because he is getting 50 and he is losing 40 rupees. Okay, now we need to analyze these amounts. Okay, let's try to analyze these amounts. So let's try to settle these amounts. Okay, so let us make a list of people who are in a debit mode, and let's make a list of people who are in credit mode. So clearly B and C are in the credit mode, and B should receive 50 rupees and C should receive 10 rupees, and we also know A is in the credit or debit mode. So we have A, and A is going to have 60 rupees that he has to give. Okay, so let me write this amount as minus 60. Okay, so what we can do is, we can pick the largest debitor and we can try to settle the person who is the largest creditor. Okay, so pick the person who has the largest debit and try to settle a person who has the largest credit. Okay, so what we can do, we can say, okay, I will take 50 rupees from A and I will try to settle B. Okay, so let's say if A gives 50 rupees to B, then the credits of B will become 0 and we will have one transaction as of now. Okay, doing this, we can ensure that A will now have 10 rupees, and now you can see A is still in the debit line, and from the credit line we have the next person who is C. Okay, so we are talking about the next largest person, so who is C. So what we can do, we can pick A and C and we can ask them to settle their amounts. Okay, maybe if A had 12 rupees and C had 10 rupees, then A will give 10 rupees to him. Okay, and A still will have 2 rupees in his pocket. So we will try to settle these amounts. So once we have only two people left, we will see the net amount of debit will be exactly equal to net amount of credit. Okay, so we can send 10 rupees to C, and A will now have 0 rupees and C will also have 0 rupees which he wants to take as a credit. Okay, so in this way, A has 0 rupees to pay and all other persons have 0 rupees to take. So making this transaction, it will make 1 plus 1 2 transactions. Okay, so this is a very simple idea. So what you can do, you can make a list of people who want to debit, you can make a list of people who want to credit, and you try to pick a person who is the largest debitor and try to settle as many transactions from the credit list by picking the persons who have the largest credit. Okay, and what you can do is, one idea is you can make a max heap of persons with debit, and you can make a max heap of the persons with the highest credit. Okay, so if you use this kind of an approach, the complexity would be n log n, and if you do a linear search to find out the person with the maximum credit, it will be n square. Okay, we can also use something called a multiset. Okay, so let me explain this with the help of another data structure. So what we will do is, we will have all these people in a multiset, So multiset is a set that contains multiple elements with the same value. So let's put all the entries in the multiset. So it's minus 60, then I have 10, and I have 50. Okay. So what we can do is we can, so entries in the starting, let's call this pointer as a low pointer. Start entries in the end, let's call this as a high pointer. So these are the people who will get money. So let's call them as people who will credit money, and these are the people who will give money. So they are the people who are going to debit. Okay. So what we can do is we can pick the smallest number and we can try to settle the amount with the highest person from the right. Okay, so that will help us to settle one transaction. So we can say, okay, if I see what is minus 60 and 50, then I will take the minimum of these two amounts in terms of the absolute value. So I will say minimum of absolute value of minus 60 and 50, that's going to be 50, and I will try to give 50 rupees to this person. Okay, so in this way one person will be settled. Okay, so what we can do is, okay, so organizing all the n nodes in a multiset is going to take n log n time. Okay, because each insertion operation takes log n, so if you insert n elements it's going to take n log n time. And if you now see that this person will actually have zero amount, because what you need to do, you need to do low equal to low plus 50, that makes this value as minus 10, 10, and what you need to do, you have to do high equal to high minus 50. Okay, because he is getting 50 rupees, so the amount that he has to take further will reduce to 0, and we will remove this entry from the multiset. Okay, and finally what we will have two entries and we will try to settle them, and if we try to settle them we will have 0 0, and we will try to remove all 0 entries from the multiset, and this will make sure there are no pending transactions in our multiset. Okay, so this is what we can do to settle all transactions. Maybe we can try with one more example. Let's say we have person A who wants to give 10 rupees to B. B wants to give 20 rupees to C. C wants to give 30 rupees to D, and D wants to give, let's say, 10 rupees to A. Okay, so in this case A should not get anything. Okay, because A is getting 10 and he is losing 10, and B is giving 20 rupees to C. So what we can do is and C is losing 10 rupees, so we can say B will give 10 rupees to D, and C will also give 10 rupees to D. Okay, so that will actually help us to simplify this diagram, and let's see how we can do it using multiset. Okay, so let's see the net gain for A, that is 0. Let's see the net gain for B, that is minus 10. The net gain for C, that is also minus 10, and let's see the net gain for D, that's plus 20. Okay, so let's add all these entries in a multiset. So we have 0, we have minus 10, we have minus 10, and we have 20. Okay, so 0 we will not consider because that means no transaction is needed to settle the debts of that particular person. So what we can do is we can say, okay, let's pick these two persons and try to settle the amount. Okay, so it will be minimum of minus 10 comma 20, so that means you can settle 10 rupees and this guy will give 10 rupees to this guy, so this amount will reduce to 0. If it is reduced to 0, we do not add it to the multiset again, and we remove this entry from the multiset and we will add an entry of 10, because person who had to take 20 rupees, he had received 10 rupees, so the remaining amount to receive is 10 rupees. Now we can say, okay, our low pointer is at this place, our high pointer is at this place, and we will try to do a transaction between them and we will try to settle them, and this will reduce it to 0 and our set will become empty. Okay, so finally when we get empty set, we say, okay, all transactions have been settled, and in this way you can count the number of transactions and you can also count what payment should have been made from one person to other person. So I hope you got little bit idea, and more details will be clear when um, we see the solution video also. Okay, thanks a lot, see you guys in the next video. Hi guys, so in this video we will see the implementation of the splitwise algorithm in C++. So let's begin with the implementation. So first of all, you need to read how many friends are there and how many transactions they are going to make, so that we have a rough idea of the underlying graph. Okay, so the way we are going to handle this is, I'm not actually going to make the entire graph because that's actually not needed. Okay, so as I go through the implementation, you will see what things are needed and what things we can actually skip. So let me first start with some inputs. So I need to input the number of transactions that are there, that is the number of edges, and also the number of friends. Okay, so let's input the number of transactions and also the number of friends. That's like the edges and the vertices of the graph. Okay, and each transaction will be of the form x gives y amount rupees. Okay, so there are three variables that if there is a person x, he wants to give this amount to y. For that I'm taking these three variables, and what I can do, I can make a array just to store, make a 1D array to store the net amount that each person will have to take at the end. Okay, so that may be a positive amount, that may be a negative amount. So let's make an array called net, and I just made it of a constant size. You can also make it of dynamic size, and I have initialized this array with 0. Okay, so now I will read all the transactions. I can say while number of transactions is available, I will take input x, y, and the amount. Okay, so data will be given like this. So I have this graph that 0 gives 100 rupees, 1 gives 2 50 rupees, and 2 gives 0 50 rupees. Okay, so I have this kind of a graph, and I'm just reading in the data. Okay, so I will say net of x minus equals to amount. Okay, so and net of y plus equals to this amount. So I'm making an array and I'm storing how much is the net balance of each person. So x is giving some amount to y, so initially it is 0. Then let's say x is giving 100 rupees to y, so net amount of x will be this. But suppose there is a h from 2 to 0, in this case 0 is gaining something. Okay, so the net of 0 will be plus 100 and minus 50. So net of 0 will be actually equal to 50. Okay, something like this, minus 50. So he's giving 100 and gaining 50, so net of 0 will be minus 50. Similarly, net of 1 will be plus 50, and net of 2 will be 0. That's what it is going to be. Okay, so we now have the net amount that is known to us for each and every person. Okay, so now what we will do, we will iterate over all the nodes, and we will see if there are some transactions that are going to happen with this node. Okay, so that we will know if the net amount is not 0, and we will add those transactions in a multiset. Okay, so we will take a multiset of this form, multiset of integers and m. So why I'm not taking set, I'm actually taking multiset because it's possible that there are multiple transactions like minus 30, minus 20, minus 20, 10, 20, 20, 30 maybe. So one thing is, I need these transactions to be in the sorted order. Second, there can be multiple transactions of the same value. Okay, so that okay, so the multiple net balances can be same. Okay, these are not exactly transactions, but the net balance of two nodes can be same. So that's why we need a multi-set. Okay, so what I will do, I will add all these net balances in the multi-set as discussed in the algorithm. So what we will do, for int I equals to 0, I less than friends, I plus plus. Okay, so we have number of friends as 3, so we will iterate over all the friends, that is over all the nodes, and we'll see if net of that particular friend is not equal to 0. That means there are some transactions related with that particular node, so I insert them in my multi-set. Okay, now my thing, now I can build the algorithm. Okay, so this will actually initialize a list like this, and we want to sort it. So that is the work that is done by the multi-set. Now what we will do, we will take out two people, one from the left and one from the right. So the left one will be debited and the right one will be credited, and we will keep on doing this until the set is empty. Okay, so this is a greedy approach. The person with the highest debt will give money to the person who has to who has been the highest creditor. Okay, so what we will do, we will now try to make this multi-set empty. Okay, so pop out two persons, okay, from left and right, and try to settle them. Okay, so while this multi-set is not empty, we will try to get a person from the left. Okay, so I can see okay, what is the left pointer, that is given by m dot begin. What is the right pointer, that is given by m dot end. But remember, m dot give end gives me a pointer after the last pointer. Okay, so I have to do something like this, -1, but -1 is not a supported operation, so we use a function called previous. So that will make this pointer point to the previous element. Okay, so I was saying we have to extract two items out of the multiset. One is the lowest one and one is the highest one, and we will try to cancel the lowest with the highest one, or at least settle one of the persons. Okay, if this amount is 50, then we can give him 30 rupees, and 20 rupees he can take from the next person in the list. Okay, so that's what is the whole idea. So low will point to the first one, and right one or the high one, let me just say it is the high one. Okay, so let's say this is my high pointer. So what we will do, we will try to settle these transactions. So low and higher pointers, and if you want to get the amount, that would be this star of low, because multiset is of a integer, and the credit amount will be star of I. Okay, so the person who will receive credits is actually having, can take up to this amount of credits. Okay, and the person who can give money can give up to this amount of money. Okay, so what we will do, we will erase these elements from the multiset, or we can say remove these elements from the multiset, because that is required. So m dot erase low and m dot erase high. So these two elements are removed, and now we will try to make a settlement between these two, and this settlement will help us to eliminate at least one person from the vector. And the new entry that we will generate, that we will push in the multiset again. Okay, so let's see the settlement amount. Okay, so if the donor is giving 30 rupees and the acceptor can accept 50 rupees, so we'll say, okay, the donor is settled, he wanted to give 30 rupees and he has already given. Okay, so that will be minimum of minus of the value of debit, because it's a negative value, and credit value will be always positive. Okay, so that's a way of taking a absolute value here. Okay, so what we will do, we will transfer this amount, that is the settlement amount, from donor to acceptor. Okay, or from debitor to creditor. So we can say the debit amount will increase by settled amount because it's a negative quantity. For example, a person had to give 50 rupees, so if he gives 30 rupees, so it becomes minus 50 plus 30, that is, he will now only give 20 rupees more to the next person, or to the same, or to the next person in the uh, that we will pop from the vector. Okay, and the credit amount will be now minus equals to settled settlement amount. Okay, so now you will see, because the settlement amount is exactly equal to either debit or credit, so this will make sure one of them will become zero. Okay, so one of them will be zero. Okay, and suppose there is a person A and there is a person B. The person A can give 50 rupees and person B can accept 30 rupees. So what it will do, we will say, okay, you give 30 rupees to this person, and this amount will be now minus 50 plus 30, that is minus 20, and this amount will be now 30 minus 30, that is 0. Now what we will do, we will insert this person again in the multiset. Okay, so we will insert the person A and the amount minus 20 in the multiset, but since we are not maintaining uh, the persons in the multiset, so we will just insert this amount minus 20 in the multiset. So we can check if debit amount is not 0, that is, if debit is not 0, we can say m dot insert debit, and if the credit amount is not 0, so exactly one of them will be surely 0. Okay, then m dot insert credit, and in the final case, when there are only two persons left in the queue, both of these amount will be 0, and our multiset will reduce from a size of 2 to size of 0. Okay, suppose there are two persons left, so it will be of this form, minus x and plus x. So this amount will go to this, and this amount will become 0, and this amount will also become 0, and both of these if conditions will not execute in that case. So that would be our like the finishing case, and this loop will stop when the multiset becomes empty. That means all transactions have been settled. So each iteration of the loop is counted as one transaction. So I take a variable count, and after each element after each settlement I can increase this count by 1, and here I can just print out this count. Okay, so let's try to run the code and see. So I'm getting 1 for this code, and let's verify also. So if there are like 3 persons, 0 owes 100 rupees and 1 owes 2 50 rupees, and 2 owes 0, 2 owes uh, 0 owes 100, 1 owes 250, and 2 also owes 150. Okay, this is a transaction like this. So these will also cancel out, but if it is 2 owes 0 50, then also there should be only one transaction. So let's see. 2. So in this case the answer should be 1, and if I make this amount as 30, then I should get 2 transactions. Okay, let's verify also. Right, so we are getting, if 0 has to give 100 rupees to 1, this has to give 50 rupees to 2, and 2 has to give 30 rupees to this. So we can say we can simplify it like this. So 0 gives okay, so we can say it's 0 gives 70 rupees here, and this guy gives 20 rupees to this guy. Okay, something like this. So net gain for this guy would be plus 50 minus 30, that is 20, and for this it would be 100 minus 50, that should be 50. Okay, and okay, let me correct this one. So net gain for this is minus 70. So yes, it should give 70 rupees, that is. Okay, yes, so it should give 70 rupees here, and this can give 20 rupees here, or we can say 0 can give 150 rupees, and 0 can give 20 rupees. I think that both are fine. So I think we will get this solution. Okay, so that's how we are going to solve this problem. So this has a debit of minus 70, and this has a gain of plus 50, and this has a gain of plus 20. Okay, so this is the solution that we will get from the algorithm. Okay, so I hope this is clear, and we will see some more stuff in the next video. Hi guys, so in this video I am going to take one extra step in the splitwise algorithm that will help us to also print who should pay what amount to whom. Okay, so I will be building the code again, and this time instead of taking integer nodes I'm going to take strings. Okay, so that will actually allow us to use map, and let's see how we can use map and solve this problem. Okay, so I will be writing the same algorithm, but this time I would be making more extensive use of standard template library, and the algorithm more or less will remain same. Okay, so I've just removed everything and I will type the code again. Okay, so let's remove this thing as well. So we are given this graph and we actually want to print out statements like these. So how much a person should pay to whom. Okay, so this time you can see the graph is of the type every node contains a string name, and we need to handle that. For that I will include header file called hash include map. Okay, so I will maintain a map, and that map will store how much is the net balance of person Rahul. Okay, so map of Rahul will tell me, okay, Rahul has to give 100 and he has to accept 40, so this value will be minus 60. Okay, so that value will go in the hash map, so net will be a hash map now. Okay, so that's what I need to do. So let's quickly write down the code, and that's one major change that we are going to make in this code. Okay, so I need to accept string xy because x and y are now name of the people. Then I need to enter the amount, and I need to scan all the transactions while number of transactions is greater than 0. So I can say, okay, read every transaction from x to y, and that has the amount. And you can see we also need to create a hash map here. Okay, so that we can do using map of string comma int. Let's call it as net, and here we can say if okay, so this is possible that that particular key does not exist in the map, so I can say if net dot count of x is equal to 0, so I will create that key and I will initialize it with 0. Okay, because in the array we had done a 0 initialization, and this is how you will do the 0 initialization in a map. You will check if the key is not present, and if net dot count of y is 0, if this is 0, then net of y will be also set to 0. After that we need to take the transaction into account. So what you will do, you will say net of x minus equals to amount, because x person is giving money, so his net will reduce, and y person is gaining money, so his net amount will increase. So that's the first step. Okay, and second step is we need to iterate over the map, iterate over the persons, and add those persons in the multi map or in the multi set, right, who have non-zero net. Okay, so either they have to take money or they have to give money. So we can iterate over the map using a for each loop for every pair that is there in the map. So that pair is going to contain two things. First is the person, that is p dot first, and then we have the amount that is given by p dot second. And you can check if net of that person is non-zero, that means his transactions need to be settled. So we will insert those values in the multimap. So this should be net. Okay, so small mistake here, and we should create a multimap here. So sorry, multiset. So multiset of pair of string comma int, let's call it as m. Okay, so we need a multiset here. Okay, now the first parameter in the multiset is a string, and okay, so multiset has only one parameter, that is a pair of string and int. So when I'm adding someone into my multiset, I'm also storing, okay, Rahul is the person and he has to make a net transaction of minus 60 rupees. So these two things I'm storing as a pair in the multiset. So this will help me to figure out the transaction between two people and print it also. Okay, so let's see, if net of person is non-zero, then I can insert in the multiset. So multiset dot insert make pair, and here I give person and the amount. Okay, so now you have to be very careful at this point, because when you're inserting things in the multiset, the comparison will happen according to the first object, okay, or the first parameter of the pair. So that's the default way multiset works, but we can change the comparison to second. So either you put amount in the first position or you write a custom comparator. Okay, so both can be done. So just to demonstrate this thing, I'm going to show you how you can write a custom comparator for multiset. Okay, so what we can do, we can write a class called person compare, and that will have a method that would be a public method like bool operator, and that is going to compare two persons. Okay, we have string int p1 and pair of string int p2, and here I can say return p1 dot second less than p2 dot second. So if the person 1 has less money than person 2, so that's how the sorting is going to be done. So this way we can ensure the sorting is done according to the, so we also need to pass this comparison class when we are initializing the multiset. Okay, so this way we can ensure that this is done in a proper manner, and you can just iterate and see if this is okay, right? Now we have the multiset ready. Okay, so we have initialized the multiset, and now we are at the third step of the algorithm, that we are ready to make settlements. Okay, so we will pop two elements from the multiset, one from the start and one from the end, and we will try to settle them. So let's say initial count is 0 while this multiset is not empty. I will find out the first pointer to the first person, that is m dot begin. I will also find the pointer to the last person, or the iterator to the last person, that is previous of m dot end. Okay, and now these two pointers are now pointers to pair objects. So if you want to access the amount of debit, that will be given by low arrow second, and if you want to see the name of the person, that will be given by low arrow first. Okay, and that would be a string. Similarly we can do for credit, that is high arrow second, and string credit person equals to high arrow first. Okay, so now we have the data, we know the two persons between which we can make a transaction. So let's try to do the transaction, and before that let's pop them out from the multiset. So I can say m dot erase low 1 and m dot erase high 1, because after the transaction we will have new data that we can insert in the multiset. So settled amount, let's find out how much amount can be settled. That will be minimum of minus of debit and credit, and that amount will be can be added to the debit amount. Debit plus equals to settled amount and should be subtracted from the credit amount. So credit minus equals to settled amount. So rest of the algorithm is almost same. We made little changes to handle the case, and here you can also print the transaction between people. Okay, so you can say see out the person who is going to debit will pay this much amount, settled amount, to the person who is getting credits, to the credit person. And after that we just need to check if the debit amount is non-zero, we can add that amount in the multi-set again. So here we have to make a pair between the debit person and the amount that is to be debited from him in the next iteration, and same goes for credit. So one of these values will be exactly 0, so only one of the if blocks will execute in each iteration. Okay, make pair the person who wants to take credit, if his credits are not completely settled, he is eligible to receive credits in the next iteration all as well. So that's what we do, and here we can increase the count by a value of 1, and finally we can just say cout count and endl. Okay, so let's try to run the code and see. Okay, so okay, there is some error in line number 19 here. Okay, I should put a comma, semicolon. Okay, so it says Rahul will pay 50 to Ajay and Rahul will pay 10 to Neha. So you can say Rahul, Ajay, and we have Neha. So I think this is correct. So Rahul will has to give 100 here, and Ajay to Neha is 50, Neha to Rahul like this is 40. So if you want to minimize, then Rahul will give 50 here and Rahul will give 10 here, and I think that's the correct solution. And you can see you have minimized the cash flow and the transactions. Okay, so that's all for this video, guys. I hope you got the idea, and I'm just saving this code so you can access this code at this link. Okay, so thanks a lot.
Welcome to the lecture series on network flow, and in this video we will discuss what is a flow inside a network of graph. So let us initially see a motivating problem that will signify what a network flow problem is. So let us just imagine a connected and directed and weighted graph like this. Suppose this is vertex A, this is vertex B, this is vertex C, this is vertex D, and these are connected like this, and these have some arbitrary weights like 30, 20, 10, 5, 15. So given a connected, directed and weighted graph, we can represent or we can imagine this graph as a pipe network. You can imagine these as junctions vertices as junctions and the edges as pipes through which anything or any material can flow, and these vertices act as the splitting point of the flow. We will describe what a flow is, but let us initially see some basic terminologies here. So in a network graph or in a pipe network graph, we have two special edges, or we have two special vertices. One vertex is known as the source and one vertex is known as the sink. Now let us define what a source vertex and what a sink vertex is. So now imagine a material flowing through this system from this source and following some path to this sink. And now we will define the source vertex. The source vertex produces the material at some steady rate. So any material which is flowing through the network is produced at the source, and the flow material is consumed at the sink. So the material which will be flowing in the network is consumed at the sink, and the rate at which this material flows is also steady. Now let us define the term flow of a network. So exactly, let us see what a flow of the network is. The flow of the material at any point in the system is intuitively defined as the rate at which the material flows. So flow is defined as rate at which material flows in the system. For example, imagine water is flowing in the pipe network and we want to know the maximum volume of water over time that can pass through the given pipe network. So these kind of problems are solved through the network flow graphs. So in the further videos, we will define some more terminologies and see some algorithm that will help us to solve the problems of maximum flow inside a graph or the network flow inside a graph. So thank you guys. See you next time. Hello guys, this is Sanket here from Coding Blocks, and today we are going to discuss some terminologies regarding the network flow problem. So as discussed in the last video, the flow of a material at any point in the system is intuitively the rate at which the material moves. So now let us know what the capacity of an edge means. So capacity of an edge is quite a different concept than the flow, as flow is the exact amount of material flowing through the edge flowing through edge, whereas capacity is the maximum amount of material that can flow through that edge. That can flow through a edge. So, for example, suppose there are two vertices A and B. So, the capacity between A and B can be a value x. So, if the capacity of the edge AB is x, then the flow F will always be less than or equal to x, as we cannot have flow more than capacity given through an edge. So now let us look at some other terminologies. Now we will discuss what is residual capacity. So residual capacity is defined as the difference of the total capacity and the flow of material through a given edge. So now I hope the concept of capacity and residual capacity is clear to you all. There is one more concept of residual graph. So if the given graph is represented in the form of its residual capacity of its edges, then the graph is called as the residual graph. So now let us look at the next terminology, which is augmented path. So the next terminology is augmented path. So what is an augmented path? An augmented path is a path from source to sink, a path from source to sink such that the the residual capacity on every edge is greater than 0. On every edge is greater than 0. So suppose there is a path such that there are vertices A, B, C, and D, and the weights are distributed as 2, 4, 0. So as you can see here, there is an edge which has 0 weight at its edge. So the residual capacity here is 0. So this path cannot be an augmented path. Whereas if the edges are given in this manner, like A, B, C, and D, and the weights are given as 2, 4, 1. So here you can see there is no edge in this path which is 0, or where the residual capacity is 0. So this path is accepted as an augmented path. Also, there is a concept such that flow on a particular path will be the minimum flow through at any edge. For example, suppose we are given a flow like A, B, C, D, and E, where the weights is given as 3, 10, 2, 4. So here you can see the the flow from A to B is 3, from B to C is 10, from C to D is 2, and from D to E is 4. So for this augmented path, for this augmented path, the maximum flow will be the weight of the edge with minimum capacity, or the minimum flow. So here you can see the weight with minimum edge is 2. So for this augmented path, the maximum flow will be 2. So I hope the concept of these basic terminologies is clear to you all, and I hope the concept of how the maximum flow for an any augmented path is called calculated is also clear to you all. So we will see how Ford-Fulkerson algorithm works in finding the maximum flow for a given network flow graph. So thank you guys. See you next time. Guys, this is Sanket here from Coding Blocks, and today we are going to discuss the Ford-Fulkerson algorithm for finding the maximum flow in a network graph. So before discussing the Ford-Fulkerson algorithm, let us see some few points that we should keep in our mind before finding the maximum flow in a network graph. So the first point is we cannot send the flow more than capacity on a given edge. So flow cannot be greater than the max capacity of an edge. The second point to keep in our mind is that for conservation of flow at any vertex other than source or sink, the amount of flow going in should be equal to the amount of flow going out. So, suppose for two vertex A and B, there is a connection like this. So, here the amount of flow going inside at every vertex should be equal to flow going outside. And we should keep in our mind here the source and sink are not included. So, excluding source and sink. Okay. And also, we should keep in our mind that for any augmented path, suppose the augmented path is given like A, B, C, and D, where the edges has weight like 10, 2, and 4. So, for this given augmented path, the maximum flow will be the value of the edge with minimum weight. So, the edge with minimum weight is 2. So, this 2 will be the max flow for this augmented path. So now our objective is to maximize the flow of the given network graph, and we should keep in our mind that no edges should go into the source and no edges should come out of the source. So now one last thing before seeing what the Ford-Fulkerson algorithm is, we should keep in our mind that any path that we are considering as an augmented path should have a non-zero forward edge and a non-zero backward edge, a non-zero backward edge, and a non-full forward edge. So this point we should keep in our mind. And now let us write the algorithm for Ford-Fulkerson algorithm for finding the maximum flow in a network graph. So let us write the algorithm. So according to the Ford-Fulkerson algorithm, initially what we will do is set up our directed residual graph with edge capacity is equals to the original graph weights. So suppose for our original graph between any two vertices there is an edge with the weight 10, then in our new directed residual graph initially we should keep the capacity as 10 among those two vertices, and then we will initialize a variable max flow with equal to 0, as initially we have not found the complete answer for our algorithm. And now we will loop in our algorithm such that while there exists any augmented path from source to sink, then what we will do is find the value f, which is the minimum edge weight along the current augmented path. Then what we will do is just decrease the capacity of all the forward edges by f and increase the capacity of all the backward edges by f. And at last, what we will do is just increase the value of max flow by f. And after iterating through this loop, we have found our result and we will just print max flow. So all you have to do is just traverse over all the augmented path in the given network graph from source to sink, and just for the current augmented path we will find the value f, which is the minimum edge weight along that path. And we know for a given augmented path the minimum edge weight for that path is the maximum flow for that augmented path. So we will find the value f, and then we will decrease the capacity of all the forward edges and increase the capacity of all the backward edges. And after doing that, we will increase our result value by f, and at last we will return the result value. So in the next video we will see why we decrease the capacity of the forward edges and increase the capacity of the backward edges, and we will also see an example of for Ford-Fulkerson algorithm for finding the maximum flow in a network graph. So thank you guys, see you next time. Guys, this is Sanket here from Coding Blocks, and today we are going to example dry run a graph for the Ford-Fulkerson algorithm. And also in this video, we will discuss why we were decreasing the capacity of the forward edges and increasing the capacity of the backward edges during the Ford-Fulkerson algorithm. So the logic behind the decreasing of capacity of forward edges is quite intuitive to think, because by sending a flow through the augmented path P, we will decrease the remaining residual capacity of the forward edges used in P. But the reason for increasing the capacity of the backward edges may or may not be that obvious. But this step is important for the correctness of the Ford-Fulkerson algorithm. So, by increasing the capacity of a backward edge, the Ford-Fulkerson algorithm allows any flow to cancel to cancel the part of the capacity used in the forward edge that was incorrectly used in some earlier flow. So what I'm trying to say is that the intuition behind the increasing of capacity of the backward edge is to cancel an already assigned flow. That is, if we have already assigned 2 units of flow from a vertex A to vertex B, if we have assigned 2 units of flow, then by passing 1 unit of flow from vertex B to vertex A, this overall flow can be interpreted as 1 unit flow from A to B, because the backward flow of 1 unit will cancel out the effect of the 2 unit flow. So the net unit flow from A to B will be 2 minus 1, that is equal to 1. So this step of increasing the capacity of the backward edge is important in order to maintain the conservation of the flow inside the network. So now let us dry run our code and see what the algorithm says. So let me just rub this graph, and now we will dry run our code in the following example. So for the following example, the source vertex is 0 and the destination vertex, or we can say the sink vertex, is 1, and every edge has a direction. So now we will apply the Ford Fulkerson algorithm and find all the augmented paths from source to sink, and for each augmented path we will calculate the flow, and for the flow calculated we will decrease the capacity of all the forward edges and increase the capacity of all the backward edges. So here you can see one of the augmented path from source to sink will be 0 to 2 and 2 to 1. So the first augmented path will be 0 to 2 and 2 to 1. So let me just change the color to avoid the confusion. So the first augmented path is from 0 to 2 and 2 to 1. And here you can see the minimum weight of any edge in this augmented path is 50. So the flow for this augmented path will be equal to 50. So for our final answer, that is our maximum flow, which was initially 0, we will increment it by 50. So now the maximum flow becomes 50. And also what we are supposed to do is decrement all the forward edges with 50. So now let me just decrement all the forward edges. So now 100 will become 50 and 50 will become 0. Okay, so now let us see the other augmented path. So one of the augmented path still left is from 0 to 2 and 2 to 4 and 4 to 1. So 0 to 2, 2 to 4 and 4 to 1. And here you can see in this path the minimum the edge with the minimum weight is 50. So the flow for this augmented path will also be equal to 50. And now we will increase our maximum flow variable. So now maximum flow will become 50. So 50, the maximum flow was earlier 50 and now it will be updated with 100. So now let us see the third augmented path. So another augmented path can be written as, okay, so I have not updated the older values. So let me just update the weight by the decreasing the flow by 50 again. So now here it will become 0, here it will become 0, and here it will become 75. Okay, so now let us see the next augmented path. So the next augmented path can be from 0 to 3, 3 to 4 and 4 to 1. So this will be 0 to 3, 3 to 4 and 4 to 1. And again you can see here the flow will be 50 because the minimum edge weight for any edge in this augmented path is 50. And now we will increment our max flow by 50. So now max flow will become 150 and we will decrease all the forward edges by the current flow, that is 50. So this will become 0, this will become 50 and this will become 25. And now here you can see we cannot have any other augmented path from source to sink, because for any augmented path we know the path should have non-full forward edges and non-zero backward edges. But here you can see we have completely filled our forward edges. So there cannot be any further augmented path. So our final maximum flow by using the Ford-Fulkerson algorithms comes out to be 150. So the final question arises in front of us is that how we will find all the augmented path. And I hope you all have watched the lecture for graph algorithms and you all have learned about depth first search. So we will use DFS algorithm to find the path from source to sink, and we will find all the path from source to sink, and we will apply Ford-Fulkerson algorithm for every possible path that will be obtained by using BFS. And use the usage of BFS in the Ford-Fulkerson algorithm for finding the augmented path is also known as the Edmond-Karp algorithm. So if we use BFS in our Ford-Fulkerson algorithm, then we will be using the Edmond-Karp algorithm. So I hope the logic for the dry run of Ford-Fulkerson algorithm is clear to you all. Try to dry run this algorithm on any other graph on your own, and in the next video we will try to implement the Edmond-Karp algorithm on our own. So thank you guys. See you next time. This is Sanketar from Coding Blocks, and this video is in continuation with the previous video in which we dry run our graph for the Ford-Fulkerson algorithm. So before implementing the Ford-Fulkerson algorithm using BFS, or I can say the Edmond-Karp algorithm, what I want to say here is that if you remember, when we wrote the algorithm for the Ford-Fulkerson algorithm, what we did is just increase for any augmented path, we were decreasing the weight for the forward edges, and we were decreasing we were increasing the weight for all the backward edges. But here you can see among any two vertices there is no backward edge between them. So in such cases what we will do is just hypothetically assume that there is a backward edge also in each pair of vertices. So here you can see I'm drawing some hypothetical backward edges with the blue color. Okay. Okay, so the weights for these edges will be initially equal to 0 because they are not initially present here. And if for any condition we are also given the backward edges with some weight, then we will give the weight given into our quotient for that particular edge. And now let us just again dry run our code and see what output we get. So for the first augmented path, that is the path from 0 to 2 and 1. So the first augmented path, that is 0 to 2 and to 1. So here you can see the flow value will be equal to 50. The flow value will be equal to 50. So for every edge, what we will do is just, if the edge is forward edge, so we will decrement our edge value with the current flow. So this will become 50 and this will become 0, and for every backward edge what we will do is just increase the value with the current flow. So this will become 50 and this also becomes 50. So now for the second augmented path, that is the path from 0 to 2, 2 to 4 and 4 to 1. So 0 to 2, 2 to 4 and 4 to 1. So here also you can see the flow value will be equal to 50. So the flow value will be equal to 50. So here you can see if the flow value is equal to 50, we will just decrement all the forward edges. So this becomes 0, this also becomes 0, this becomes 75, and increase all the backward edges. So this becomes 100, and here you can see I have not put the backward edge. This becomes 50 and this also becomes 50. So here you can see in this manner we will again traverse the graph, and if there is no backward edge present, we will hypothetically assume that there is a backward edge. And in our adjacency matrix representation of any graph, we represent if we represent the value of the edge with 0 when there is no edge present between any two vertices. So now in the next video we will try to implement this algorithm using our BFS algorithm for finding the augmented path, and then this will be transformed to the Edmond-Karp algorithm. So one more point that I want to mention, that there can be situations that here you can see I have chosen the path 0 to 2, 2 to 4, and 4 to 1, but I could also have chosen the path 0 to 2, 2 to 3, 3 to 4, and 4 to 1. That is 0 to 2, 2 to 3, 3 to 4, and 4 to 1. So this will also be a valid path. So which path we are choosing will depend on our BFS implementation, but the overall max flow value will never change, despite the fact that whatever path we are choosing. So if we choose the path 0241, then also we will get the same max flow, and if we choose the path 02341, then also we will get same max flow. So we will see in our code that how we will implement the BFS algorithm for modifying the Ford-Fulkerson algorithm for finding the augmented path using BFS. So thank you guys, see you next time. Hello guys, this is Sanket here from Coding Blocks, and today we are going to implement the Edmond-Karp algorithm for finding the maximum flow inside a network graph. So now let us start implementing our code. So we will make a user, we will make the program that will take the input from the user. So we will take an input V, which will denote the number of vertices, and an input E, which will denote the number of edges. So let us just take the input of V and E. And now we will prepare an adjacency matrix that will denote our graph. So in our adjacency matrix, every edge will denote the corresponding capacity it has for the network graph. So now let us just name the adjacency matrix as capacity, and here you can see I am using dynamic memory allocation to allocate memory for our 2D array that will represent the adjacency matrix. So I have prepared the 2D array, and now let us just finish its preparation. Okay, so here you can see I have completely formed our 2D array, and let us just take the input of the edges of our 2D array, or I can say of our adjacency matrix. So we will get E number of edges, and for each edge we will get 3 input, that is the starting edge, the destination edge, and the weight that will denote the capacity of that edge. So let us just take input of all the 3 parameters, and what we will do here is just fill our adjacency matrix from our source to destination and mark the capacity as C. Let me just name it as C. Okay, so here you can see we have prepared the input for our graph, and now let us first implement our BFS algorithm that will be used to calculate the augmented path in our Edmond-Karp algorithm. So now here I am writing our BFS algorithm. So now for Edmond-Karp algorithm, our BFS algorithm will take our adjacency matrix, that is the capacity, or I should say here the residual capacity. We will see why I am placing the residual capacity here. Then we will have a source, a sink. Also we will have the number of edges, and we will have a array that will denote the parent of each vertex. So why I have taken the residual capacity here? So the logic behind taking the residual capacity in our BFS algorithm was, as you can recall, that for every augmented path found in our network graph, what we were doing is just decreasing all the edges with the current flow by all the edges in our residual is in our augmented path with the current flow, and increasing all the edges in the reverse direction by the current flow. So after updating any edge with its capacity, what we were getting was the new residual capacity of that edge. So after every update we will get a new residual graph. So that's why I have taken the input of the residual capacity graph. So now let me just make a boolean array that will keep the visited parameter of our BFS algorithm, and let me just initialize our visited array by all the values as false. Okay, so here you can see I have initialized my visited array, and now what I will do is just prepare a queue for our BFS algorithm. So let me just change the header file to bits/std c++.h, so it will automatically include all the header files. And now here you can see I have also made our queue. So now let us just mark our source as visited and also push this source in our queue. Okay, and also I will keep a parameter found augmented path, that will be a boolean parameter. So why I am taking this parameter is because we also have to track whether we are able to found an augmented path by applying our BFS algorithm or not. So at last we will also return this found augmented path parameter. So now while our queue not becomes empty, while not queue dot empty, we will repeatedly do some task. So what we are supposed to do is just extract the front of our queue, pop it from the queue, and then for each vertex what we will try to do is just check if the current vertex is already visited or not. So if it is not visited and the residual capacity of the edge we are mapping is greater than 0 or not. As you know, we cannot reduce the residual capacity less than 0. So if the residual capacity of the edge from u to v, that is the front of our queue, and v, which is the current vertex, so the edge from u to v is greater than 0, so what we will do is mark the parent of v equal to u, and also mark v as true as we have visited this vertex, and also push the vertex v in our queue, and then we will check if the vertex v is equal to the sink or not, that is if we have reached our destination or not. So if we have reached our destination, we will make the parameter found augmented path equal to true, and we will just break the loop, otherwise the loop will be continued. Okay, so here you can see we have finally implemented our BFS algorithm. If you are not able to understand what logic I am implementing in the BFS algorithm, I would highly recommend you to first watch the lecture of the graph algorithms, and specifically watch the lecture of breadth first search algorithm. So now as you can see I have implemented the BFS algorithm. So now I will write one arbitrary function which will print all the augmented paths. So I will name it as print augmented paths, and it will take a parameter which will be a vector of vectors. So I will name it as augmented paths, and all we are supposed to do is just iterate over this vector of vectors, and then we will just print every element in these vector of vectors. So let me just place an endl also here. So here you can see we have implemented our utility function that was printing for the augmented path. And now we will implement our final function, that is the max flow. So I will write int max flow, and this function will return the maximum flow in our network graph. So here you can see I am taking the parameter of the capacity, or I can say the adjacency matrix, which is denoting our graph. Also I am taking the source, the sink, and the number of vertices v. So now here I will initialize one residual capacity graph, which will be a 2D array. So we will not make the changes inside the original array. We are making another residual capacity 2D array, which will be representing our adjacency matrix for our residual graph. So let me just initialize all the rows of this graph. Okay, so here you can see I have successfully initialized all the rows, and now I am making a parent array. So let us just describe it of 1000 size. It will not matter that much. And now we will prepare a vector of vectors which will store our augmented paths. So augmented paths. And now we will initialize a variable max flow with 0, and at last we will return this max flow. So let us see how we will update this variable max flow, which will denote the maximum flow in our network graph. So while BFS is returning any augmented path. So if BFS will return any augmented path, it will return true. So while BFS is true, and then just pass the parameter as residual capacity, source, sink, the number of vertices, and the parent array. So after passing this, what we will do is just prepare a vector which will denote the current augmented path. So current augmented path. And then what we will do is just get the parent of the vertex at v. Okay, so sorry, before this, let us just initialize our flow variable with int max. So what this flow variable will do, for all the edges in our current augmented path, it will find the edge with the minimum weight, and the edge with the value of the minimum weight edge will be stored in this variable flow. So let us just mark a variable v equal to sink, and we will iterate over v until v is not equal to source. So we will backtrace our path. So we will push back our current augmented path by v. So we are backtracking or backtracing our current augmented path, and then we will see what is the parent of the current vertex. So I have extracted the parent of the current vertex, and also if the flow, the overall flow seen till now is greater than the residual capacity of the current edge, then we will update the flow value by the residual capacity of the current edge. Also, we will now transfer the value of u to v so that the iteration continues. And at last, when we have successfully found our current augmented path, we will push back this current augmented path in our overall augmented paths 2D vector or vector of vector. So we will just push back this current augmented path in our total augmented paths vector. Okay, so here you can see we have backtraced our path from sink to source. So it is our duty to just reverse this path, so that whenever we will be printing our path, we will get the path from source to sink and not from sink to source. So we will use the reverse function already implemented in our C++ STL, and we will pass the iterator of the current augmented path. So we will pass the begin iterator, and also I will pass the end iterator. So here you can see we have successfully reversed our current augmented path. So I guess we should push back our current augmented path after reversing it. And also, before reversing our current augmented path, we should also push back the source in our current augmented path. Okay, so now as you can see, I have successfully added our current augmented path, and now what we are supposed to do is just increase the value of max flow with the current flow for that augmented path. And now here we will now update our residual capacity graph. So let us just again mark V is equals to sink, and until V becomes source, what we will do is just extract the parent of V, and then we will, if decrease the capacity for the forward edge UV by the flow, and we will increase the capacity for the backward edge. So we are decreasing the capacity for the forward edge, and we are increasing the capacity for the backward edge. And now we will just swap V with U. And here you can see we have successfully implemented our overall max flow algorithm. And now let us just call the print augmented paths function and just pass our augmented paths vector of vector. So now here you can see I've already prepared the input for the graph that was discussed in the previous video, and let us just run our code and see if it works perfectly fine or not. Okay, so here you can see there is a small mistake in our code, that is we were decrementing our flow from all the forward edges and incrementing our flow for all the backward edges. So for denoting the backward edge, we should write it as residual capacity from from V to U and not from U to V, which was written earlier. And also there is one more mistake, that is we should initialize our residual capacity graph with the initial values of our capacity graph. So let me write just a nested loop to initialize the value of the residual capacity graph with the initial capacity graph. Okay, so now let us just call our function. We will pass our capacity graph, our source as 0, our sink as 1, and V as the number of vertices. So let me just run our code. And here you can see we have printed all the augmented path, and also we have printed the maximum flow value for this network graph. So here you can see what we have did is just implemented a function that calculates the breadth first search for a given residual graph. And if we are able to find an augmented path using the breadth first search algorithm, we return true, otherwise we return false. So this function is quite explanatory in its own manner. And then we have written a print augmented path function which takes a 2D vector, or I can say a vector of vectors, and then print all the rows of this vector of vectors one by one. So So the final logic is written in our max flow function. So inside the max flow function, we are taking the parameter of our original graph, the source, the sink, and the number of vertices. And then we are initializing another graph which denotes our residual graph. So initially the residual graph will be equal to the original graph, and all the edge weights will be equal to the edge weight of the original graph. And then one by one we will decrease the edge weights and calculate the new residual capacity for each edge. And then we are initializing a parent array that will take care of the parent of any vertex of the current augmented path. Then we are preparing a vector of vectors which will store all the augmented paths which we will find using the Ford Fulkerson algorithm. Then we are initializing a variable max flow store which will store the final value of our max flow algorithm. Then while the BFS algorithm is returning augmented paths from the given graph, we will iterate, and then what we will do for the current augmented path, we will calculate the flow value. And as you can remind that the flow value for any current augmented path is the value of the weight of the edge which is minimum among all the weights of all the edges. So here you can see we are updating the flow value whenever we find any edge that has a residual capacity less than the current flow, and then we will update the flow. And here you can see for calculating the flow we are backtracing our path from sink to source. So as we have backtraced our path, we have stored the path in reverse manner. So to get the original path, what we will do is just first push our source in the augmented path vector and just reverse the whole vector so that we will get the original path. And then we will push this original path in our overall augmented paths 2D vector and just increase our max flow variable which will be returned at the end of the function with the current flow, that is the flow for the current augmented path. And after we have find the current flow for the current augmented path, what we are supposed to do is just decrease the all the it just decrease the weights from all the forward edges and increase the weight for all the backward edges. And if there is no backward edge, we will assume some hypothetical backward edges and increase its flow. And at last what we are doing is just printing all the augmented paths and just returning the max flow for the current network. So I hope the logic for this problem is clear to you all. I will highly recommend to try this code on your own and also try to implement this Edmund Karp algorithm, that is a modification of the Ford Fulkerson algorithm by using BFS, by using the linked list representation, or I can say the adjacency list representation of the graph. So thank you guys. See you next time. Hello guys, in this video we will discuss an application of the maximum flow problems in which we discuss the Ford-Fulkerson algorithm and its modification as Edmund-Karp algorithm. So in this video we will discuss about the application of the minimum cut problem. So what the minimum cut problem says is that in a flow network or in any given network graph, an ST cut an ST cut is a cut that requires the source and the sink to be in different subsets. So I think all you know about a cut in a graph. So a cut in a graph is a division which we will make in a graph so that graph is divided into more than one component. And in a network flow graph, an ST cut is a cut that requires the source and sink to be in a different cut, where S component will describe the component which will have the source, and the T component will be the component in which sink has been placed. And also it consists all the it consists of all edges going from the source side to the sink side. So in the ST cut, the cut will be described by the source and the sink, and they will be in different subsets. And also, it will consist of all the edges that will be going from the source side, that is the component which will contain the source, to the sink side, that is the component which will contain the sink. The capacity of an ST cut is defined as the sum of the capacity of each edge in the cut set. And what edges we are including? We are including all the edges that are going from the source side to the sink side. So to find the minimum cut, or find the minimum cut in a flow network, we will use the Ford-Fulkerson algorithm. So according to the Ford-Fulkerson algorithm, all we are supposed to do is just run our Ford-Fulkerson algorithm, run the Ford algorithm, and calculate the final residual graph. So the final residual graph will be made by calculating the maximum flow inside the flow network. And then after calculating the final residual graph, all we are supposed to do is just find the set of vertices that are reachable from the source. So all the vertices that will be reachable directly from the source will be belonging to the S component in which the source is present. And then what we will do is that all the edges which are not reachable vertex, all the edges which are non reachable vertex from a reachable vertex are minimum cut edges. So what I'm trying to say is that all the edges which are which are from a reachable vertex. So what is a reachable vertex? A reachable vertex is a vertex that is reachable from the source. So all the edges which are from a reachable vertex to a non-reachable vertex. So what is a non-reachable vertex? A non-reachable vertex is a vertex that will be belonging to the sink component. So all edges which are from reachable vertex to a non-reachable vertex are inside the minimum cut edges. So we will print all such edges. So uh, how the min cut problem is solved by this Ford-Fulkerson algorithm is that we get the capacity of the minimum cut. So how we are getting the capacity of the minimum cut? The max flow min cut problem inside a flow network states that the amount of maximum flow is equal to the capacity of the minimum cut. So we are not going inside the proof of how the minimum cut value is equal to the maximum flow, but just we need to keep in our mind that according to the theorem of max flow min cut, the maximum flow inside a network graph is equal to the capacity of the minimum cut. So for calculating the minimum cut, all we have to do is just find the final residual graph and then get all the vertices that are reachable from the source and the rest of the vertices that are in and the all the vertices that are from a reachable vertex to a non-reachable vertex are our minimum cut edges. So I hope the logic for finding the minimum cut value inside a network graph is clear to you all. So thank you guys. See you next time.
Hello everyone. Let us see how can I compute range queries using sparse table. Right. So first of all, what we'll see in this video lecture, we'll see what is the structure of the sparse table, how to construct a sparse table, and how to perform query operations on a sparse table. Okay. So guys, first of all, the most important thing that we need to understand is that any integer can be written as a power of 2, right? That is, 5 can be written as 4 plus 1, 2 can be written as 2, 10 can be written as 8 plus 2, right? 15 can be written as 8 plus 4 plus 2 plus 1. Basically, if I write any integer in some powers of 2, then what is the minimum powers that I have? That is equals to, that can be at most log of n, right? Log base 2n. So basically, this is the main concept of using sparse table. Okay, so I'll explain it in more details in the coming time. Okay, so guys, let us see what is the structure of sparse table. Okay, so basically, as we can see from the name, this sparse table has a table type structure, that is a matrix. Okay, so what does sparse table do? Sparse table can perform any query operations in log n, any range query operations in log base 2n, right? And for some functions that are idempotent functions, I'll explain you what is an idempotent functions. When we'll see this third part of the query part, then we'll easily understand what is an idempotent function. So for idempotent functions, sparse table computes range query in log of in O of 1. Okay, so basically, if we have idempotent functions like min, max, gcd, right? So these range query for these functions that find a minimum in the range L2R, maximum in the range L2R, gcd of the range L2R, this can be easily find out by sparse table in O of 1, easily computed. Okay, now let us see further. Okay, I have actually made this array to demonstrate you, so I have to erase all this. Okay, now guys, it's a structure, right? So basically, we'll have a matrix, let's name it mat. Okay, so it will be a table type structure, and this matrix will be of, let's say we have an array on which we have to perform these operations. So let the length of the array be n. Okay, so we have n, that is the length of the array. I'm just making some variables. After this video, I'll also code down this parse table and run it for you all. Okay, and m equals to log base 2n ceil plus 1. Okay, you know about the ceil function, right? Floor and ceil. Okay, so basically what I'll do is, we'll have a matrix of n cross m size, right? And in this matrix of n cross m size, what will we do? We'll okay, let me write it and then I'll explain it to you. Let me write a matrix. Okay, let's just make some rows and say make the value of n. You will get the construction of sparse table after this, and basically n is 1 2 3 4 5 6 7, so we can have m greater than equal to 4, right? Right, so okay, now let's say the array was 1 2 3 4 5 6 7, 1 2 3 4 5 6. Okay, I have made it of 6, but it won't matter, right? M can be greater than equal to log base 2n ceil plus 1. Okay, it won't matter, but m should not be less than this. You'll get this. Let's continue in the video, you'll understand why am I saying this. So guys, what does I have named it mat, right? So basically, what does mat ij contains? That's the main question, right? I comma j, that means ith row and jth column. Okay, so let me just name it, and 0 1 2 3 4 5. Okay, right, so mat ij, that's the main thing about the this structure, that what does actually mat ij contains. So this is the most important thing to understand, right?
So mat ij, the value at position ij in this matrix contains that if I start from I and my length goes till I plus 2 to the power j, right? So if I start at I, let's say I'm at 1 and I have length is 2, okay? So matrix of 1 2 will contain, matrix of 1 2 will contain that if I start at 1 and my length is of 2, then my range is from 1 to 2, right? So if my range is from 1 to 2, that I'm currently at position 1 and my range is, okay, here my j is 2, right? So basically what's my range now? J is 2, that means this j is 2, so my range is of 4, not 2, okay? So if I start from 1, my range is of 4 length. So from if I started 1, my range of 4 length will be from 1 to 4, that is equals to 1 plus 2 to the power j minus 1, right? Why am I saying this, guys? Because let's compute some ranges, okay? Let's say I'm starting at position 0 and I want a range of length 10, right? So basically my range will begin from 0 0 plus 10 minus 1 na? Because 0 to 9 will be the range of length 10. I hope this thing is clear, that why I'm doing minus 1 over here, right? So what does matrix ij contains? Let me raise this. So matrix ij contains that if I start at I, my answer for the range 2 की power j, okay? So basically what does matrix 1 0 contains? 1 0 contains that if I start at I, that I started 1, my range for 2 की power 0, that is 1, so 1 to 1 only, okay? What does 1 1 contains? That is if I started 1 and my range for length 2, that is 1 to 2, right? I hope you're getting this. What does my range matrix 1 to 2 will contain? The range that 1 to 2 will contain started 1 and the total range of this is 2 to the power 2, that is 4. So basically 1 to 4. Have you got this? 1 to 3 will contain 1 to 8, right? So basically matrix ij contains answer for a range starting at I and going till I plus 2 की power j minus 1, okay? Similarly guys, okay, now coming back to the construction of sparse table. Right, so coming back to the construction of sparse table, let's say I have an array, I have made this array of length 6 na. So let's say I have this array of length 6, okay, length is 7, indexing from 0 to 6, right? So let me write some values, 1 2 3 4 5 6 7. Let's take these values, this is an array and these are its indexes. So guys, if I start from position 0 and I try to fill this cell, what does this cell means? 0 comma 0. This means that if I start at index 0, my length for 2 की power 0, that is 1 length answer, that is from 0 to 0 itself, right? So basically this column, this whole column will contain the answer for I to I, right? This 0th column, because 2 की power 0 is length 1. So if I start at any I, my answer for length 1 will go from I to I only, right? So let me fill answer. So if I start from 0 to 0, my answer is 1. I'm right now constructing sparse table for min query, okay? I have to find range min query, so my answer means minimum of that range, right? So if I start at 1 and go to the power go to the length 1 only, then my answer will be 2, because we have 2 over here. Similarly 3 4 5 6 and 7, right? So first construction part is done. How is this construction taken place? The first column, it has been constructed on the basis of length 2 की power 0 is length 1, right? So if I start at any I, my length is 1 only, so I to I will be my total range. Now guys, now it is the most important part to understand about the construction. Now guys, if I want to fill this cell, what does this cell mean? This cell means that I start at 0 and my length should go to 2 की power 1, that is length 2. So from 0 to 1, this cell should contain the answer from 0 to 1, right? Because what does my matrix ij means? Answer for the range I till I plus 2 की power j minus 1. Okay, so how will I construct this answer? Now this is my this is the question. So the most important part to again see about this is that we are working in powers of 2, right? Let's say I have to construct an answer for range I, and then I have to construct answer for I to I plus 8, means the length is of 8. Okay, let's take length of 8. I have to fill the length 8. So guys, basically if this length is 8, I have to construct its answer. What I can do is I can divide it into two parts, right? This part, what does this part contain? I and 4. And what does this part contain? I the answer for this part, where is the answer for this part? The right part, it is I plus 4, right? And 4 means from the index I plus 4, length of 4, and from I, length of 4, right? So basically if I talk about this I, let's say this is index I, and I want to construct the answer for I and length 8, right? So what I need is I length 4 and I plus 4 length 4. This is I plus 4, right? So I plus 4, if I have I plus 4 length 4 and I length 4, then I can easily combine them in O1 operation. The minimum of these two will be my answer for I8, right? Basically let's write a recurrence relation for this, so so that you can understand it. Yeah, so basically there's just one thing that you need to realize is 2 की power j is equals to 2 की power j minus 1, right, into 2, right? What does this mean? That if I have to find what is at 8th place, I can easily find it by current place, that what is it at 4th place, right, and its 4th place, right? Basically we can also write it as like this. The main function that will become 2 की power j can be represented as 2 की power j by 2 into 2 की power j by 2, right? So I have divided my range that is of length j, length 2 की power j into two other ranges of length 2 की power j by 2, right? Again coming back to construction, let's see the construction of sparse table. Continue it. Yeah, so guys, what will be at this position at this index? It will be starting from 0 and length 2, right? Which means is if I start at 0 and I go to length 2, so I can divide the 2 into other two parts, right? What are the other two parts? If I start at 0 and I go for length 2, that is 0 to 1, I can easily say na ki if I start at 0, answer for length 1, and if I start at 1, answer for length 1, right? Then I can easily compute the answer for 0 to 1. So basically its answer is kept here. Minimum of these two will give me the answer for this current cell, right? I've got this. Why am I doing so, guys? Again I'm trying to explain this thing, that for a particular I, I'm computing length that is a power of 2, right? This is a power of 2 length. So if this length is a power of 2, I have already computed my answer for the length that is less than this power of 2. Basically 2 की power j minus 1 I have already computed na, right? You can easily see this. I have already filled 0, I will compute 1, then by using 1 I'll compute length 2, then I already then by using 2 I'll compute 3, and then by using 3 I'll compute 4, right? Have you got this? Okay, let's move further. So if guys I have already computed some answer for length of 2 की power j minus 1, then by using that answer I can easily compute the length of 2 की power j. So for I, if I go to 2 की power length 2 की power j, so what answers do I need? I length how much? 2 की power j minus 1. Tell me the answer for I and length 2 की power j minus 1, right? And tell me the answer for I plus 2 की power j starting at this index now, and other 2 की power j minus 1. Basically my whole range is divided into two parts, right? So and where are the answer for these two parts? It's already been kept here, right? So let me fill this table. Enough discussion. So if I start at 0 and I want the answer for length 1, where is my answer? At from 0 of length 1 and from 1 of length 1, minimum of these two will be 1. Again minimum of these two will be 2, 3, 4, 5, 6. I won't compute its answer, this cell's answer. Why won't I compute this cell's answer? Because if I start at 6 and I want to compute answer for length 2 की power 1, that is 2, it's not quite possible na. Why? Because my array is finished over there. That's why I won't be able to compute its answer, so I'll leave it blank. Okay, now guys, try to understand the next step. Again I'll use the same step here. So if we are at currently this column 2, right? So if column is 2, what does this mean? That for any I have to compute the answer for length 2 की power 2, that is 4, right? And for each I have already calculated answer for length 2, that is this column is already filled na, right? Basically what I'll do is I'll divide 4 into 2 parts now, na? So let's divide 4 into 2 parts then. So if I have to compute answer for from 0 and length 4, so what I can do is I can compute answer for 0 till length 2, and then I can compute the answer for 2 till length 2, right? So total I'll have length 4. So where is my answer for 0 and length 2? It's over here, right? If I start from 0 and I want the answer for length 2, and if I started 2 and my answer for length 2 is over here, basically I want minimum of these two over here, that will be 1, right? I hope you're getting this. Why is this how I am trying to construct this matrix. So if I have to compute these answers, so where are my answers kept now? One answer over here, other answer over here, minimum of these two will be 1, right? Now again coming to this other next cell. So for this cell, what do I need? From 1 I need length 4 answer. So basically from 1 I take length 2 answer, and from 3 I take length 2 answer. That will give me answer for length 1 to 2, 3 to 4, right? So this whole will be covered, right? So where is this answer for length 2 and starting from 1? It's over here, and from 3 starting here. So minimum of these two will be 2. I hope you're getting this. How am I filling this sparse table, right? So in the similar fashion, by using the same recurrence relation, I can fill the sparse table completely. Okay, now let's try to move forward. We are done with the construction part. I'll build this. I'll also code it out. Okay, so let's come on the second part. So structure is clear to you. Structure is n cross m, where m can be greater than equal to log base 2n plus 1. Okay, and I've shown you how to build this sparse table by using the property of 2, right? So basically what I have done is I've just divided a particular range into two parts. If a range is of length 8, divide it into 4 parts. If the range is of length 16, divide it into 2 parts of length 8. Okay, and for any range of length 8, answer for 4 is already calculated, right? So for any range of length 4, let's say, how was this length 4 built? It was built by taking 2 ranges of length 2. How was this built? By taking 2 ranges of length 1, right? So basically there is just one operation that I'll do to build this array, right? Okay, to build this matrix. Now guys, let's see the third part of this sparse table, and then after that we'll try to understand ki, when will this query work in O1 and when will this query work in log n. And after that also I'll code this sparse table. Okay, so guys, query. Yeah, we are on the query part. So now how will I query pass table, right? How will this pass table give my answer in O1 about minimum? Let's take minimum range. Okay, what is the minimum element in a range? Minimum range query. Let's first talk about this, then after this we'll talk about some range sum query. Okay, right? So let's talk about minimum range query. How will this give my answer in minimum time, right? So for this, let's build a array. Okay, assume the sparse table is already built. So let me index it. Okay, the length is 11. So guys, now let's see if I want to query for 2 to 7. Let's take this range 2 to 7. So what is the length of this range? The length of this range is 7 minus 2 plus 1, right? What is this range? 6. Okay, so I have a range of length 6 and I want to ask for the minimum range query from this sparse table, right? So guys, if I have a range of length 7, what of range 6, है ना? So what I can do is I can divide this range into two parts of length 4, right? How is this happening, guys? Don't worry, it's not wrong what I said. Don't think that it's wrong. Okay, I will divide this 6 into range of two parts, that is 4 and 4. How? 4 from range 4 from starting from 2 and range 4 starting from 7. Okay, so basically I have two ranges, that is 2 to 5, one range of length 4 and other ranges starting from 7, that is also of length 4 only. Okay, so basically from 4 to 7. So guys, if I take minimum of these two ranges, then I'll get my answer, right? Why am I saying so? Because we can easily see that. Okay, let me color it. This is the first range and this is the second range, right? We can see that these two boxes are overlapping, 4 and 5. So what guys, let them overlap, है ना? This is an idempotent function, minimum. If I have to compute minimum, it is an idempotent function, na? What is an idempotent function? If I take something extra, then also my answer won't change. So basically I am repeating this twice, na? I am taking minimum of 4 and 5 twice. So what? The answer won't change, na? Because it's minimum, it's intuition, right? You can also search about idempotent functions on Wikipedia and learn about them. So I hope you got what this means. Even if there is some part in the given algorithm that is overlapping, then also I will get my answer, right? So basically guys, what how will I get my answer for this query? The query was from 2 to 7, na? 2 to 7. So what I have done, I divided into two ranges, 2 to 5 and 4 to 7. So guys, where is the answer for 2 to 5 kept? Actually it is starting from 2 and length 4, right? 2 की power j is 4, so j will be 2. So basically my matrix of 2 comma 2 will contain answer for this range 2 to 5, right? And where is my answer kept for 4 to 7? Again starting from 4 and going till 2, right? So 2 to 2, that means starting from 2 and range 2 की power 2, and starting from 4 and range 2 की power 2. If I take minimum of these two values in the matrix, in the above matrix, right, I'll get my answer for this range 2 to 7, because whole range is being covered except for the fact that this part is being covered twice, but it doesn't matter because it's an idempotent function, right? So guys, I cannot use the same logic for range sum query, right? That's where this sparse matrix lacks. Okay, so there are some disadvantages of this. Okay, what is the advantage of this? For idempotent function, it will calculate the query in O of 1 only, right? O of 1 is quite fast, na? Range query in O of 1, it's quite fast because I just have to take minimum of two values that are kept in a matrix at certain positions, right? So let's take this distance. Oh sorry, distance I'm saying, disadvantages. What are the disadvantages? That for non-idempotent functions it will work in log n. I will explain you how it will work in range sum query. Okay, for non-idempotent function it will work in log n, right? And one more disadvantage is that it does not support update operations, because once the matrix is built, it's built. Otherwise you have to make the whole matrix again, right? So guys, what is the time complexity to build this matrix? We can easily see that matrix is of n cross m, where m is approximately log n, right? And there are few places that I'm not filling even, right? These places I won't fill na. This I won't fill, this I won't fill. Why I won't fill this? Because length is 4, so from 4 I cannot take anything that is length 4, right? Because it's length 3 only at max. So there are various places that I won't fill na. So whole table is n log n only, and there are various places that I won't fill, so my complexity for this will be less than n log n somewhere, right? Because there are few places that I'm not going to fill in the matrix. Okay, so uh, so on an average we can say the complexity to build is n log n. Okay, approximately n log n, but faster than n log n. Okay, have you got this? Now guys, trying to get this. It does not support update operation. Advantage is that it will give my range query in O of 1 only. Okay, I hope you got this. Now guys, let's discuss about the second function, that is the range sum query function. Okay, so what is about this range sum query function, right? So guys, let's say I want to compute answer for 2 to 7. Let's take the same case. Okay, so for 2 to 7, if I want to compute range sum, okay, how will I compute range sum? By using sparse matrix. First of all, I will build the sparse matrix by taking addition instead of minimum, right? So basically my matrix ij will represent if I start at I, then sum for the range 2 ki power j, right? So that part should be clear to you by now. Now guys, how will I calculate the range sum? What is the length of this range? It is 7 minus 2 plus 1, that is 6. 6 is the length. So guys, 6 can be written as 4 plus 2. So if I take my answer from 2, I'll take answer for length 4, and from 5 I'll take my answer for length, oh okay, from 6 I'll take my answer for length 2, then I'll get my answer now in just 2 steps only, right? Because every range can be written as some powers of 2. So let's start at 2. I'll take answer for 4 length, that is 2, 3, 4 and 5, right? And then I'll start at 6 and I'll take answer for this 2. So where are these answers kept? In the matrix 2 comma 2, and this answer is kept in matrix 6 comma 1, right? So these answers are kept over here. So basically I just need these two values to compute my sum of the whole range, because these two values are already calculated na, in the matrix, right? Okay, now there is just one important thing. There is a slight tricky case over here, right? So what is the tricky case over here, guys? When my range is of length that is an exact power of 2. Okay, let's try to understand that case. There are two cases. First case is not power of 2, second case is power of 2. So for 6 I already told you that is not a power of 2. So for any number n, where n actually, let's not write it n, let us write it as range, length of the range. Okay, so for any number range, what I'll do is I'll compute its lowest 2 ki power. That is for 6 we get 4, right? 5, for 5 we get 4, means a power, the highest power of 2 that is just less than this number, right? So for 8 guys, what will be the highest power of 2 that is less than 8? It will be 4, right guys? I won't take 8 here. I have got a tricky case. I won't take 8. Okay, in the case of 8, if my range is of length 8. Why? Because for the range of length 8 I can easily calculate my answer by using two ranges of length 4 na, right? So what I'll do is I'll calculate two ranges of length 4 by taking the power of length 4, है ना? So guys, I hope you got this. So you must also be thinking here, for length 8 I can easily do it. From any index I can compute this position, right? Matrix I comma 3 will give me the let's say if the range is L comma R and its range equals to 8 only, R minus L plus 1, then my answer will be kept here, L3, right? Starting from L and range is 2 की power 3 8. So guys, if you want to do this, you can also try doing this, but we have to make a separate case then, right? So instead of making a separate case, what I do is I'll just break 8 into 2 powers of 4, length 2 lengths of 4, right? So by using that I can easily compute my answer. Okay, so guys, let me see you in the next video, and in the next video we will code sparse table. Hello guys, let's see the code for sparse table. Let's try to build a code. So first of all, let's make a structure called sparse table. Okay, and in this structure, what does this should contain? It should contain a 2D array. So let's take a vector of vector, okay, and let's name it mat, right? Now let's take two other variables called n and m. Basically, first of all, what I'll do is I'll initialize it with some value, right? So let's make an initialize function in it, and in this function I'll send two variables that are n and n. Okay, so how will I initialize this? First of all, what we need to do is let's set n equals to underscore n and m equals to underscore m, right? So let us fill these n and m values, because I will be using these n and m values while building my matrix, right? And now for other, what do I need? Let's resize matrix by n, right? And then okay, so basically let me just write it here also, size and log and 2D matrix. Okay, now we have n and m for that, and we have to compute this matrix. So let's also resize this matrix by m, right? Because it's a 2D matrix na. So mat I dot resize by m, right? Now after performing this for loop, I have got this matrix as a 2D vector, right? Two-dimensional matrix. Okay, now guys, as discussed above, that we also need power of 2 for this na. So there are two ways to take power of 2, right? So when do we need power of 2? While calculating query, because I already said we need the lowest power of 2 for every range of the query. So if I want to compute them, I can use log base 2. That's an inbuilt function that will give me a log value, but guys, that will take a lot of time, right? Log base 2 function takes a lot of time. If you will call it again and again, this code might give a TLE. Okay, so for that, let's make another array, and that array will store log base 2 that I already discussed. Okay, so let's name it as p2 power of 2, right? So again, p2 dot resize, and let us resize till n, and for let us fill this p2 array, right? Let's resize till n plus 1, because we need power of n also na, log base to n also. Why? Because there can be a query that goes from 0 to n minus 1 and its range will be n, so I need log base to n, right? So let's compute this till power n plus 1. Okay, so I 0 to I less than n. What's the recurrence relation to calculate this power value? The recurrence relation to calculate this power value is this. Okay, let me write it here. We all know about this na, log base 2 n equals to log base 2 n by 2 plus 1, right? So let me write it here. Okay, initially it is 0. Let's start by 1. So p2 I by 2 equals to p2 Okay, p2 I equals to p2 I by 2 plus 1 I by 2, right? So after having been finished with this initialization function, what we have got here is we have got a matrix, 2D matrix. Initially it is all filled with zeros, and we have got a vector, that is power of 2 vector, that I need to calculate my queries, right? So let us begin with this. Yeah, now let's try to build a function. Let's try to write a function build. Okay, so in this function build, what I'll do is I will just pass an array, right? There can be various ways to code it. Okay, you can definitely, if you don't want to write it as a structure, you should not write it as a structure, right? It depends totally on you. I prefer coding in this way because it is easy to understand. All the functions have their unique identification over here, and moreover this is generic, right? Because we can use it again and again for every test case. Let's say we are having various test cases, so we just need to initialize this structure in every test case. So if I'll initialize it and then make this means I'll just, for every test case, what I can do is we can write it over here key sparse table something, right? And in every test case we don't again need to clear the things up, because again a new structure is being initialized. I hope you got me, right? So that's why I prefer using data structures in a structure type variable, right? In a structure type variable, right? So let's move forward. Now how will I build? Let's say I have passed an array A. So how will I build this? First of all, what we need to do is we need to fill the base case, right? So how do we fill the base case? What is the base case? The first column, this first column that I filled, right? Key length 1 key, what is the answer for the length 1? So currently I am trying to build this parse table for minimum value, right? So what will be for length 1? For length 1 the value will be mat I 0, 0 means length 1, equals to ai, right? That's why I already sent n, because I'll use it again and again. Okay, so mat I 0 is equals to ai initially, right? Now let's compute answer for all these columns. Okay, so starting from j equals to 1 going till j less than m, right? Let's compute answer for these values. Now again for each column I'll go for each row int, right? I'll go for each row, and for each row, guys, till which I will I want to go, because I already described this to you earlier that there are few places that I won't be able to filling that I won't need to fill my answer, right? Because there is no answer for index 4 of length 4, because total size is 6 only. If the size was 7, then I can fill this place, right? So basically, if let's say I'm at a current index I and I'm going to fill something of range the value j, and the range is 1 less shift j, right? 2 ki power j, right? So from if I start from I and the range is 2 ki power j, so I plus 1 less shift j minus 1, this is my total range, right? Starting from I and going to I plus 1 less shift j minus 1, right? This range should completely lie inside my array. So how will I check this completely lie inside my array? That this point, this term, this term should completely lie inside this term, should be less than n, right? So basically I can write it as like this ki I plus 1 less shift j should be less than equal to n, है ना? That's the r part of the range, right part. Okay, so basically 1 less shift j should be less than equal to n. Now all these i's are valid for the particular j, right? Now guys, very simple, I have already discussed this matrix ij will be equal to minimum of matrix I j minus 1, right? For length of it I am dividing into two parts of length 4 and 4, and also equals to I plus right? So basically already I have told this to you. For length I I will be going for length 4, and then I plus 4 of length 4, right? These two values I need. So basically what I have here is matrix I plus 1 left shift j and length j minus 1 again. I hope you got this. Okay, you can try writing different values for different ranges. Okay, and now finally my table is being built. Okay, if you want to compute the sum, then what will you do? You just replace this minimum by addition. Okay, so that will compute the ranges, because these are disjoint ranges, right? Okay, now let me write this query function. It's a very simple function. It will be of type integer. Okay, so int l to int r, I'll ask for a query, right? So how will I ask for a query? Simple. I already told you, let's compute the lowest power of uh, the length of the range, right? So how will I compute? Let's name it pw and make it equals to p2 r minus l, right? So for 8, what will I get for 8, guys? Tell me. If the range is from 0 to 7, so total length is 8. But guys, total length is 8 na. I need power that is less than 8, basically 4 and 4, right? So how will I get this? I'll just simply subtract r minus l. I'm not doing uh, right, I'm not doing r minus l plus 1. Key, tell me the log base 2 of r minus l plus 1, that is the original range. I'm not doing this. Why? Because I actually need, for this 8 I need 4 and 4. Okay, try to pause this video and think about this, what I'm trying to explain it here. Why am I doing r minus l and why I'm not doing r minus l plus 1? Because there are few numbers that are in the ranges of power of 2. Okay, so for this number, what I have here is, I have these two values, right? Basically what I will return, I'll return minimum of two values, that is the value starting at l and range how much, this value pw, right? And other, what will be the other value? I told you na ki 4 from the left hand side and 4 from the right hand side. What is 4 from the right hand side? It is r minus 1 left shift pw plus 1. Basically this will be the starting point na. If I want 4 from the left side, that means let's say I want previous 4 window. Where will that window start? 7 minus 4 plus 1 pe. It will start at this point, that is 4, and it will go till 7, right? So the length will be of 4 only, j minus pw. I hope you got this, right? So basically I have completely written the structure of sparse table to find the minimum value in a given range. You can try using this function, this structure. And also there's one more thing, that you can write for query also of sum, right? So try building a sparse table yourself to answer the range for a sum value, right? Range sum query. Okay guys, thank you. I actually see a slight error over here, that we understood it right, but we just wrote it wrong, right? Just think about this line. So what happens here is that for a length 8, I want an answer starting from 0 and of length 8, right? Basically my j will be 3. So what does this mean? So 1 2 3 5 6 7, from 0 I want the answer of length 4, that is from 0 index I want the answer of j minus 1 range, and from the index 4 I want the answer of j minus 1, right? So how will I get this index 4? Should be equal to I plus 1 left shift j minus 1, right? Okay, I mean to say is minus 1, because I want this to be plus 4, right? Not plus 8. Should be j minus 1, right? Change. Some of you might have got it yourself. So this was it. Try to write a code, find the summation of a range, and in that We just have to change the query part and the minimum part. Here we need summation. It is not that tough. Just divide the query into ranges of 2 and just move forward, right? So guys, thank you. Hello everyone, let us see what is the lowest common ancestor, and let's discuss this topic, and further on we'll understand the concept. We'll see all possible ways of finding the lowest common ancestor of two nodes, and after that we'll try to optimize that algorithm further, and also we'll also try to find lowest common ancestor by different means, okay, in different ways. So prerequisites for this video is sparse table. You must know about sparse table. The video has already been provided to you all. And the second prerequisite, Euler tour, right? So Euler tour has also been provided to you all. So these are the prerequisites for this video, right? So first of all, try to understand those two topics and then come on to this topic, right? So guys, let's try to code it. Okay, let's try to see what is lowest common ancestor. So lowest, let's write it LCA. I will speak LCA, okay? Let's define it. Let's take define LCA as lowest common ancestor. Okay, so when I'll speak LCA, your mind should say lowest common ancestor. Okay, so LCA of two nodes of X and Y is that first of all there are various ancestors. Okay, so what are ancestors of X and Y? So an ancestor is a node that occurs in the path from X to root. Okay, so if I move from X to towards root, then ancestor will come in the path from X to root. Okay, now what is common? The word common will tell us that if there are ancestors of X and ancestors of Y, then there may be some ancestors that are common in both. There has to be ancestors that are common in both. Why? Because both are ending at root, na? So at least root will be common in both, right? So there has to be a common ancestors in both of these paths, right? Now discussing about we have heard about ancestor, we have heard about common. Now discussing about lowest, the third term, lowest. So out of all the common ancestors, we'll consider the ancestors that is the lowest. Lowest means lowest, right? That means it has more depth. The highest depth ancestor or the lowest ancestor. I hope it sounds clear to you. Let's take examples to make it more clear. Okay, for example, let's take these two values 5 and 10. So guys, what are, if I write the path from 5 to root, then I go from 5 to 2 to 1 and 10 to 3 to 1. So what's the common ancestors? 1, and what's the lowest among them is 1, right? After this, let's take another good example. Let me write 13 and let me write 10. Okay, let's find lowest common ancestor of 13 and 10. So writing these paths 10, 3 and 1, and 13 to 12 to 11 to 3 to 1. So these are ancestors of these nodes 10 and 13, right? What are the common ancestors? 1, 3, right? And what is the lowest among them that has more depth? It is 3. So basically 3 is the lowest common ancestor of 10 and 13. I hope it sounds clear to you now ki what is the lowest common ancestors of these nodes. Okay, let's take another example, a third variation. Okay, let's take 11 and let's take 16. So for 11 we have a path 11 to 3 to 1, and for 16 we have a path 16 to 15 to 12 to 11 to 3 to 1. So what are the common ancestors? 11, 3 and 1. Basically, what's the lowest among them? It is 11, right? Because 11 is at more depth than 1 and 3, right? So LCA for 11 and 16 is 11. Basically, we have key if if one of the two nodes, let's say if I'm okay, let me write it here now. If I have finding LCA of two nodes x and y, right? If x is ancestor of y, that means as x was encountered in the path from y to root, then LCA is x. Okay, like for the third example, 11 and 16, because 11 was an ancestor of 16 na? So 11 will be an LCA, right? It's intuition also and it's common sense also, right? Now because it will be the lowest, otherwise all the ancestors of x will be above x, and if y is an ancestor of x, then LCA will be y, right? So these are some small corner cases. Now let's understand how to find lowest common ancestor. So guys, the basic brute force approach to find the lowest common ancestor is okay, let's try to find the lowest common ancestor of this 10 and 15. Okay, so currently I am trying to find the lowest common ancestor of 10 and 15. So what will be my algorithm in this? Let me erase all these. Right now I'll discuss the brute force approach, the basic approach of finding the lowest common ancestor, and then we'll try to modify that approach to optimize that approach. Okay, right. So let's try to find the LCA of 10 and 15, right? So guys, what's the LCA of 10 and 15? We can easily see that it's 3. Okay, now let's see how to find this. So guys, what is depth of 10? Okay, let's mark depth values. Let's take some depth values. So this is at 0 depth, first depth, second depth, third, fourth depth, and fifth depth. So 16 is at fifth depth, right? Basically these are levels of the tree. Now what I'll do is I have two pointers, one is at 10 and one is at 15. So the pointer that is at 10 is at a depth 2, and the pointer that is at 15 is at the depth 4. Firstly what I'll do is I'll make them have equal depths. So I have to move this pointer to one step up and other step up such that both the pointers are on the same depth, right? What does this mean is I'll move 15th pointer to 12. That means currently I'm on 12, but still my depth is 3 and the depth of 10 is 2, and I'll again move on to 11, right? So I have jumped 2 steps above. The pointer that was at 15 is now at 11. Okay, there are 2 pointers. I'm using 2 pointer. Now guys, both of these pointers are at the same depth, right? So now it's pretty intuition, or we can say it's clearly visible that if I try to move both the pointers together upwards, then wherever they'll meet the first time will be the lowest common ancestors. Let me write it. Move both pointers together now. Together. Move both pointers together, right? Because now they are on the same depth. Now when I try to move them together, what does this mean? That I am trying to move both of them one step above. They are always on the same depth, and if they encounter a particular node, that means if they are on the same node, right, that means that node will be the LCA. So moving them together, the pointer comes here and this pointer comes here. Now we can see both of these pointers are pointing to the same node, so this node will be the LCA of 10 and 15. Okay, let's take different examples. Try to pause this video and try to have this try to run this algorithm yourself. Okay, now let me take another example. Okay, so which example should I take? Let's extend its 3, otherwise let's take it 17. Now let's make it 18, make it 19. Okay, okay, now let's try to find LCA of 19 comma 16. Okay, so my one pointer is at 19, other pointer is at 16. Now what I'll do is, first of all I have to move both of them to the same depth. So which is at more depth? The pointer which is at 16, I'll move it above. This will come to depth 4 now. Now we can easily see that they are at the same depth, because 19 is also at depth 4 and 15 is also at depth 4. Now the distance from 19 to root is also 4, and distance from 15 to root is also 4, right? Okay, so basically I have 2 pointers now which are on the same depth. Now let's try to move them together above. In one step this pointer comes here and this pointer comes here. Another step this pointer comes here, this pointer comes here, right? And now in another step the pointers come on 3. Now we have encountered a position where both these pointers are pointing to the same node. This means that both these paths from 19 to 1 and from 16 to 15 to 1 will pass through 3. Okay, I hope I have made it clear to you all how to find ancestor using 2 pointers. Okay, so basically this is the first brute force algorithm to find the ancestors of 2 nodes. Now let's discuss its complexity. So what am I doing is I am trying to find depth. First of all, I have run a DFS on the tree to store depth of every node. Depth. After that, what I am doing is I am trying to go over parents, right? From one node I am trying to go to its parent until I find the same parent, right? Basically I'm going to all the ancestors, so I'm moving them to the same depth, and from the same depth I'm moving upwards to the same ancestors, right? I hope I have made it clear to you all. So what is the time complexity of this algorithm? So time complexity is on, right? Why? Because it's a worst case complexity. Let's say I have this tree 5 and 6 7 8 and 9. Now let's say I have to find the LC of these 2 nodes. So the pointers will move above, then above, then above, then finally come here. So I have to travel the whole tree now. So basically it takes O of n time. So the worst case complexity will be On, right? So the complexity of this algorithm is On. If I have to find the ancestor of 2 nodes, I can do it in On, right? So in the next video I'll code. Okay, so I think I should code this in this video only, and in the next video what we'll do is we'll discuss approach of finding LCA of 2 nodes in log of n only. Log of n, right? Not n, log of n. In log n we'll find LCA of 2 nodes in the next video. So let's try to code this. Let's try to code this in the next video itself, right? Okay, so guys, thank you for watching this. In the next video I'll code the current algorithm, the basic 2-pointer algorithm, and in the next video, the next to next video, right, in that we'll discuss how to find LCA in log n only by using sparse table or sparse matrix, and in the video after that we'll code the log n solution to find the LCA of a node. Okay, so thank you. Okay guys, so let us try to code this brute force approach to find LCA first, right? So let's input n, and in the input I have taken the graph, same graph that I have made in this over here, the same tree, right? So let's make it, let's code it, right? And there will be n-1 edges, so let's push them in the adjacency list. Always remember guys that LCA depends upon root, first common ancestor, because we are following the path from a node to the root, right? So if you change the root of this tree, LCA will change for the nodes. So always remember this, right? So I have just inputted the whole graph. After this what I need to do is I have to mark depths, right? We need depth, so let's start a DFS currently taking the root as 0. Okay, root as 1. Let's take 1 as the root because I've already made this, starting from 1 and passing on the parent, right? Void DFS int current int parent. And also guys, we need to store the parent of every node. So simple, how to store? Let's make an array called parent. So here what we can do is parent of current equals to parent, right? And for auto x, going to the adjacency list of the current graph, if x not equal to parent, then dfs x comma current, right? It's a basic code to perform a dfs written, right? Now in this dfs I have just marked the parents. I also need depth, like what is the depth of a current node. So depth of x will be equal to depth of current plus 1, right? So if the initially starting with 0, depth of current is 0, right? And after every moment of time the depth will increase. Okay, so let's try to print them. Cout I, depth of I and parent of I, just to be sure. And I will go from 1 to n. Right, see, we can see this. Depth of 1 is 0 and parent is 0, depth of 2 is 1 and parent is 1, depth of 3 is 1 and parent is, see, depth of 3 is 1 and parent is 1, right? Depth of 4 is 2 and parent is 2, right? So I hope you got this. Parent of 6 is 5, parent of 16 is 15, right? And depth is 5. I've just coded in front of you everything. I'll just mark it. Now guys, if I have to find LCA of two nodes, let's write a function. Okay, int LCA brute. It's a brute force, right? To find the LCA of x and y. So let me see out LCA root of, let's say 18 and 16, right? 18 and 16. Let's just try to print this LCA of 18 and 16. So guys, first of all what I need to do is I have to move them to the same depth, right? So while, okay, what we can do here is, first of all we need to know na ki which one is at more depth and which is at less depth, right? So let's take x to be at more depth. Okay, so if I'm always assuming that x will be at more depth, then what we can do is, if depth of x is less than depth of y, swap x comma y. So if depth of x will be less than depth of y, then I have swapped x and y. Basically I have all basically after this swap may take place and this swap may not take place, right? So but after this, always depth of x will be greater than depth of y. It can be equal to also, right? So okay, let's start this now. So if let's make a corner case. If x equals to y, return x, right? If both of them are equal, let's return them only. And after this, take x to be at more depth. Or guys, it will be better if we take u and v, because generally we take u and v in graph, right? So that you don't get confused, u and v. Let's talk about u and v now. Okay, so always depth of u is greater than depth of v, means u is more down than v, otherwise they are on the same height, right? So while, what I'll do is, while depth of u is greater than depth of v, because it is always greater than depth of v till now, or it can be equal to, in that case while loop will not run. So while depth of u is always greater than depth of v, what will I do is, u equals to parent of u. Okay, I'll move u one step forward, step upward, right? Till the time depth of u equals depth of v. Now they are they are at the same level, right? Okay, now they are at the same level. Now when they are at the same level, what I need to do is, while u not equals to v, what I'll do, u equals to parent of u and v equals to parent of v. I'll just move them one step upwards together, right? And after this while loop ends, u and v will be equal, because they have to be equal, otherwise they reach the root and then they will be equal, right? Because LCA always exists. Then I'll return u or v, anything, because both of them are equal. I hope I just used 2 pointers over here. Let's try to run this code, check some errors. No errors, right? So what is the LCA of 19 and 16? It's 3, right? We can easily see here, and let's check for some other cases also, so that we don't miss out anything. What is the LCA of 9 and 9? It will be 9, right? And what is the LCA of 9 and 2? 9 and 2. So LCA of 9 and 2 we can see is 2, right? So it is 2. I hope you got this. This is the first algorithm. It will take O and time. Let me write it. Don't get confused. Don't try to use it in the contest, okay? Because in that ON approach won't work, right? In the next video we'll discuss about how to modify this thing. While depth of view I am increasing it by 1 na? In the next video we'll discuss how to jump to parents, so that in login steps we can cover this while loop, right? And in the login steps we'll cover this while loop also, so that our complexity to find LCA is login, right? Okay guys, see you in the next video. Let us discuss about the optimization find LCA in login. So guys, in the previous video we discussed about the approach when we were trying to move the pointers one by one above, right? We were just moving parents, right? So guys, instead of moving one by one, what we can do is we can use the technique of binary splitting or binary lifting, right? So what I'll use is we can say I'll use an advantage that every number can be written as binary number, right? So okay, let me give you an example first, then we'll continue on. For example, if I have to find let's say I have to find the third parent of 16, right? What's the third parent of 16? So what is the first parent of 16? First parent of 16 will be, let me write it here. The first parent of 16 will be 15. The second parent of 16 will be 12, and the third parent of 16 will be 11. How can I easily find out the third parent of 16? Write 3 in binary form, right? So find second parent of 16, that is this one, and then find, that will be 12, and then find the first parent of 12. Basically I have divided it into 2, that is 2, right? If I have to find the, let's say I have to find the fourth parent, I actually have done binary splitting of a given tree. I'll show you how, okay? Firstly, right now try to understand that every number can be divided into binary parts, right? And those parts are at most log n only, because the contains at most log n digits in binary, right? So let's say for a particular node x I have to find its 30th parent. Okay, tell me what is the 30th parent. So this 30 can be split into, okay, let me write over here only, right? say this was a tree, and for a particular value x I have to find its 30th parent, right? How will I find the 30th parent? I can easily write 13 powers of 2, that is 16 plus 8 plus 4 plus 2. Do is I'll find its 16th parent, and then I'll find its 8th parent, I'll find its parent, and then I'll find its second parent. This will give me 30th parent of x, right? I hope you're getting this. So how many steps did I perform? I performed only log n steps over here, right? Why? Because when I try to write a number in binary, that will be 1110, then there are at most log n set bits, right? Okay. So right now what we are discussing is to find the nth parent of a node, right? So to find the nth parent of a node, we did is binary lifting or binary splitting, or in short we used the property of binary numbers, right? Okay, so let's move forward now. So this was the first approach. Now guys, let us see how to make these binary numbers, like how to jump on from x to 16 in one step. Now how to jump on from that to its 8th parent in one step, right? So guys, for that we can easily use the data structure that has already been explained, called sparse matrix, sparse table, whatever, right? So for every node, what I'll do is I'll try to store for every node, let's say parent. This is a sparse matrix that contains I comma j. So what does this mean? That the value at parent I comma j will be equal to ith 2 की power j parent. Okay. In short, what does this mean? If I write for an example, okay, if I try to write, let me erase this. For example, let's take 16. What will be parent of 16 comma 0? Parent of 16 comma 0 will be 15. Why? Because 0 is 2 की power 0, that is, it is actually 16th का first parent, right? That is 2 की power 0th parent. Parent 16 comma 0, 16 comma 1 will be 12. Why? Because 2 की power is 2, so I have to find the second parent of 16, that is 12, right? And this will represent 2 to the power 2, that is 4. Basically 16's 4 parent, that is 3, right? And this will represent 2 to the power 3, that is 8, which will be equal to how much? Which will be equal to how much, guys? 0, because I will consider 0 to be the universal parent. Initially we will mark it as 0. So if there is no value, so if there is other value other than 0, that means that parent exists. Or if it is 0, let's say it is actually connected to 0, let's take 0 as the universal parent. Otherwise we'll just fill it with 0 only. Okay, so basically parent 16 comma 3 is 0, 16 comma 4 will also be 0, it will be 2 to the power 4, 16th parent of 16, right? I hope you got this, and so on. Guys, what will be the table size? Basically I here, I is going for all the nodes, I here is going for all the nodes, so this will take n space, and all the node I have to compute 2 to the power jth parent. So guys, for a tree of range 10 to the power 5, what will be the value of j? We can take j easily as 18, or in short it as 20, right? It won't matter. So j can go till 20 and I can go 10, so that it will be n cross 20. In short, n log n, c of log n plus. Basically this part has already been explained in the sparse table. video tutorial. What is the size of a sparse table? Ki how, what size should be of a sparse table? Okay, so basically we construct this sparse table. So guys, how can we construct this sparse table? Let us see how can we construct it. Again, see, let's take, if I have to let's fill the base case that will be parent of some I0, that I filled the first parent of number that will be parent that I will pass in the recursion, right? So basically it's a recursive relation. So parent of I comma 1 will be, think about it this, what will be the parent of I comma 1, 2 to the power 1, what it will be? It will be 2 to the power that its first parent and its first parent, right? Let me just say it again. Let's say this is let me number them also, 6, and let's say this was a chain, and what is the zeroth parent of this? It is equal to 4. Now guys, what is the parent of this? So I can write this first parent as iska zeroth parent and zeroth parent, right? Basically I can split 2 into 2 parts, 1 plus 1. So I find its first parent that has already been calculated, that is 4. It will be equal to parent of 4 comma 0, right? Zeroth parent ये है and its zeroth parent is 3. What is the zeroth parent? It is 2 to the power 0 is first. I hope you got this. You should again see, if you are not getting this, you should again go to the sparse table video and look at that properly, right? Okay, let me construct other examples now. So guys, what will be I comma 2? What it will be? I have to find out what is the 2 to the power 2th parent of a node. So 2 to the power 2th parent of a node will be its 2 to the power 1th parent and its 2 to the power 1th parent, right? Basically I have divided 1 2 3 4 this length into 2 parts, that its 2th parent and its 2 to the power 2th parent, right? So it will be parent of how much? 3, right? Basically this value, or let me write it again. Guys, again I'm saying, please go for sparse table if you are not getting this. So basically what I have is parent of parent 4 comma 0, right? And with, and this actually how much? 3. So it equals to parent of 3 comma 1, which is also equals to which is also equals to 1, right? What is 1 here? It's 2 to the power 1, na? So this is 1. So what I get is I comma is 1. In how many steps? In O1 only. Why? Because this is already calculated. This is already calculated. For a j value, I need j minus 1 value, right? So for a j value, if I need j minus 1 value, I am iterating forward in a loop. So j minus 1 is already calculated. Then I am going to j, na? Right? It's like DP, top down DP. Oh, sorry, bottom up DP. I am filling the table in the bottom up DP manner, as in sparse table. I'm just filling the sparse table. Okay. Okay. Now again, moving on to the next step. What is parent of I comma? I'll do this for all the nodes, right? Currently, I'm giving you an example for the node 5. So what will be I comma 3? It will be parent of I comma 2 comma, right? So it's 2 to the power 2th parent will be 1, that is already being calculated over here. So it equals to parent of 1 comma 2, that means 1 to the power 2th parent, that is 4. So if there is no such root over here, no node here, then we just mark it as 0, right? 0 is the parent. I have taken as 0 as initial parent, so here it will be 0. So what will be the power third parent of I, it will be 0. Right? I actually marked all the 2 to the power parents of any node. So now if I have to find let's say I have to find, he gave me 10th, or let's say 12, or let's say 13, a good example. I have to find 13th parent of a node X, right? So how can I write 13? I can write 13 as 8 plus 4 plus 1, right? So how will I move my this node X? First of all, it will be equal to parent of X comma 3. Why? Because this will give me 2 to the power 3, that is 8th parent. Now X is equals to its 8th parent. Now again X will be equal to parent of X comma, why? 2 is 4, and now X will be equal to parent of X comma 0. Now how much? 0 is 1. So 8 plus 4 plus 1 will give me 13. So after these 3 operations, I have found out the 13th parent. After these 3 operations, I have found out the 13th parent of X. I hope you got this. So guys, pre-computing sparse matrix takes how much time? N log n, it has already been discussed, right? So if I can pre-compute in n log n and I can query everything in log n only, it's fast na, because 10 to the power 6 is the length. Let's say log n will be like 22 approx, right? So if I can answer every query in 22 instead of 10 to the power 6, so it's very clear, right? So my all the queries will be answered in log n. So this is one part of finding LCA, right? To compute sparse matrix and to jump to the parents. Now guys, again I'll use the brute force logic over here and try to explain you with a good example. Okay, let me erase this. This is the main part of the algorithm, to find the nth parent in log n, because n can be written as a binary number in powers of 2. Right. So guys, now let's take example 18 and 16. Let's take example of 18 and 16. So guys, initially what was I doing in the brute force algorithm? First I made or what should I write? Let's write bring both pointers to same level. Bring both pointers to same level. It means I bring both the pointers to the same level, right? And after that, when I have brought both pointers to the same level, what I need to do is now move the pointers again till I don't find a till I find a node that is different, that is same for the both the pointers, right? So basically move pointers upwards means to the parent till I find encounter same node, right? Actually I was doing this one by one in the brute force algorithm that I even coded. Now guys, I'll perform these both operations in log n only by using sparse table. So if I have to bring both the pointers to the same level, how can I bring both the pointers to the same level? I can bring both the pointers to the level by think about it, then we'll discuss. Pause the video, think. If this is over here and this is over here and I have to move two steps of, right? So what I'll do is I'll take the difference of the depths. Let's say diff is to depth of u, that is greater than depth of v, right? So let's say depth of u is greater than depth of v. So I have taken a difference. Right now the difference is 2. Okay, I have to just move u to its how much parent? 2th parent, that is different parent. Basically I have to move to its different parent, I got me, so that they come on the same level. So how will I move it to the different parent? Again simple. How? By I have already explained this, right? Very different this approach, 8 plus 4 plus 1 approach. right? So it can be done in log n steps now. So both the pointers can be made to the same depth in log n steps, right? By using sparse table. Now guys, both the pointers are over here. One is at 17 and one is at 12. I will code this in the next video, okay? Okay, so 17 and 12. Now what I need to do is I need to use my second step of the algorithm, that I have to move one by one above in the brute force, right? But what I will do is I'll try to move, listen to this properly because it's a little tricky, okay? So what I'll do is, let me go slow now. What I'll do is, if first of all I'll find this pointer and let's say u and v. We are on u and v right now. Firstly, what I'll do is I'll find use 2 की power 22th parent and v is 2 की power 22th parent if I have taken 22 as log n, right? That means I'm finding a really high parent, right? So if I'm finding a really very a parent that is quite far from them, and if that parent is same, then I won't do anything. Otherwise, if that parent is not same, then I'll move on to those parents. Why am I doing so? Now see why am I doing so, okay? Let's say I'm at 18 and I'm at 15, I'm at the same level. Now guys, if both of their parents are same, let's say this parent, that 18's 1 2 3 4, 18's fourth parent, this equals 15's fourth parent. So guys, this can be an LCA, but there can be other LCAs, right? So I found its fourth parent and I said that this can be its LCA, but I don't need it. Why? Because it's not necessary na ki it is the LCA, right? So what I'll do here is I won't go to their fourth parent. Now guys, coming down, what I'll do, I'll find their second parent, okay? So I found 18's second parent and 15's second parent. That will be 10 and that will be 11, right? So guys, if the parents are different, I'll move on to those parents. I'll move on to 10 and I'll move on to 11. Why am I doing so? Because currently I'm on the same depth. I'll move here and why? Because currently I'm on the same depth, and if I encounter different parents, that means I am on the different path still now. If I'm on the different path, let's move to the path, right? That's what I was doing in the brute force na. If I encounter a different parent, then I'll move on to that parent, right? So why am I trying to move backwards? Because okay, let me make it more clear to you all. Let's say I have to find the LCA of 18 and 15. Now we all know that LCA is 3, right? What I'll do is I'll just move 2 steps above, right? Because see, it is really important to understand the last step here, LCA, and this is some x and this is some y, but this height is same because now they are standing on the same depth, right? This let's say difference, so this difference is same because they are standing on the same depth, है ना? So guys, if I actually do not know what is this difference, right? The difference between LC and X, the difference of depth of LC and F, right? So what I can do is I can go to difference minus 1, that means this position, right? I go to difference minus 1 and I can easily know difference minus 1. How? If I try to find the parent of X and parent of Y and they are different, then I'll move on X over here, then again I'll try to do the same thing for smaller values of 2. Again I'll move X over here and Y over here, right? So there will be a time when I will be standing on LCA and just next neighbor and just next, right? From x I traveled here, and y I traveled over here. In the end, what will be my answer? My answer will be parent of x comma 0, right? Or we can also say parent of y comma 0, because now we know that both of their parents are same. I hope you got this, that I am actually trying to fill this difference minus 1 in the power, because I know na कि I can easily fill this difference minus 1 in the powers of 2 by using the trick that the parents will be different, right? Their parents will be different, right? Otherwise their parents will be same, right? Write it down and I'll code it in the next video to understand it more properly, right? Or should I take another example? Okay, let me take another example. Take another example. So it is 1 2 3 4. Let's take one more depth. 9 10 11 12 and 13. Let's take this example, and we have value of 10 and 13, 11 and 13. So they are on the same depth. So the first part is done. Now we have to do the second part. So first of all, I'll try to find 11's 20th parent. Let's take a great value, right? 11's 2 की power 20th parent, not 20th. 2 की power 20th parent. So that parent will be 0, and 13's 2 की power 20th parent will be 0. So if they are 0, I won't do anything. So now when I'll come to 2 की power 19 and so on. So now I come to 2 की power 3. Now let's directly jump to 2 की power 3, because for all these values we'll get 0, right? Now I have to find 11's 2 की power 3th parent. That will be 1 2 3 4 5 6. That will also be 0. And 13's 2 3th parent will also be 0, because 0 is the universal parent, right? Okay, now guys, now it's quite tricky to understand. Now try to understand. Okay, now I will find 2 की power 4th parent of 11, or 2 की power 2nd parent, that is 4th parent equal to 1 2 3 4, that is 7, right? And let's find 13 की power 2th parent. That will be equal to how much? 4. So this is, we can say na, these parents are different. 7 is different from 4, because earlier we get 0 and they were equal. So when I get this, my question changes to 7 and 4. That currently I am on 7 and currently I am on 4, and I have moved how much? I am at 2 की power 2th parent, and it's done, right? Basically my pointers are now at 2 and 4. Now what I'll do is, let's try to find 2th parent of 7. That will be equal to 1, and 13th and 4th. Let's try to find 2 की power parent of 4. That will be 1, right? So again we are getting the different values, right? So we won't take it. Why we won't take it? Because I already told you that we have to just cover this distance. How much distance? Difference minus 1, right? So I won't take this. Now moving on to 2 power 0. This will be 7 ka 2 power 0 parent. It will be 2, and 7 4th ka 2 power 0 parent 3. So 2 and 3, they are different. So we move on to 2 and 3. So basically now we are at 0, and now loop is finished, because we started at 20 and we finished at 2. So I have traveled how much? I have traveled difference minus 1 steps in how much time? Log in steps only. From 20 to 0 I am going, right? So currently I am over here. Now we know, now we are sure about one thing, that their both parents will be different. Why? Because again the same logic na. If they were not different, then we have already covered up that by performing this loop, right? If they were same, then we have not gone over them, right? Basically I have covered difference minus 1, so I am standing here. So this will be equal to the LCA, that is parent of u comma 0 and parent of y v comma 0. Both of them will be equal to how much? The LCA of these other two nodes. I hope I have made it clear. Otherwise you should try to write it down and think about it, that how am I traveling difference minus 1 depth, how am I covering this much, why am I using this property these parents are different and then I am trying to cover them up. Okay, otherwise what you can do is try to difference minus 1 in powers of 2 and then you can easily cover that by going over the parents, right? So in the next video we will code this thing, how to find LCA using depth. Right now we're finding LCA using depth, and in the next video, next to next video, we will see how to find LCA using time in timeout, right? And what is time in timeout? It has already been discussed in the Euler tour video. Okay, and after that we'll discuss how to find LCA using actually we code it, code or LCA using time in. Okay, so guys, see you in the next video. So guys, let us see how to code and how to find out lowest common ancestor of two nodes in log n steps by sparse matrix and using the advantages of binary numbers, also called binary lifting, right? Okay, so guys, this was the code that is already written in LCA brute force video, right? I already written this code over there. So this was my tree. Now let's comment these things out. Okay, or let's just erase it. Okay, and let's erase this also, LCA brute, or should I not? Yes, I should, or should I not? Okay, so guys, to find LCA now what we need to do is, okay, let's erase this, right? To find LCA in log n, what we need to do is, first of all I have to perform a depth first search, and in the depth first search I have to calculate the parent, or we have to calculate the depth of every node, because depth is important, right? Let's try to calculate depth of every node. So after this DFS finishes, we have depth of every node, right? Okay, now let's try to write a function called calculate sparse table, right? So this function will calculate sparse table for every value of every node of the tree. Okay, so after DFS, call this function and calculate sparse table. Okay, right, so let's start. Let's see how can we calculate sparse table. Again, the very simple approach. What I said was key already discussed here, that parent of current 0 will be equal to the parent that I am coming from, that will be passed on this recursion. Okay, that means its first parent. Now what will be other parents? We have a simple recursive relation. So parent current j, that means 2 की power jth parent is equals to currents 2 की power j minus 1th parent and its j minus 1th parent. I hope you got this, right? I have already explained this. This is equals to parent of current j minus 1 and j minus 1. So this part is already calculated because we are moving in that way in the for loop, right? Like bottom up dp type, and this is already calculated because we are because in the DFS we are coming from this node, right? Because this node will be somewhere above in the tree and we are already coming from that node. That means that nodes, all these that notes the value, all these parents values are already filled. I hope you got this. Why I'm saying this? Let's say when I reach at 3, then for 2, it's all the parents answers is calculated na. That's why I can use the parents answer of 2 in 3, right? Okay, just like dynamic programming. Okay, right. So let's try to code it out. So calculate sparse table, current and parent I have passed. So basically I need this sparse table. Let's name it parent only, and I have to give it m because log of something. So I've taken 22 to be in the upper limit, right? For 10 to the power 5 you can give 20, that's the safe limit. Okay, so parent of current 0, that means its first parent is parent that I have passed on with recursion, right? Now let's try to go for all the other nodes starting from j equals to 1, j less than m, j plus plus. What will be now the reconciliation that I have already discussed? So parent current j will be equals to parent of parent current j minus 1, right? Because I have divided into two parts, and j minus 1, right? Okay, so when this loop finishes, what I'll do is I'll just continue my calculate sparse table. It is actually DFS only, and it's going for all the nodes. But when coming to a node, okay, sorry, when coming to a node, it has already calculated the sparse values of a parent, of all the parents, all the ancestors. Okay, so let me write it. Right, so it is x comma correct, right? So I hope this works fine. So this is a function that calculates the sparse table, that builds a sparse table for every node. Okay, right, it should work fine. So right, okay, now where were we? Let's try to find LCA using depth. Int LCA using depth. Okay, so let's say we have two values u and v. Let's take u and v only, u and v. We have to find LCA of them. So I'll just apply the same brute force thing, but in the brute force we use while loops na, to move one step above. Here we'll use binary lifting, otherwise everything is same. Okay, so if again, if depth is already calculated, let me check. Yeah, depth is already. And also guys, you can you can merge these two functions in depth first search only, because this is also performing a depth first search only, right? You can write them both in the same function, it's your wish. I'm just explaining here, right? So if depth of u is less than depth of v, swap u comma v. So after this what we have is, okay, before this let's make a case. If u equals to v, return u. Okay, if they are equal then return u. So we have made the corner case. Now after this what I have is depth of u is less than v, swap uv. What does this mean? Now depth of u is always greater than depth of v. That means u is somewhere down than v. Okay, so now guys, already explained here that I have to cover up some difference. Okay, I erased it up. So basically there is a difference between those depths na, so I have to move those two pointers to the same depth. So how can I cover up that difference? Let's mark that difference and let's name it depth of v. Okay, depth of u minus depth of v. Why I have done depth of u minus v? Because u is greater than v. Depth of u is greater than depth of v, right? So this is the difference. Now start from I equals to how much? M minus 1, go till greater than equal to 0 and I minus minus, or basically, yeah. Okay, now guys, what I need to do is I have to cover this step only, this difference step, right? That means I have to cover the difference of the two nodes u and v. So how will I cover the difference of two nodes u and v? Very simple. If the difference that bit is set, that means if diff right shift I and 1, that means that bit is set, that means I have to move that 2 की power step, right? So what I'll do is u equals to parent of u comma I, right? So what I am doing is just I have divided difference into powers of 2 and I'm moving one by one step above. Firstly, I am moving with the largest power of 2 that fits in it. For example, take the example of 15 na? So for 15 what I'll get is 8 plus 4 plus 3 plus 8 plus 4 plus 2 plus 1. I hope you got this. So after this u and v are on the same level. Let me write it. U and v are on the same level. What does the same level means? Same depth, right? So it's quite possible that u is an ancestor of v. So if u equals v is an ancestor of u, right? So if u equals to v, return u, right? This is the case if u was if v was ancestor of u. If v was ancestor of u, I have covered up the depth, the difference in their depths. I moved the two pointers to the same location, that means they are equal, right? If they are not equal, then what I'll do is I'll do my last operation, this operation, to cover the difference minus 1. How will I cover the difference minus 1? Again, let me write the same for loop over here, right? And what I need to do is just one thing. If parent of u, if u का to give ith parent not equals to parent of v का to give ith parent, then u equals to this and v equals to this. Move those pointers above, right? So finally here I am standing on different nodes, right? And both these nodes are child of LCA. So basically what I'll return parent u comma 0. I can also return parent v comma 0 because both of them will move on to the same thing, because I have moved both the pointers together. If I'm moving one pointer to some power of 2, I'm also moving the other pointer to the power of the same power of 2. I hope this thing is clear to you. Let's try to build this so that we don't get any errors. Yeah, no errors. Okay, now let's try to run this code. Okay, this is LCA using depth, and guys, in the next video I'll code okay, I'll first explain how to find LCA using time in and time out. So LCA using depth, let's find the LCA of okay 9 and 15. Let's take 9 and 15. What is the LCA of 9 and 15? It's 1, right? 1. Let's find 18 and 15. 3, right? 18 and 15. Let's try to write 15 and 15. I hope you got this. So basically my DFS, this function runs in how much? O of n. This function runs in on sparse table. This goes for every value of graph and basically om into n, right? And m is what? M is log n. You can take m greater than some value of log n, okay? And this LCA using depth, this works in how much? In the worst case it is O of log n. Why? Because here I am iterating over m different values, and here I am also iterating over m different values. So how much? 2 into log m, 2 into m, which is approximately log n, that is m, right? So instead of writing log n, we can also write it as, take this double equal to as you know, the congruency thing, right? Like this, I guess, you know, it is approximately equal to O of m. Okay, but m is approximately equal to on. And now let's take a case where the other is an ancestor of the other, 11 and 15. 11 and 16, take it 16. So 11 and 16, it will give me 11. I hope you got this. Try to write this code yourself first, and then we'll see this code, okay? And in the next video I'll discuss how to find LCA using time in and time out, okay? Hello everyone, we have already discussed about the brute force approach of lowest common ancestor, and also the optimization to find LCA in by using depth in log n, right? And now we'll discuss about how to find LCA using time in and time out values. What are time in and time out values? That has already been discussed in the previous videos. You can find it in which topic? Euler 2 topic, time in and time out videos, okay? So first of all, you all should know what is time in and time out, right? Now guys, it's a very clear cut thing. Actually this thing has already been discussed as, let's write, I'm just making two paths, okay? That this is the LCA, and this is some vertex, okay? This is some vertex u and this is some vertex v, okay? So first of all, what I was doing, I was making them both to the same depth, right? But now guys, I don't need depth, I just need time in and time out values, okay? So guys, again I have the same approach that I have already discussed, right? What is that approach? See, if actually I have to move u to this point, right? Which point is this? This is actually difference minus 1. So let's take difference as LCA, depth of LCA. Okay, let me write it properly. Let's take difference as depth of LCA minus depth of okay, it will be just the other way around because LCA will be at lower depth, right? So depth of u minus depth of LCA, right? Let's take it as difference, that this is the depth difference, right? Now guys, I have to cover up this distance. I have to cover this distance. I have to move u over here, right? So what's the best thing to do, guys? Again the same thing that I have used as the second step in the above algorithm. This second step, I was trying to move both the pointers upwards, right? Here what I'll do is I'll just try to move one pointer upwards. I'll just move u upwards and I'll not move b anywhere. B will be here itself, okay? So see, if parent of u, let's say ith parent of u, what is I here? It is actually 2 ki power I, right? So if 2 ki power ith parent of u was ancestor of v also, that means I don't have to move there, right? Because I have to come over here in the end. And how can I come over here? Such that I'll jump over here and I can come here, right? Because if parent of u is ancestor of v, try to pause this video and think about this line. If parent of ui, that is some big number, if there is some parent that is ancestor of v also, that means it's LCA or it's above LCA, right? Basically this is actually parent of ui, but it is not an ancestor of v, this node. So how can I come to this node? Again I'll use the same logic. So if this condition holds true, then I won't do anything, and if this condition don't hold true, what I'll do, I'll just move u above, make u as parent of u comma I, right? So basically first of all, where I will be at I equals to 20. So parent of ui will be 0 because 2 ki power 20 is too much I'll get that by sparse table, right? And how will I find is ancestor of V? That is this node ancestor of V or not? How? Basically, very easy, guys. It has already been discussed in the Euler tour video, right? That if how to find if X is ancestor of Y or not? If time in of X is uh, less than equal to time in of Y, and it's already discussed, right? Time out of X is greater than equal to time out of Y. If this condition, both these condition holds true, then X is an ancestor of Y, right? Okay. So if some parent of U is also ancestor of V, then I won't go to that parent. Otherwise, I'll move one step above. So guys, in the end, I will reach here by moving above steps. For in this case, when I'll come to I equals to 1, right? Then what I'll get? It's 2 to the power 1th parent. It will be this, and this is not an ancestor of V, right? And if it is not an ancestor of V, what I'll get is simple. I'll move U over here, right? Now again, what now I am at I equals to 0. So 2 to the power 0, that is first parent. Again, it is not an ancestor of V. I'll move U over here, right? So I have reached over here, and now my parent of U comma 0 is the answer. This is the LC. Okay, so let's code it down in this video only. Let's not write different code. It's a small video, right? So let's code it in this video only. So basically this is already discussed in the previous videos, how to find LCA using depth, right? Now let me just comment them out. Okay, wait. What I need is I need time in and timeout values, right? And how to find time in and timeout values? Whenever I've already discussed this, right? Time in current equals to plus timer, right? And timeout current equals to timer. Let's define timer now. Timer, right? And before going in the DFS, here I'll mark timer as 0. And also guys, we need to mark, because 0 is the universal parent, right? So we have to consider its case. So time in of 0 equals to, let's say 0, right? Because time in of 1 starts from 1, right? And time out of 0 should let's give it n plus 1, so that it becomes the universal parent. Because from 0 to n plus 1, it will cover all, it will overlap all the other ranges, all the other time in and time out for the nodes. Universal parent, right? It's the parent of the root, basically. That's why I've done this, right? So DFS 10, calculate sparse table, right? So I have completed a DFS. Now I have time in and time out. Now what I need to write is, I need to write a function which will calculate LCA using time in and time out, that I have already discussed. Let's write it, LCA using time. Okay, so let's take U B. Now simple, what will the base case is? If U is ancestor of V, so I have to write a function called is ancestor. That will be a boolean function. Bool is ancestor. So this will tell me whether U is an ancestor of V or not. Okay, so is U an ancestor of V? Okay, so what should it return? It return that T of U should be less than equal to T of V, and T out of U should be greater than equal to T out of V. I hope you got this, right? So let me just write a question mark over here, right? So if is ancestor, so if U is ancestor of V, that means LCA should be U, right? So write it like this, it will look short. Okay, so this means that u is ancestor of v if this returns true, right? Otherwise, let's say is v ancestor of u, then what I'll return v, right? Otherwise what I'll do is it's copy from here only, right? So I'll iterate for all the values, and let me, what did we discuss? If some parent, that is let me write it. Okay, if parent of u comma I, if this is not ancestor of v, then move to it, because I have to move to the difference minus 1 position, right? So how will I write this easily? If not is ancestor, so if parent u comma I is not an ancestor of v, then I'll just move to that position. In the end what I have to return is, I just have to return parent of u comma 0. I hope you got this. It's a pretty small code as compared to the depth thing, na? Okay, so let's try to write these values and match our answers from both the functions. Okay, so this is LCA using time. Let me copy it. Okay, this I have to, let's say in these four. See, 13511 from the LCA using depth and 13511 from the LCA using time. I hope you got these two methods of finding LCA. These are the best two methods to find LCA in a tree. And in the next video I'll take a question which can only be solved by finding LCA. Okay, least common ancestor of two nodes, right? So thank you guys. Hello everyone, let us see a good question, that why are we finding a lowest common ancestor of two nodes. Okay, so let's see a question, and let me write the question over here. Question says that if you move from x to y in a tree, you're given two nodes x and y, and there is a path from x to y, right? So you have to find the length of this path from x to y. Okay, so I hope you got the question. I have been given x and y two nodes, and I have to find the length of the path from x to y, and take the tree to be weighted. Okay, don't take unweighted tree. For example, let's construct a good example. Okay, and let me write some weights over here. Okay, so let's say okay, let me take another example. Okay, just continue with this example. Let's say I have given 4 and 6, and I have to find the length of the path from 4 to 6. So where will I go? I'll go to 4 to 2, then from 2 to 5, then from 2 to 6, right? So it will be 4 plus 5 plus 9. So this is how much? 18, right? I hope you got this 18. How we got 18 over here? It's a simple example. So I have to find the length of two nodes, length of the path of the two nodes where the graph is weighted. Okay, right? So think about it, and then we'll move on forward, right? Pause the video and think. Okay, moving on to the solution, guys. What we have here is that whenever I have to move from x to y, I'll go from x to LCA of x comma y, and from LCA I'll come back to y. That means from x I have to go somewhere till LCA, and I don't have to go up, because there is only one path such that no nodes get repeated, and after going to LCA I have to come back to y, because LCA was the lowest common ancestor of these two nodes. So the path from x to y will 100% go from passing from LCA of the tree, right? So let's try to code it, right? I hope you got this. The path from x to y will always pass through LCA. So guys, now what I need is, I need the distance from x to LCA, and I need the distance from y to LCA. Basically distance from x to y is equals to distance of x to LCA plus distance of LCA to y, right? Now again what I can do is, how can I find the distance from x to LCA and LCA to y? First of all, I can easily calculate LCA in log n. I've already coded it, right? Now guys, if I have to find the distance from x to LCA, what you do, take distance from root to every other node, right? So distance from root to LCA is 1, and distance from LCA root to 4 is how much? 5. Basically I have taken prefix of distances. This is 1 and this is 1 plus 5 is 6, and 6 plus 9 is 15, right? So I have written distances in green. Now I need to find the distance from x to LCA. How much is the distance from x to LCA? It is equal to distance from 1 to x minus distance from 1 to LCA, right? And what is distance of LCA and y? It is equals to distance of 1 to y minus distance of 1 to LCA. So distance of 1 to some 1 is the root, right? So distance from root to any other vertex can be calculated in only one DFS, right? As the same way we are calculating depth, in this way we'll calculate the distance, right? So what we need is the sum of these two, right? So let's add these two. What we get is distance of 1 to x plus distance of 1 to y minus 2 times distance of 1 to LCA, right? Because this plus this, and I have to subtract this thing 2 times, 1 to LCA. So this is my final answer, that is equals to distance from x to y. So to find distance of x to y, we need to calculate LCA and this distance values, okay? So guys, now let's try to code it. Let's try to code this question, right? So this was the code that I have already coded earlier, right? This was giving me the LCA, nah? So there's just one extra thing, that the graph is weighted. So if the graph is weighted, what I need to do is, I need to take a weight W, right? And we'll make this graph of weighted graph, right? W. Basically this is now a weighted tree, okay? Timer is 0, DFS, okay, calculates sparse table, okay. So let's go in DFS, and also we have to change a little over here. It will be pair of int comma int, because I have taken adjacency list of pairs, right? That the edge consists कि यहाँ से कहाँ जा रही है and its weight. Now here it will be x dot first, x dot first, and x dot first, right? Why I am doing first? Because I've already defined f as first, and x dot first contains where I am leading it, right? And what will be the distance? Distance of x dot first will be equal to distance of current plus x dot second. Why? Because x dot second is weight. Don't get confused guys, that I'm coding in the middle of, I'm not starting the code again because I've written everything. So I have pushed in the list y comma w. W is the weight, okay, right? So I'll change this input, don't get confused, okay? Change the input. Now guys, yeah, I've changed this function, and I also have to change this function, I guess, because x dot first it will be, not x dot x, right? X dot first, right? And do I need to change it? No, I don't think so. I need to no, yeah, now it should work fine. Let me build it. Okay, I haven't taken array distance array, distance, right? And also let's just remove these LCA, right? So the code is building. Now is what we need to do is, let's try to calculate distance between two nodes. So let's write a function called distance Okay, distance between x and y in a given tree. Okay, so let me write over here key C out distance x comma y, and x comma y will be, okay, let's just take this tree as an input. It has how many? 7 nodes. 7 nodes: 1 to 2, 2 to 4, 1 to 2, 2 to 4, 2 to 5, 5 to 6, 1 to 3, and 3 to 7. Right, so this is my tree. And also I need weights. 1 to 2 has weight 1, 2 to 4 has weight 4, and 2 to 5 has weight 5, 5 to 6 has weight 9. Okay, and 1 to 3 has weight 2, and that has weight 10. 3 to 7 is 10. Right, yeah. So let's try to build it. Okay, let me comment it right now. So let's try to find the distance between 4 and 6. 4 and 6. Okay, yeah. So distance between 4 and 6. So what do I need? Let me write that formula over here. What was it? The distance of x comma y equals to distance of x plus distance of y plus minus 2 into distance of LCA. Simple, right? So let's take LCA. LCA will be equal to, use any LCA technique, both of them are working. Okay, for this question guys, the root of the tree doesn't matter, because distance between the two nodes will be same na, if you use any root. Although LCA will change, but it won't affect my final answer. So let's find LCA using depth x comma y. I got the LCA. What I need to return is distance of x plus distance of y minus 2 into distance of LCA. I hope you got this. See, distance of 4 and 6 is 18. 9 plus 5 plus 4 is 18. Okay, let's try to write other distance values. Let's take distance from 1 to 7. 1 to 7. 12. See, 2 plus 10. Okay, so guys, I hope this question is clear to you. And guys, we have calculated it in n log n, this sparse table. This function runs in on, this function runs in n log n, and this distance function, this runs in how much? I've just called a function called find LCA. So this will run in how much? I've already discussed this, O of log n, right, which is actually m. And after this, just one step operation. So basically OM, this distance function runs in how much time? OM, where m is how much? 22 right now. I hope you got what is m, right? For n 10 to the power 6 you can take 22 also. For m 10 to the power 5 you can take 20. It's upon you. Always try to take two values above, because it's seal value. I've already explained that part. So I hope this question is clear to you, how to find distance between two nodes in a tree in only log n steps. So if there are let's say there are queries, and these queries are like 10 to the power 5 queries, key in every query tell me the distance between two nodes. So every query can be solved in OM, and I can easily answer all the answers into 10 to the power 5 into OM. That will give me how much? Approximately 10 to the power 6 operations, right? So we won't get a TL, it will run in 1 second, because we are able to find the distance in how much? OM, that is O log n in short. Okay, so guys, thank you for watching the video.
Hi everybody, this is Pulkit from Coding Blogs, and in this video we'll be discussing this problem called Beautiful Graph from codeforces.com. This is the link of the problem. You can read it out for yourself if you want to. Let's read the problem out. You are given an undirected, unweighted graph consisting of n vertices and n edges. You have to write a number on each vertex. Each number should be either 1, 2 or 3. The graph becomes beautiful if for each edge the sum of numbers written on vertices connected by this edge is odd. So basically, the for every edge, if u and v are the vertices that the edge connects, the number written on vertex u plus number on v should be odd, right? Calculate the number of possible ways of writing the numbers on the vertices so that the graph becomes beautiful. Since this number may be large, print it modulo this particular value. Okay. Note that you have to write exactly one number. Okay. The graph does not contain any self loops or multiple edges. The the first line contains number of test cases, then the standard stuff, which is the number of vertices, number of edges, then the next m line contains the description of the edges, right? So for each test case, we have to output the possible number of ways to write the numbers modulo this particular number. From this point onwards, I'll be discussing the solution. If you want to think the solution, you can pause the video, think it for yourself, and jump to the coding part to basically validate your solution, right? So if we see what are going to be the total number of possible ways, 3 power n, right? 3 raised to power n. We can try for each vertex, basically putting the numbers 1, 2 and 3, and for each way it's possible to check if the condition holds or not, but this is going to be a really expensive algorithm. It's going to be 3 raised to power n into some other factor as well, the time that will require to basically check each particular case, but we cannot afford it since the number of vertices and edges are up to 3 into 10 raised to power 5. So let's basically come up with something more efficient, and before that, let's basically analyze the first sample test case for which the answer given is 4. It says we have 2 vertices and 1 edge, that is 1 and 2. That's it, I think. Yeah. So if we basically write 1 on this and 1 on this, I'll list down the all possible 6 ways: 1 1 1 2 1 3, 2 1 2 2 and 2 3, and the other possibilities are 3 1 3 2 3 3, not 6, sorry, 9 possibilities, right? In this case the sum is even, so no. Odd, right? Even, no. Odd, even, odd, even, odd, even. So 1 2 3 4, these 4 cases are cases, so in this case the answer is 4. If you notice, I think that's pretty basic. The sum is going to be odd only if one of the numbers written in the neighbors is odd and another one is even. If both of them are either even or both of them are odd, the sum is always going to be even. So basically for every edge, we want the parity of the numbers that is written on the neighbors to be different, right? uh, Checking if we can basically represent our graph in such way that each edge has either 0 written on it, each vertex has either 0 written on it, or 1, where 0 represents even parity and 1 represents odd parity. If that's possible, then we'll see how to calculate the number of ways. But to check if that's possible, if you want to, you can pause the video and see what a bipartite graph is. This is basically checking if the graph is bipartite or not, right? I'll proceed with how to calculate the number of ways, but if you want to, you can have a look at checking if the have a look to check if the graph is bipartite or not. You can look on the internet, right? So now coming to the solution, we want our numbers to be such that if two vertices are neighbors, if they are adjacent to each other, one of them should have an even number written on it and one of them should have an odd number written on it. Let's just first see how to basically divide the graph in such a way that there's an even number on this node and there's an even number on this node. And let's say for a given connected component, if we see, we will have to calculate the number of ways for each connected component separately, right? Because one connected component has nothing to do with another connected component, because there will not be even one edge between those. So if we calculate the number of ways of assigning numbers to each connected component, let's say we had c connected components. Let's say the number of ways that we got are n1, n2, up to nc. What I'm trying to say is that my total answer is going to be the product of all these, pi I equals to 1 to c n I. That's what I'm trying to say, because I have to number each of the connected components simultaneously to decide for a to decide a particular way for a graph, so they'll be multiplied, right? So now my problem has been reduced to checking the number of ways if the graph is connected, right? Because each connected component is connected. Now for each connected component, if I basically start by from any index, from any vertex, let's say for this example 1 2 3 and 4, right? If I, let's say, give this the even parity, even, then these both should be odd and odd, and according to both of these, this should be even, right? Now I know for odd number I have exactly two ways to number them, either 1 or 3, and but for even I have just one way, that is 2, to number them. But I could have also done the other way around, that is, this would have been odd, this could have been odd, and these two even, and this odd. In both the cases, exactly two are even and two are odd, right? And for odd, we have just one. Sorry, for even we have just one case, that is number equals to 2, and for odd we have two cases, 1 or 3. So what I'm basically trying to say is, in this case the number of cases will be 2 into 2 raised to power 2. 2 raised to power 2, because uh, in both the cases there were exactly two numbers which were to be numbered odd, and both of them had two choices, right? So the first vertex had two choices, and the second vertex also had two choices, and third and fourth had one choice only, right? So 2 power 2 for each case, and there were two cases. In the one case in which we colored in which we numbered the vertex 1 by an odd number, and the other case was in which we numbered the vertex 1 with an even number, right? I hope this much is clear. So this point onwards, I'll be discussing the coding part. I'll be discussing how to implement what I am basically trying to explain to you guys. I've already written the code down, I just submitted it. So let's basically look at the code. I have defined the adjacency list and n and m and the other things that I require globally. So for each test case, wt I'm writing because I've already defined wx to be this thing. I'll input the number of vertices, the number of edges. I'll basically clear the adjacency list from the last test case, and then I'll input the edges and the standard stuff, right? Now the main algorithm is in the get function. Now when I reach the get function, I'll initialize my answer to be 1 initially. Then this is the visited array, this is the visited vector, which will tell me if I have visited the current node or not. From I1 to n, I'll iterate. If I have visited the current node, I'll do nothing, I'll just continue to the next node. If not, I'll run a DFS from the ith node. When I'll run the DFS, I'll basically check, before running the DFS I have initialized them to be 0 0 and 1. I'll tell you in some time why. So after having run the DFS, I'll basically check the number of even and number of odd numbered vertices, and this will be if I give the parity even to the ith vertex. As you can see, I have initialized the parity by 0. Even if I can pass here 0, it doesn't really matter. and can will become 0 at the end of the DFS if I am not even able to, partition them into even and odd. If we see in this case, 1, 2, 3, no matter what we do, we cannot satisfy the condition. Let's say we give it even, then we'll have to give both of them the odd number, because this 1 and 3 are also neighbors, and 1 and 2 are also neighbors. Then I'll have to give odd. But giving both of them odd is not allowed, because these two are also connected, right? So if I am to tell you, if there is any if there is any odd cycle in the graph, then the answer is not going to be possible, then the answer is going to be 0, right? So if at any point, if at any connected component I see that I cannot assign the numbers in the desired way, then I'll simply return 0. Else what I'll do is I'll multiply the answer in with the current number of ways, with the number of ways for this particular connected component, right? And basically just take percent mod, and in the final, after having iterated from 1 to 1, I'll return the answer. Now let's see what this DFS function does. In this DFS function, what I have basically done is, uh, if visited of I means I have already visited this current node, I'll basically check if the parity that you know I have currently on this node is equal to the parity that I require, right? I'll explain it to you in a while how this particular thing is checked. Else, if it is not visited, if parity equals 0, I'll just say count of 0 plus plus and visited of I equals to 1, right? Else, count of 1 plus plus and visited of I equals to 2. So I am basically using this visited array to denote the parity that I have given to the current vertex. It is 1 if the parity is even, it is 2 if the parity is odd, right? And after that, I'll basically iterate towards the iterate to through all of its neighbors, and I'll pass the I'll call the DFS function elviz, and I'll just basically split the parity. If the parity is 1, it'll become 0, else if it is 0, it'll become 1. And now let's see how this thing worked. Here I say 1 plus parity is not equal to viz of I can equal to 0. So in this case, I know that if viz of I can be either 1 or 2, right? If viz of I equals to 2, I know that parity should be odd, right? Then p should be odd, which is 1. So in this case, 1 plus 1 equals to 2, right? And if viz of I equals to 1, the parity should be 0, right? Which of I equals to 1, parity equals to 1. And in this case also, 0 plus 1 is equals to 1, right? So for the system to be consistent, I know that 1 plus parity should be equals to viz of I. If it's not the case, it means that the parity is not equal to the desired parity. I'll just simply say can equals to 0, and I'll just return to save some time, right? Yeah, so when I come back here, if can's value is 0, I'll simply return 0. And now I have basically counted the values of count 0 and count 1. In the case if I give the parity 0 to the ith node, right? Now in this case, the number of ways are going to be 2 raised to power count 1, right? Because into 1 raised to power count 0, because for every even number I have just one option, and for every odd numbered node I have two options, that is 1 and 3, right? And for this is there is only one option, which is 2. So the number of ways are going to be 2 raised to power count 1, which is 2 raised to power count 1 in this case. PV mod is the function defined by me. It will basically help us find the power in an efficient manner in logarithmic time, and it will give me the percent mod value. Already you can I hope you would have already studied it. It is fast exponentiation. And but there's another case. If let's say I would have given the parity odd to the the ith node, then the values of count 1 and count 0 would have replaced, right? So in that case, our number of ways would have been 2 raised to power count 0 into 1 raised to power count 1, right? Because count 0 and count 1 have now been replaced, and for every odd value have two options, and similarly for even value I have an option. So I'll add both of these numbers. The number of ways in total are going to be 2 raised to power count 0 plus 2 raised to power count 1, and I'll add them, and then I just multiplied it by answer. As we just discussed, the answer is going to be the multiplication is going to be equal to the product of all the the product of answers for all the connected components, right? And then I'll just return the answer and print it out. I hope the solution is clear. The time complexity, if I talk about, is going to be big of v plus e, right? Because what I am basically doing is I'm just running running a DFS. The time complexity is going to be big O of v plus e for DFS, and it's going to be big O of v log v also for this logarithmic thing, power calculating thing. So it's going to be big O of v plus e plus v log v, right? I hope the time complexity is also clear. So it'll easily run in the time limit, because 3 into 10 raised to power 5, for 3 into 10 raised to power 5, v log v, or say e, is going to work, since we also know that the sum total of these numbers over all test cases is also not going to exceed 3 into 10 raised to power 5. I hope the solution is clear, the time complexity is clear. Thank you. Hi guys, this is Pulkit from Coding Vlogs, and in this video we'll be discussing this problem called Course Schedule 2 from LeetCode. So the problem says that we are given a total of n courses that we have to take, labeled from 0 to n minus 1. Alright, some courses may have prerequisites. For example, to take course you have to take the first you have to first take course 1, which is expressed as pair 0 1. Alright, given the total number of courses and a list of prerequisite pairs, return the ordering of courses you should take to finish all courses. If there are multiple correct orders, you just need to return one of them. If it is impossible to finish all the courses, just return an empty array. Okay. I hope after reading the question, topological sort rings a bell in your minds. What we can basically do to solve this question is that just represent the courses as a graph where each course is a node. And if basically let me explain it by this example. In this example, it says that we have a total number of courses as 4, and let me basically draw the courses as 0 1 2 3 and 4. It says that I need to finish course 0 before 1, which means 0 needs to come before 1, and 0 before 2, 0 before 2, and 3 before 1, sorry, 1 before 3, and 2 before 3. Yeah, so this will be the graph that is basically formed. I'm sorry, this 4 shouldn't be there because number of nodes were 4 and it should have been 0 to 3. Okay, so this will be the graph, and if I basically make a directed graph, what I need is the topological sort, any valid topological sort of this graph. And as we can see, 0 1 2 3 or 0 2 1 3, both of these are valid topological sortings. And if there is no valid topological sorting, we just need to return an empty array. So the question is as simple as it sounds. I hope you would have already learned how to find a topological sort. I have implemented it on my own. I have used a different algorithm actually that you would have seen in the videos. I'll go through the code once. I basically made adjacency list, and in this vector count I'm storing the in degrees of the courses. Okay, and then I visit every prerequisite pair and I add it to the adjacency list, and I just do count of p of 0 plus plus, that is my in degree of p of 0 has been incremented by 1. Now I have this set where I store the int degree and the node number. Like the first of the pair is the int degree and the second of the pair is the node number. Okay, I iterate from 0 to n minus 1, which is the number of courses minus 1, and I basically insert the int degree of I and I into the set. Then I have my final answer. I'll iterate this in this loop while there is at least one node to be added to the answer, and I'll simply get the smallest get the first pair from the set. Now when I'm getting the first pair, it will basically get me one of the nodes which have the minimum in degree, right? Now I'll see if the minimum in degree in the remaining nodes is greater than 0. It means that if p dot first is greater than 0 or is non-zero, this means that none of the the available nodes that I have right now has in degree 0. It means that the topological sort is not possible. The graph must have had a cycle. If you want an example, the if the graph is something like this, that we need to finish 0 before 1, 1 before 2, and 2 before 0, then we would have stuck in you know we would have stuck and we would never be able to satisfy all these conditions, right? So if this is the case, I'll just simply clear the answer because I want my answer to be empty in that case, and I'll just block I'll just break. Else I'll push the second of the current pair into the answer, which is the node number, and then I'll erase the pair from the set. And what I'll basically do is I'll decrease the in degrees of all the nodes that had the current node as their prerequisite, right? I'll just iterate in the adjacency list of p dot second, and if count of I, basically if the in degree of that particular node is greater than 0, then I'll just erase count of I and I from the set. I'll decrement the count by 1, and I'll then again insert it to the set. Although the time complexity of this algorithm is going to be n log n, and as you guys just studied, it can also be done in big of n, and it was just something extra I thought you could get to know about. So this is the solution, as simple as it seems. Just check if the topological sort is possible or not. If it's not, return an empty array. If it is possible, then just return any one of the topological sorts. I hope the solution is clear. It was pretty straightforward. So this was it for this video. Thank you guys. Hi everybody, this is Pulkit Chabra from Coding Blocks, and in this video we'll be discussing this problem called Field of Dreams. It was recently asked in a coding contest, which I do not have access to anymore. So I just took a screenshot and I'll be reading the problem out from there. A field is represented by a 2D grid of size n cross m. Okay, each cell in the grid is either a G cell or a D cell, where G denotes grass and D denotes dirt. Two cells are said to be connected if they share an edge. Okay, the grid is said to be connected if all the G cells can be traversed without passing through a D cell. Okay, otherwise the grid is said to be disconnected. Write a program to find the minimum number of G cells that must be replaced by D cells such that the grid is disconnected. If the grid is initially disconnected, print 0. Okay, I hope the question is pretty clear. You can pause and digest it once if you want to. The input format is that the first line contains n and m, and the next n line contains m spaced characters, G or D. Okay, print the minimum number of G cells that must be replaced by D cells to make the grid disconnected, or if it is initially disconnected, then the answer is going to be 0. And it says that n and m are between 1 and 400, and in the sample test case we can see that the grid here is triple G, G, D, G, and then I can't really read it. I think it's G, G, and G. So in this case, we can see that it's initially connected. We can reach from each from any G cell to any G cell without having to move to a D cell. Now, okay, I'll just replace G and D by 1 and 0 to avoid any miscommunication, because D and G sound a lot like each other. Yeah, so we have to now G is 1 and D is 0. Okay, now I'll talk in zeros and ones. So if we see, if we remove this one cell, we know that the answer can't be 0 because it's initially connected. Let's see if the answer can be 1. It can't be. We can check for every one cell. If we remove this cell, then also we can move from every one cell to every one cell. This, then also we can move this, then also we can move this, then also we can move, and so on. We'll be able to move. But if we remove these two one cells, by removing I mean replacing them by 0, then we'll basically have two connected components. It means that we would have disconnected the ones, right? So in this case the answer is 2. Now this point onwards I'll be discussing the solution. So if you want to think it for yourself, you can pause the video and come back and watch it again to verify that. If not, then you can watch it. An important observation that we need to make here is that the answer, the minimum number of one cells that we have to change with 0 cannot be greater than 2. We can always disconnect the graph, the grid, by replacing the corner ones by zeros. By corner ones, what do I mean? We can have an example. Take any connected component, 0 1 1 0 1. So if we must be having a corner one, right? What we can do is a corner, the ones which are adjacent to that corner one, these are, which is these two in this case, we can make them 0. So we would have isolated this one. We can try and see it for some more example. Let's say our it was like this. In this case also, what we could have done is we could have simply done replace it by 0, so this one would have been isolated. What I'm trying to say is there will always be a corner one which will have either one adjacent cell to it. In this case this one had one adjacent cell to it, or there will be a one which will have two adjacent cells to it. It's not possible for a connected component to have all such ones which have at least three adjacent ones. There will be at least one such cell with only two or one adjacent one wala cell, right? So in that case we can remove the two ones that were adjacent to it, and our answer is always going to be less than or equal to 2. Now we need to check out of the three possible answers, which is 0 1 and 2, that what can be our possible answer. We know that the answer is 0 if the graph of, if the grid of ones is disconnected, right? It's 1. We'll see if it will try and find that if it can be 1 or not. If it's 1, if it can be 1, then the answer will be 1. If not, then we know that the answer is 2 for sure. Now regarding 1, what does it basically mean? If we basically view the grid as a graph in a way that I'm going to tell you. Let's say for example our grid was this 0 1 1 0. Let's say I have 1 2 3 4 5 6 cells in my graph, and in all of those cells the adjacency, the edges are like this, right? Let's say if my grid was a little bigger, yeah, so in this case it would have been this connected with this. So basically what I am saying is I'll make the graph generally as we make in uh, grids by connecting the neighboring cells to the current cell, but we'll assume that the cells which have zero value, basically d value, are not actually a part of graph. So if I consider such graph, if the number of connected components in that graph are basically greater than one, that is, if there are multiple connected components on already, it means that the graph is disconnected. In that case, our answer is going to be 0. But if that's not the case, if there is just one connected component, there can be a case if it's just one cell, it means that we will have to remove that cell, the answer is going to be 1. But if it's not the case, what we'll have to basically see is that is it possible that if we remove exactly one cell from the graph, exactly one cell from the graph, is it possible to make that graph disconnected? If yes, then our answer is 1. If not, we have already established that our answer can not be, we can always get the answer within 2 changes. So in that case, our answer is going to be 2. Now, how to check if by removing a vertex can we basically disconnect the graph? Can we basically increase the number of connected components from 1 to something greater than 1? This is basically just checking if the graph has an articulation point or not. Such nodes, if any such node which basically increases the number of connected components, if deleted, it is called an articulation point or cut point. And for example, this particular node here is an articulation point, because if we delete it and all the edges corresponding to it, obviously, then the number of connected components will increase to 3, and initially they were 2. Also, this one is also an articulation point, because if we delete it, then we would have split this connected component into 2, which means we would have increased the number of connected components, right? So there is already there is already a video that tells you how to basically check if find the articulation points, so you can refer that. I hope you would have already seen that, and I'll not be going into the depth of how to find if there is any articulation point or not. I'll just be reusing the code. I've written down the code. I'll go through the code once, but I'll not be explaining the code where I find the articulation points, where I see if there is an articulation point available or not. So yeah, I'll be going through the rest of the code. Now this find cut points function and the DFS function and all of these 4-5 variables are just to find if there is an articulation point or not. If there is an articulation point, they'll make my global variable 1, one as 1. If not, my global variable one, which I have declared here, will remain 0 only. I'll be going through the rest of the code now, right? N and M, I take them as input. They are the dimensions of the field, and I can also simply change it. It was GGG, GDG, the sample test case basically. Yeah, let's see if it gives 2. Yeah, it gives 2. So I am just taking input the array values. This array is basically a string vector, a string array, string ARR 401 because the maximum size was 400, the maximum basically value of n. Yeah, so I'm taking it as an input. Then I am basically trying to make a graph of just those cells which have a g value, which have a value g on them. The value of current initially is 0, I think 0 or 1, I'm not sure. Yeah, it's 0. It will basically give a code to each such ij which has a green cell, so that I can transform into a normal adjacency list, into a normal graph with integral node values, because in this case there will be a pair of integer to represent the node value, just to make things simpler so that I can reuse this code. I did this. So code of ij will be current plus plus. In this case, code is a map of pair of intent and int, map of pair and intent, pair of intent comma int, right? So I have assigned the codes. Now I'll be adding the edges. To add the edges, what I have basically done is adjacency list has been resized to current, because current is going to be the number of edges that the number of nodes that I'll have in my graph. Then I'll iterate over the whole matrix. If the current value at ij, if the current value is d, if the current character is d, it means that this node is not going to be a part of my graph, so I'll just continue. Else I'll just note down, I'll just store the code of the current node. My represents the code of ij. Then I'll simply iterate on the four neighbors that it has, and I'll check if they are green. All of those which are green, I'll add the edge between the current node and the neighbor node. If I plus 1 is less than n and I plus 1 j value is g, then add it to the adjacency list of my code of I plus 1 j. Similarly, code of I minus 1 j, cos I j minus 1, I j plus 1. So by the end of this loops, I would have gotten my adjacency list of the matrix, adjacency list of the graph. And in this case, I am just updating my n to current, so that I use the n value from now on instead of current. Now n, this point onwards, n will represent the number of nodes that I'll have in my graph, and they'll be numbered from 0 to n minus 1, right? So now it's a general graph problem. We just have to check, I just made some cases down here, you'll be able to understand. If not, and it means that all of the cells had a d value, then 0, then there is no need to delete anything, it's already all dirty. Else if n is 1, it means that there is exactly one g cell, then we would have to basically convert it to d, right? Else if n is 0, I just checked if adj 0 dot size. If adj 0 dot size, it means that they have an edge between those two. Basically, if there are just two nodes 0 and 1, it will either be like this, or it will either be like this. So in the case if adj dot size, it means that adjacency list of 0 has something. It means if it has something, it's obvious that there would have been an edge between 0 and 1. It means that I'll have to convert both of them to d. So answer is 2. Else the answer is 0. I know I have this else if is actually redundant. This would have been covered here only, I think, but just to be sure, I wrote it. Then I'll call the function find cut points. It will basically set the one value to 1 if an articulation point is present in the graph. Otherwise it will be 0 only, right? And also it will get me the number of connected components whenever the DFS value is called. Whenever the DFS function is called, it means a new connected component is basically visited, has started. So I'll just do comp plus plus. The value of comp initially is 0, I think. Yeah, it's 0. So I'll just check if the number of connected components are already greater than 1. It means the array, the graph is already disconnected. In that case, my answer is going to be 0. Else if I'll see 1 equals 1, it means that there is at least one articulation point present in the graph. So I can just delete that node. By deleting that, I mean that I'll convert it from g to d, from 1 to 0. In that case, my answer is going to be 1. Else the answer is always going to be always going to be 2. We just discussed that we'll always be able to find such two nodes which will disconnect the graph, right? I hope the intuition is clear. I hope you are you have seen an example where articulation points actually help, although it's not that a common topic. I have also seen it just a couple of times during participating in the contests, but yeah, it can come handy whenever and wherever required. So this was it for this video, guys. Thank you. See you guys in the next video. Hi everybody, this is Pulkit from Coding Blogs, and in this video we'll be discussing this problem called Lunar New Year and a Wander from codeforces.com. This is the link if you want to open and read it for yourself. This is a graph based problem, and let me read out the problem to you guys. New Year is approaching and Bob wants to wander in a nearby park. The park can be represented as a connected graph with n nodes and n bidirectional edges. Initially, Bob is at the node 1 and he records 1 on his notebook. Okay, so the first node that will be recorded will obviously be 1. He can wander from one node to another through those bidirectional edges, which means it is an undirected graph. Whenever he visits a node not recorded on his notebook, he records it. So basically he records each node the first time he visits that particular node, right? After he visits all nodes at least once, he stops wandering, and thus finally permutation of nodes a1 to an is recorded, right? Wandering is a boring thing, but solving problems is fascinating. So Bob wants to know the lexicographically smallest sequence of nodes he can record while wandering. So we basically need to get the smallest, the lexicographically smallest string, smallest sequence that Bob can record. The definition of being lexicographically smaller is here. You can read it out and then continue watching. The input format is that in the first line will be given two integers n and m, denoting the number of nodes and edges respectively. Uh, the next 10 lines are going to be the description of each edge. This is standard stuff. I hope you guys already know it. Then note that the graph can have multiple edges connecting the two same nodes and self loops, and it is guaranteed that the graph is going to be connected. In case there is some unclarity in the question, you can pause the video and read it again. I'll be discussing the sample test cases from now on. In the first test case, we can see that the graph is going to be 1, 2 and 3. So there is going to be only one possibility to visit the vertices from 1 to 2 and then 3, right? There is no other possibility, so this is going to be the answer. In the next test case, if we see, the graph is going to be 1, 4, 3, 5, 2 and 1 and 5. There is an edge between 1 and 5, right? So from 1 he can either go to 4 or 5, but we'll choose 4, right? Because 4 is smaller than 5, we'll go to 4. And then through 4 he can either go to 5 or 2, right? Sorry, or 3. We'll go to 3 because 3 is smaller than 5. And from 3 he can either go to 2, or he can go back to 4 and then 5, right? So from here also I will choose to go to 3 because 2 will choose to go to 2 because 2 is smaller than 5. Now there's only one node left. We can basically go back to 3 and then 4 then 5. So the sequence is going to be 1 4 3 2 5, 1 4 3 2 5, right? Let's not draw this case. It's going to be a larger one. I hope you get an idea from the two test cases that we discussed. At each point we basically need to choose the smallest node that we can go to and just visit it, right? Because at each point we would want our current value in the sequence to be as minimum as possible, right? To be as small as possible. This is the basic intuition. Will basically run some traversal sort of thing to at each point just visit the smallest node that we can visit, that is visitable, right? And we'll also maintain a visit array which will let us know that which all nodes have been already visited and which all have not been, right? So let's discuss the code. I have already written it down. We'll have n, and the adjacency list size will be n plus 1, and then we'll have m edges, wm, because I've already defined wx to be this, right? So we'll take the edges as the input. Then we have our answer vector, and this set can denotes basically stores the set of nodes that are to be visited, that can be visited from the current scenario, right? For example, in this second case we saw that our graph was 1 5 and 4 and 3 and 2, right? 1 5 3 2 4 5 3 4 and 1 4. So 4 5 was also there. 1 2 3 4 5, 1 2 3 4 5, right? So while I was at 1, in my can set I'll have 5 and 4 because I can visit just 5 and 4 from this. And now I'll choose to go to 4. Now after having gone to 4, my can set will contain 5 and 3 because I can visit 5 and 3 in my next move. Now I'll go to 3 because my out of 3 and 5, 3 is the smaller one. Now when I am at 3, my can array will have 5 and 2, because I can go to 2 from 3, and but I can go to 5 from one of the nodes that I have already visited, because I can go back to any node that I have visited, and from there I can explore any of the neighbors of those particular nodes that I have already visited. Now out of 5 and 2, 2 is the smaller node, then I'll visit 2. And now at this point onwards, the can will only contain 5, so I'll just go to 5 in this manner, right? Doesn't really matter that in what manner I go to 5, because all the nodes in the path would have already been visited, so it doesn't make any difference, right? So let's see how to implement. This will contain the set of nodes that I can visit in my next move, and this will contain that which all nodes that have I already visited and which are to be visited yet. I initialize it by 0 because all of them are to be visited yet. The first node that I'm going to visit is going to be 1. I'll just push back 1 to my answer, and mark visited of 1 as 1. Now I'll run this loop while my answer size is less than n, because I have to visit all of the n nodes. Now I is going to be answer dot back. It means that I is going to be the last node that I visited, the node I just visited in the current step. What I'll basically do is I'll iterate towards the neighbors of the ith node, the last node that I just visited, and if the neighbor has not been visited yet, I'll just simply insert that particular neighbor into can, right? Because now I can visit that node. Then out of the nodes that I can visit right now, I'll get the smallest node. Can dot begin will give me the iterator to the smallest node. So I'll just push back to my answer the smallest node's value. I'll just mark the smallest node's value to be visited, just visited of star it equals to 1, and then I'll basically delete that particular iterator from can, because we can no longer visit it for the first time, because we have already visited it once, right? Now as soon as we come out of this loop, we can just go on and print the answer value. I hope the solution is clear. This is it. The time complexity of this solution, if we analyze, is going to be bigger of e, because we have we would have basically iterated all of the edges, plus v log v, because this loop is going to run n times, right? And each time I'll take log time to basically erase and erase the it value from the can array. So my time complexity is going to be big of v log v plus e, right? Yeah, so it is going to be within time limit, and the space complexity that I'm going to take is going to be big O of n, right? Because I am not just making n nodes. I hope the solution is clear. Thank you. Hi everybody, this is Pulkit from Coding Blocks, and in this video we'll be discussing this problem called secret passwords from codeforces.com. This is the link of the problem if you want to open it out and read the problem for yourself. I'll anyway be reading it out. There's an hacker who wants to get the admin's password at AdForce's testing system to get problems for the next contest. Okay, this is a story. To achieve that, he sneaked into the office and stole a piece of paper with a list of n passwords, that is strings consisting of small Latin letters. Okay, then he went home and started preparing to hack the website. He found that the system only contains passwords from the stolen list. Okay, and the system determines the equivalence of passwords a and b as follows. Okay, two passwords a and b are equivalent if there is a letter that exists in both of these strings, both of these passwords, or if there is another password c from the list which is equivalent to both a and b. Okay, so if a password is set in the system and an equivalent one is applied to the system, then the user is accessed into the system. Okay, for example, if the list contains the passwords these, then A, B and AB are equivalent to each other because AB and A have A in common, AB and B have B in common, and A and B are equivalent because they are both equivalent to AB, right? But the password D is not equivalent to any other password from the list. In other words, if admin's password is B, then you can access the system by using any of these three passwords. But if this password is, say for example, D, then you can only access the system by using this password D only, right? So only one password from the list is the admin's password, and we have to help hacker to find the minimal number of passwords that he has to try required to guaranteed success in the system to the system. Keep in mind that the hacker does not know the password, and we have to basically consider the worst case scenario, right? So in the input we are given an integer n, the number of passwords, and the next n lines contains passwords from the list, non-empty strings si, which with length at most 50 letters. Okay, some passwords may be equal. Okay, it is guaranteed that the total length of the passwords does not exceed 10 to the power 6 characters, and all of them are having only lowercase letters. Okay, we have to print a single line that is the number of minimal passwords that are required for guaranteed access. All right, so you can pause the video, you can think it around, think something to do with graphs. I'll be discussing the sample and the solution from now on. Let's see, for the first test case, we know that AB and AB are equivalent to each other, and D is another password which is not equivalent to any of these, as we just saw in the sample test case only, the sample example only, sorry. We'll just need two accesses, two tries. In the first try we can enter D, in the second try we can enter any of these passwords, and we'll be logged into the system. And parallelly, in this case, we'll see that all of the passwords are equivalent to each other, and AB and BC are equivalent because B is common between them. BC and ABC is equivalent because B and C are common, and parallelly AB and ABC are common because AB and ABC are equivalent because AB is the common are the common letters in both of these passwords. So we can enter any of these, they are anyway equivalent to each other. We would have entered the system in one go only. In this case there is only one password, so the answer is obviously going to be 1, right? If we think in a more general way, to basically get the crux out of these two lines, the crux out of these two lines, the basically equivalence of two different passwords, what I'm trying to basically tell you here is that if I consider the different passwords, consider the different indices from 1 to n, the different si values, the different I values, to be nodes of a graph, with n nodes. uh, and if I add a bidirectional edge, that means I'll be considering an undirected graph. Yeah, coming back, if I add a bidirectional edge to each pair of passwords, to each pair of indices, if those two particular passwords have at least one letter in common, then two passwords will be equivalent if they lie in the same connected component. How? Let's say we have passwords ABC. ABC are not the actual passwords. I'm just labeling the passwords to be ABC. Let's say P1, P2, P3. Okay, P1, P2, P3, and let's say one more P4 also. Yeah, P4 also. And let's say P1, P2, and P4 have something in common. P1 and P3 have something in common, and let's say P4 and P1 also have something in common. So what I'm trying to say is, here P3 and P4 are also going to be equivalent because P4 is equivalent to P1 and P1 is equivalent to P4, and P2 and P3 are also going to be equivalent because P2 is equivalent with P4, which means it is also equivalent with P1, which means it is also equivalent with P3, right? So through edges, we can come up with a path from if in this graph we can come up with a path from one password to another, it means it is equivalent, right? So if we can come up with a path, it means that they both lie in the same connected component. So in this case, the answer is going to be number of connected components, right? Because for each connected component, I can pick up any of the passwords and enter it, and I'll basically be logged into the system if my actual password lied in that particular connected component only. If not, I can try another connected component. So my target is to count the number of connected components. But here's some trick. The number of passwords are too high. The number of passwords are 2 into 10 raised to power 5. So I can't basically, iterate over every pair and add the edge if there is something common. No, we can't do that, because in that case the time complexity will be minimum big O of n square, right? But to get rid of this problem, what we can basically do is, we know that if 1, 2, 3, 4 all have a common letter, let's say they all consist the letter A, instead of adding the edges between every pair, we can just add only the required the minimum required edges. Like we could have also made the graph like 1, 2, 3 and 4. This and this graph doesn't really make any difference, because in this case also all of them are in the same connected component, and in this case also they are all in the same connected component, because we just want to ensure that all of the equivalent passwords in the same connected are in the same connected component. We don't really want to just add redundant edges. So we'll see how to do that. We'll see how to limit the time complexity, so that our solution passes within the time limit, and we'll see how to avoid adding redundant edges, right? Let's see. This is the coding part. I'll be discussing the code from now on. First of all, I'll input the number of passwords, and then what I'm going to do is, I'll iterate from 1 to n, and then I'll iterate that particular string. When I'm iterating a particular string, I'll be adding to for every possible character, for character A, B and Z, I'll be maintaining 26 vectors, and in each vector I'll be storing the indices of those strings in which we incur that character, in which we have that character at least once, or it doesn't matter, we can have the indices multiple times as well. So to do that, what I'll be doing is, I had made an array of size 26, vector int idv of size 26, and now when I'm iterating the string, I'll just add I to idv of ch minus a, right? So for A, my index is going to be 0, for B it's going to be 1, and for so on for Z it's going to be 25, right? So after that I'll just resize my adjacency list to n. I have declared it globally over here. Now what I'll do is I'll iterate over each character. Now when I'm iterating on the ith character, I'm basically adding the edges corresponding to that particular character. Now let's say the vertices that the indices that contain the ith character, let's say they are id1, id2 and let's say up to idx, right? Now instead of adding the edges between each possible pair, I am just adding the edges in chain wise, like id between id1 and id2, id2 and id3 and idx minus 1 to idx. I'm just adding the edges in such a way, because that will ensure that we have basically put them all in the same connected component, right? So in this loop, what I'm basically doing is I'll iterate from j equals to 0 to its size minus 2, like up till j plus 1 is less than idbi dot size plus j. It's a common mistake. Sometimes I also make this mistake. Instead of plus j, I sometimes do plus I. You must take care of that. Then I'm adding to idvij the idvij plus 1, that is the two consecutive indices, and similarly I am adding it in the reverse way, right? So from after this point my graph is ready, right? Now I'll initialize my answer with 0. Now I have initialized the visited array with n and 0. Now this line onwards is just standard DFS. I'll just go through it once if you really want to. So I'll iterate from 0 to n minus 1 because that's the range of my indices. If the ith node has already been visited, then continue. Else the ith node is to be visited for the first time, so this is going to make a new connected component, and by calling DFS I'll ensure that I visit all of the nodes that are in the connected component of I, so that I do not visit them again. In the end I'll print the answer. So let's see what this DFS function does. If the ith node has already been visited, just basically return. Else if not, then I'll mark it as visited, and then I'll basically iterate call the same function to its neighbors for NB belonging to ADJ of I hope, I think you would have already learned how to call DFS, and in the end my answer will be equal to the number of connected components. I just simply print the answer. So in this case my time complexity, if we analyze, in this loop it's just the sum of characters, right? And in this case it's simply the number of different edges, right? And in this case also it's big of v plus e. So in any case my time complexity is not going to exceed 10 raised to power 6, right? Because this is the maximum number of times I'll iterate, and number of edges are also not going to exceed this you know uh, loop, the number of iterations of this loop, right? So in layman terms my complexity is going to be big of v plus e, where v equals n and e will basically depend on the input, but it is not going to be more than 26 into v 25 into v 26 into v minus 1 actually. Let's say each of the node, so basically each of the vertex have uh, each of the letter, then the number of edges for each character are going to be v minus 1, and the total number of letters are 26, so number of edges are going to be maximum 26 of v minus 1. So we can say that our time complexity is going to be big of v only, right? I hope the solution is clear. Thank you.
Hi everybody, this is Pulkit from Coding Blocks, and in this video we'll be discussing this problem called snakes and transition from capitalism to socialism, or simply let's say SN social. As you can see, this is a problem from codechef.com, and let's read the problem. After a long duration of the painful, torturous, and blah blah blah, the houses in the snake land are arranged in a rectangular fashion of dimension n cross m. So there's an n cross m grid. The wealth of the snake in the house ij is given by a ij rupees. So basically there is a value associated with each cell ij. A bill has been passed to make a smooth transition from capitalism to socialism. At the end of each hour, the wealth of a snake will grow and will become equal to the highest wealth that its neighbor had at the start of the hour. Okay, that is, consider the maximum wealth among its neighbor at the start of the hour, and this snake's wealth will become equal to that at the end of the hour. All right, note that this increase will happen simultaneously for each snake. Two houses are said to be neighbors if they share a side or corner with each other. Find out the minimum number of hours required for this transition. Okay, let's first read the input and output format, and then I'll basically start discussing the solution and analyzing the question. We first get the number of test cases, then n and m, which is the number of rows and columns, and then we basically get n into m numbers, denoting the the value associated, or the rupees that the snake at the house ij has. For output, we have to simply output the minimum number of hours required for the transition for each particular test case, and the number of test case will be from 1 to 4, and m can be up to 500 and aij values can be up to 10 raised to power 6. Okay, so the basic thing that is happening here is that if we see that for each cell, first of all, these 8 cells are going to be its neighboring cells. Yeah, for this cell, the rest of these are the neighboring cells for this one, right? So what is basically happening is that let's say these all had some values x y z and so on at the start of r1. So basically at the end of r1, by first r's end, this value will be maximum of all these. One second, this will become equal to that value. Okay. Okay, so the value will become the maximum of all these values for this particular snake and would remain the same if the value of this particular cell was already greater than or equal to all the neighbors values, right? So we have to basically find the minimum number of hours after which the values will stop changing, the transition will stop, and the array will become constant. So if we try to observe, this will happen only when all of the cells will have equal values. It's only when there will be no transition, and that equal value is going to be the maximum of the array, right? Like if we consider the second test case, the second test case here is this one, 2 2, and the values are 1 1 1 and 2. It will take 1 hour because this 2 is a neighbor for each of these cells, and by the end of the first hour the values are going to be 2 2. Let's see, yeah, the answer is 1 only. And for the third test case, if we see, this will be equal to 2 in the first hour because of this 2. Let me draw it in a more spacious manner. 1 1 1 2 1 1 2 2. Yeah, this one will turn to 2 after first hour. I am making the transition for the first hour. This one will also turn to 2 for after the first hour due to these both 2's. This one will also turn to 2 due to this one will not turn to 2 because all of its neighbors were 1 by the start of the first hour. This will turn 2 due to this one. This will turn to 2 due to this one, and this will also turn to 2 due to this 2. And now by the end of the first hour, or let's say the start of second hour, all these are 2 but this is 1. So by the end of second hour this will also turn to 2 due to all of these, let's say. And after 2 hours there will be no more transitions because all of the values have already been changed to the maximum value, right? So as we can see, the answer is 2 for this test case, and the answer is 0 for the first test case because all of the values are already equal. So if we make an observation, the cells which have a value equal to the maximum value initially, this and this cell for the first case, let me mark it, this yeah, and all these only, these are these have something special because they are the maximum before the start of the whole process, right? And after each hour, as the hours pass, after the hth hour, let's say let's look at it in a different way. What I'm basically trying to say is, for a cell ij to become equal to the maximum, it will take that many number of hours, that is the minimum distance of that cell from some 2, right? Let me explain it to you by an example. Let's say these two cells were having a value 2 and all of the other cells are having a value 1. Now what I'm basically trying to say is, uh, this cell, for this cell, if we see the distance for this cell from this cell is 2 1 2, right? And the distance of this cell from this cell is also 2 1 2. So it will become the minimum distance I am talking about. So it will become 2 after 2 hours. If we see for this cell has a distance of 1 2 and 3 from this 2, and a distance of 1 and 2 from this 2. So min of 3 comma 2 is 2. So this will also become basically equal to 2 after exactly 2 hours. And if we see for this one, the distance is 1, and from this 2 the distance is 1 2 3, and min of 1 and 3 is 1, so it will become 2 after 1 hour. Had there been more 2s also, we would simply have taken the minimum distance of a particular cell ij, or any other ij you can take example, from all of these cells, and the minimum distance would have been the number of hours that would that the cell would take to basically become the maximum, to basically take the maximum value, right? So what we are basically looking for is, for every cell ij, we'll find the shortest distance. We want the shortest distance of this cell out of all of those cells we have, the which have the maximum value. And after having done this this process for every cell, we basically want the maximum value, because that will be the number of hours that will require for sure, to make sure that every cell has attained the maximum value, right? So to do this, one of the possible ways that I can think of right now is, go to every cell, apply bfs from that cell, check the shortest distance from the special cells, and just move on, and then take the maximum for each cell, right? Now for this particular case, our time complexity is going to be number of cells into the time required for bfs, and the time required for bf is also going to be n, which is the number of cells, and the number of cells are n into m. So our bf, so for time complexity will be n square m square, right? But this clearly will not be in our time limit, because what we are looking at is 500 power 4. So we are looking at 625 followed by 8 zeros. 1 2 3 4, okay, 625 into 10 raised to power 8, and it is not going to pass in time, right? So we want to look, we want to find a more efficient algorithm, and in this case we'll be using something called multi-source bfs. Multi-source bfs will basically be useful in applying bfs, but not from one source. We'll be applying it from multiple sources, and the multiple sources that I'm talking about will be the special cells that I just told you about. The special cells, meaning the cells which have the maximum ai value, aij value, initially, right? So let's see how this multi-source bfs thing works and how it computes the answer. Let me discuss the code now. Sure. So I've copied down the test case also. Let me go through the code for you. So in the main function, firstly I'm taking the number of test cases and running the loop test cases number of times, because the wx is defined as int x in x while x minus minus. All right, so I'll take the n and m as input, which is the number of rows and columns. Then I'll initialize my mx by 0, because the cells are from 1 to 10 raised to power 6, cell values are from 1 to 10 raised to power 6, so 0 will do my work. Then I'll iterate, and seeing the error ij values, actually I have declared n m and error ij has the array has global, so it's not going to be a problem. Then I'm simply taking mx equals to max of aij. Then I'll add the edges of the matrix to consider it as a graph. So to add the edges, I am basically iterating on each cell, and I am first clearing this adjacency list aij's value. You can see that I have made an adjacency list of 501 cross 501, where each cell ij is a node in itself, and the vector of pai will store the nodes that are adjacent to this particular node, right? So I'll clear it because there are multiple test cases. I would have stored the adjacency list corresponding to the last test case. I don't want it to mingle with the current test case, so I'll clear it. And then these are the 8 possible scenarios for the neighboring cells, that is -1 -1, that is I minus 1 j minus 1 -1 0, which is I minus 1 j, and so on. You can pause and look at. Then I'll iterate for all of the neighboring cells, that is id equals to 0 and less than 8. I'll check if that particular cell, which is I plus di of id and j plus di id, dj of id, lies in the range. The check function simply checks if I is greater than equal to 1 and j is greater than equal to 1, and both of them should be basically less than or equals to n and m respectively, right? If that's the case, I'll simply add it to the adjacency list of ij, right? The number of the edges, the required edges have been added now. Then I'll clear the special array, the special vector, because it would have some values from the last test case, and I don't want them to basically uh, come in the way. So after having cleared them, I'll iterate over the whole matrix, and all of the values, all of the ij values which have their ARR value as the maximum, I'll add those values in the special vector, right? And then I'll basically call my get answer function and print \n. Now let's see what this get answer function does. This get answer function is simply a multi-source BFS function. It will contain a queue of pair intent where pair intent represents my node, and I'll have a 2D vector of called visited, which will tell me if the current node has been visited or not. It is somewhat similar to the BFS we generally see in the 1D graph, in which the node is represented by an integer, but the only difference is in this case the node is represented by a pair of integers. So I'll have to have a 2D matrix for visited instead of a 1D one. So it is of n plus 1 cross n plus 1, and all of the values are initialized by 0. And I have a d array, the distance array, which is n plus 1 cross n plus 1. Okay. Then I'll iterate over each cell in the special vector, and I'll basically mark its distance to be 0 and mark it visited, and I'll push it to the queue. Unlike the single source, the normal BFS, we just does it for we just do these things for the source node, but in this case all of these nodes are going to be the source nodes, so we'll do it for every node, right? And then I'll initialize my answer by 0, and while the queue is not empty, I'll simply apply the normal BFS that you would have already studied. I'll pop out the front, I'll move to its adjacency list, and if the neighbor has not been visited, I'll mark it as visited. I'll push it to the queue. I'll update its distance. Now the additional thing I want to do is I want to take the maximum of the distance with answer, and I'll simply return the answer. Now by the end, my answer would have stored the value of the longest distance a cell has, and a distance of a cell is represented, a distance of a cell, and by a distance of a cell I mean the shortest distance from any of the special nodes, right? So these will be the number of hours that I would require to basically completely transit the array, right? Transit the matrix, and I'll just simply print it. I hope the intuition behind the solution is clear. I hope the solution itself is clear. I hope the code is clear. So that was it for this video, guys. Thank you very much.
Hi everybody, this is Pulkit from Coding Blogs, and in this video we'll be discussing this problem called tree queries. This is from Codeforces, as you can see. Let us read the problem out. The problem says that we are given a rooted tree consisting of n vertices numbered from 1 to n, and the root is a vertex number 1. Okay, a tree is connected. A tree is a connected undirected graph with n minus 1 edges. I hope you all already know that. We are given m queries. The ith query consists of the set of ki distinct vertices v1, vi1, vi2, and up to vi ki. All right. Our task is to say if there is some path from the root to some vertex u such that each of the given k vertices in this particular query is either belonging to this path or has a distance 1 to some vertex of this path. So basically, to sum it up, we want to get we want to know if there exists some path from the root to some node, that either each of these vertices lie themselves on the path, or some other node that is adjacent to the node in the list lies on the path, right? So the input format is n and m, which is the number of vertices and the number of queries, and then the next n minus 1 lines contain the description of the edges. The ith edge is denoted by two integers ui and vi. This is just standard stuff. You can read it out if you want to. Okay, and then the next m and m lines consist the queries. The ith line consists an integer ki, which is the number of vertices. It can be from 1 to n, and the number of vertices in the current. Okay, then k integers follow v1 to vk, and the vij represents the jth vertex of the ith query. Okay, it is guaranteed that all vertices in a single query are distinct, and it is also guaranteed that the total number of vertices in the queries do not exceed 2 into 10 raised to power 5. Okay, for each query we have to print yes if there is a path, or no if there isn't a path. Okay, so if we analyze this problem, okay, from this point onwards I'll be discussing the solution. If you want to think it for yourself, you may pause the video. It is a good time to do that. All right, so if we try to come up with at least one solution, a possible solution can be just run a dfs from the tree for each query. For each path, for each path that you get, you can keep storing the path till the current node. Let's say if I am at 6, I can store the current path, which is 1, 2 and 6, and I can basically check for each path if this can be a possible path or not. And the time complexity for running the DFS is going to be big of n, right? If we run a DFS every time, the time complexity is going to be big of n, and there will be some additional time also to basically check if the current path is a possible path or not. So the time complexity for each query is not going to be less than big of n in any case, and that's not gonna work because our number of queries are up to 2 into 10 raised to power 5, and n is also up to 2 into 10 raised to power 5. So big of n into m is clearly not the solution that we are looking for. We are looking for something that answers our queries in either big of log n or big of 1, right? And we can obviously do some pre-processing to get the answers in a lesser time. So what do we basically do? Let's analyze. Let's try to find what is the path that we are trying to find is going to look like, right? So if we take an example query, the queries start from here, I think. Yeah, the first query is 3, 8, 9, 10. Okay, 3, 8, 9, 10. The answer for this is yes, and we can see if we simply let the path be 1 to 10, 1, 3, 7, 9, 10, then each of the nodes are lying on the path except the node 8, but 8 has an adjacent a neighbor, that is 7, that lies on the path, right? Let's see some test case, some query for which the answer is no. 6, 10, the answer is no for 6, 10. 6 is there, 10 is there. We can clearly see there is no path in which either the vertices themselves or any vertex adjacent to these vertices lie on the path. And similarly for 5, for 7, 5, okay, 5, 1 second, yeah, 5, 4 and 7. For these also I don't think there lies a
path, it's clear that we can't satisfy the constraints. And as we just saw for 3 7 8 9, the path was 1 3 7 9, or 10 also we can include. Both of these paths satisfies the constraints. Even 137 satisfies the constraints. If we see this path, then 3 9 and 10 lie on the path itself, and 8 has a neighbor lying on the path, right? So the constraints are satisfied. Now let's try to analyze what type of path are we looking for. If we see, for some vertex v in the list of the ith query, we want either one of its neighbors or the v itself to lie on the path, right? So either v lies on the path or parent of v lies on the path, because parent of v is one of the neighbors of v, or some child of v lies on the path, right? Now in the cases, if we see if v lies on the path, it is pretty clear that p of v, that is the parent of v, is also be lying will also be lying on the path, right? Because the path will be from root to some vertex, and if we are going through the vertex v itself, then we would have already passed through the parent of v also, right? Similarly, if a child of v lies on the path, it is pretty clear then v is also going to lie in the path, and if v is going to lie on the path, then parent of v is also going to lie on the path. So all in all the three cases, we can conclude that no matter what, the parent of v should definitely lie on the path. And if parent of v does not lie on the path, then we can be sure that neither v nor any child of v lies on the path. So it is a bidirectional. If the path is what do we say, the path is satisfactory, let's say satisfactory. One sec. The path is satisfactory for v if and only if parent of v lies on the path, lies on it, okay, right? And this is the case when the vertex v is not the root node. Obviously if v is not root node, p of v does not make any sense. If we are talking about root node, we can be sure that it will lie on the path, because every path that will start from the root will consist of itself. This is for all the other nodes, right? So it will be, the path is satisfactory for v if and only if p of v lies on it. So basically we are looking for some path such that the parent of every node that is present in the given list of the current query lies on the path, right? If we can find such path, then the answer is going to be yes, else it's going to be no. So we'll see how to how we can find find out if such path exists or not. Let's get to the coding part. I have already written a code here, and we'll see how this can be done in time limit with the code, right? We'll be first taking in input the NNM, which is the number of vertices and the queries. Then we'll be taking n-1 edges. Then I'm calling DFS. While calling DFS, what I'm basically doing is I'm storing the level of each node, and then I'm storing the parent of each node, and I'm storing the end time of each node. That is the first time that I visit this particular node during the DFS. And this is the out time basically represents that I have covered all of the subtree of this particular node, and now I am basically going to the other tree. If I tell you in this example, the end time for 1 is going to be 0, and for in time of 2 is going to be 1. Then for this one, in time is going to be 2. Let me write it down so that you don't confuse it. N equals to 0, n equals to 1, n equals to 2. Since there is nothing in it subtree, n equals to out equals to 3 for us. And then basically we go to this n equals to 4, out equals to 5, and for this out equals to 6. So basically in and out of every node in a subtree of a node is basically lying between the in and out of that particular node, right? If we see 2 and 3 both lie between 1 and 6, and 4 and 5 also both lie between 1 and 6. So using in and out times I can basically come to know if a node lies in the subtree of a particular node or not. That means we can know if some node is an ancestor of a particular node or not, right? uh, by ancestor I mean, if it comes on the path, when I say 7 is ancestor of 10, it means that if I trace the path from 1 to 10, 7 is gonna come in between, right? It is equivalent to say to saying that 10 basically lies in the subtree of 7, right? I hope it is clear. Now I'll be using this information that I just told you while checking if such path exists or not, right? So I am then proceeding on to my uh, the queries, and while getting the queries I am first basically uh, having two variables, farth and dp. I think I'm not using farth. Yeah, I'm using farth. Farthest, basically this is farthest, and this is some variable dp which I have initialized with -1. Let's see. Then I'm taking input the number of vertices, then I am taking input each vertex. Now I'm saying that if L of L of v of I is greater than dp. Dp basically means depth, right? I am basically going to get the vertex which is the deepest. If L of v of I is greater than depth, then depth is going to be equal to L of v of I, and the farthest node is equals to v of I. I'm storing the farthest node and the depth of that farthest node, right? And I am basically replacing vi if with p of v of I for every node I, right? Now I'll initially initialize the answer with yes, and then I'll see if there is something wrong with the list, and if it's the case I'll simply change the answer to no and simply break. Now let's see how are we checking that if something's wrong, right? What I am basically trying to say here is what I'm basically trying to claim here is that if we want each if we want the parent of each node, if we see that test case where we had 3 8 9 10, 3 8 9 10 were my nodes, right? So I wanted 1, that is the parent of 3, 7, that is the parent of 8, and 7 again the parent of 9, and 9 the parent of 10. I want all these nodes to be the path to be the part of my path. So if I consider the lowest node, the deepest node, it is going to be 9 in my case, right? So basically what I'm trying to say is I'll simply check if all of the parents lie on the path from 1 to the deepest node, which is 10. Because if I want the parent of the deepest node to be present in the path, I can simply trace down the path from this particular 1 to this particular deepest node, and I would want that all of the other parents should lie on this path. If they do not, it means my answer is no, because there is no other path which will contain all of those other nodes, and if this path doesn't, right? Now what I'm basically checking here is that if all of the nodes are present in the path from 1 to the deepest node or not. If not, then my answer is simply no. Now to check it, what I'm basically doing is if not v of I, it means if v of I equal 0, we know that we have set the parent of 1 to be 0. When I'm setting the parent of 1, it is going to be 0. So for 1 I simply need to ignore, but else if it's not the case, for the parent for the node v of I to be present on the path from 1 to fath, the farthest node, it basically should be the ancestor of the node fath, right? It means that the node FARTH should be in subtree of VI, right? And if that's the case, its in and out times should be, lying in the range of in and out times of that particular node, right? So if in of Vi is greater than in of fath, it means if the Vi started after, the farthest node, or it ended before the starting of the farthest node, it means that the answer is no. If we see, let's say the time range for Vi is this, and the time range of then the time range of path should be something like this, which is inside the, Vi. Now to check if that's not the case, either the case is going to be like Vi first and then the range of FARTH, or FAD first then the range of, V of I. And these two cases check if this is the case or this is the case. If this is the case, then out of Vi is less than V out in of fath, right? This one. And if this is the case, then and if this is the case, then in of Vi is greater than in of fath, right? It means that we entered fath before we entered Vi, right? Then otherwise this is the case, and this case will also be, covered in this particular case only. Now if this is the case, then we simply know that the farthest node is not in the subtree of Vi, and if we find any such node from 0 to k minus 1, then our answer is going to be no, and we'll simply break, right? And then we'll simply print the answer. I hope the basic condition is clear. I hope the code is clear. So that's it for this video, guys. Thank you.
Hey everybody, this is Pulkit Chabra from Coding Blocks. In this video, we'll be discussing this problem called path queries. This is a problem from codeforces.com. So the problem says that we are given a weighted tree consisting of n vertices. Recall that a tree is a connected graph without cycles. Vertices ui and vi are connected by an edge with weight wi. Okay. We are given m queries. The ith query is given as an integer qi. In this query, we need to find the number of pairs of vertices uv such that the maximum weight on an edge on a simple path between u and v does not exceed qi. Okay, so to make it even more, to give it some more clarity, I'll just repeat it again. We are given a tree. A tree means that it will have n minus 1 edges. We are given a weighted tree. It means there will be a weight associated with each edge. And we are given some queries. We are given m queries. In ith query, we'll be given a number qi. We want to find the number of vertices, the number of pairs of vertices uv, such that on the path between uv, to recall, we know that there will be exactly one path between u and v. Because this is a tree, there will be just one path from u and v. On that particular path, if there is not any edge that whose weight exceeds qi, will count that particular pair. So in this query, we need to calculate the number of pairs of vertices uv. U less than v, it means that uv and vu will not be counted twice, they'll be counted just once, such that the maximum weight on an edge on a simple path between u and v does not exceed qi. If there is something still unclear, you can pause the video and read it. Let's see the constraints and the input output format. The input line, for the input, the first line contains two integers n and m, basically the number of vertices and the number of queries. N and m can be up to 200,000, and the next n minus 1 lines describe the edges of the tree. The ith edge consists of three integers ui, vi, and wi. Ui and vi will be basically the nodes that this particular edge connects, and wi is going to be the weight of this edge. It is given that ui is not going to be equal to wi. That's, I think,
understood, since it's a tree, there are not going to be any loops. The weight of the edge, yeah, and UA and VI can be up to from 1 to n, and WI can be up to 200,000 again. It is guaranteed that the given edges form a tree. Yeah, so we have n minus 1 edges. It is guaranteed that they form a tree. It means that the graph is connected. It is connected. Uh, the last line of the input contains m integers q1 to qm, and each qi can be up to 2 into 10 raised to power 5. Okay, where qi is the maximum weight of an edge in the ith query, right? So we have to print m integers, the answers to the queries. The ith value should be equal to the number of pairs uv, u less than v, such that the maximum weight on an edge on a simple path between u and v does not exceed qi, right? Queries are numbered from 1 to m in the order of the input. Okay, I don't know how does this uh, add value to the question. Anyway, shall we just start by taking the first input as an example and seeing the answers, right? Okay, let's take the third one as example because it's a smaller one. We have 3 nodes, and so we have 2 edges. 1 to 2 is an edge with weight 1, 1, and 2 to 3 is an edge with a weight 2, right? And we have 3 queries which are 1, 3, and 2. So if we do not want the edge weight to exceed 1, so we have just this one possibility, that is 1 comma 2. If we include 3, then we'll have this edge with weight 2, which is not something that we want. For qi equals to 3, we know that all of the edges are basically having a weight less than 3, so we can just simply say take any path, it's fine. So 3c2 means 3 pairs of vertices, so 3. For the case 2 as well, we know that each of the uh, each of the edge length is less than or equal to 2, so we can simply say 3c2, right? So that's it for the example part. I'll be discussing the solution now. It's a pretty solution. You need to be alert while you know listening to it, so that you can understand it properly. If you want to give it a try for yourself, it will be a good time to pause the video and do that. So to discuss the solution, I'll just be drawing the tree for this graph. I'll just open OneNote and draw it and come back and continue the video. Yeah, so I have drawn the tree. I have written down the queries for that particular test case. Let's see what our answer can be for each particular test case. Now for 5, we know that all the nodes are less than or equal to, all the edges have their weight less than or equal to 5, so we can choose anything. So our answer is going to be NC2, that is 7C2, which means 7 into 6 by 2, which is 21, right? For 2, what I plan to do is, I can't really visit any edge that has a weight greater than 2. So why don't we just forget the edges which have a weight greater than 2? So we forget these 2 edges. Now what we can do here is, we can see each different connected component that we had after deleting these edges. We have this connected component, we have this one, and we had this one. Now in each connected component we can visit any pair of nodes, so and that pair will be a valid one. So in this case 2c1, that is 2, plus sorry, not 2c1, 2c2, which is 1, plus 4c2, which is 6, plus 1c2, which is 0. So 6 in this case and 1 in this case. The answer should be 7 in this case. Now for 3, I'll remove, okay, I'll just have to draw it again, this edge, and yeah, done. So for in case of 3, I'll have to remove the nodes with edges with weight greater than 3, so just remove this. In this case, this will be a different connected component which will contain no pair, and all of the others will form a different connected component. So our answer is going to be 62, which is 15. For 1, no, for 4, we need to delete all the you know but edges which have a weight greater than 4. There is none of the edges have a great weight greater than 4, so in this case also our answer is going to be 21. For 1, we want to delete all the nodes which have a weight greater than 1. Delete this, and this. We are left with only these two nodes. Let's see, only these two nodes. So in this case our answer is going to be 3c2, because all of the other connected components will just have one node, so no pair. So our answer is going to be 3c2 in this case, which is 3. Let's match the answer. Our answer is according to me, our answer according to us should be 21, 7, 15, 21, 3. 21, 7, 15, 21, 3. Yeah, right. So basically what we want is, for each query we want to consider only those nodes, sorry, only those wedges, only those edges which have a weight, which have a wi value less than or equal to qi value. Consider only those edges, and if we consider only those edges to be the edges in the tree, then what I want is, let's say I have some connected component, let's say I have g connected components. What I want is, I want s1c2 plus s2c2 and up to SGC2. That's what I want, right? That is my that's the answer that I'm looking for. And to do that, what I can think of possibly is that, what if we basically come up with something in which we answer the queries in increasing order of their values. Let's say we sort them according to their values. We sort them, in this case the values will be sorted, the sorted values will be 1 2 3 4 5, and while we are at this query, we look for the answer if the okay, once again, we don't really need to sort the queries. What we can do is, we can sort the edges. If we sort the edges were these 1 3 2 1 2 4. If we sort the edges, and while inserting the edges in the graph, in the tree, after we insert one more edge, can we basically get the answer at this point in maybe log n time? Because if we take big of n time, then the total time that we would have taken will be big O of n square, because we'll be inserting n minus 1 edges, and for each edge, if we take big O of n time, it will be 10 square. So one possible way was that, after inserting each edge, what we do is, we call a BFS or a DFS, and calculate these values using DFS, but we can't really do that. So we'll have to think of something else to do that. Now let's say we have the values of the answer, for after adding each weight in the increasing order. Let's say we have the values after adding the weight 1 2, because it has the let's say after adding the edges with weight 1, after adding the edges with weight 2, we have two such edges. Then after adding the weight with edges 3, then after adding the weights with edges 4. While answering the queries, what we can do is, we can find the largest weight of the edges that is less than or equal to that particular edge. In this case, our largest weight is going to be 4. In this case, our largest weight is going to be 1. So we can basically get the answer from that particular index. We can further getting the answer for query where qi equals to 2, we can print the answer for the case when we have just you know entered the edges with weight 1 only, right? So now we'll be seeing how we are going to implement this. I'll be showing you the code. This thing, to implement this, I'll be basically using DSU, disjoint entity name. I hope you would have seen the video of that. I'll not be discussing the implementation of DSU. I'll be just discussing how that proves useful in this particular scenario, right? I'll be jumping to the code now. So in the starting, I have taken the n and m values as the input, and then I have taken the input for all the edges, u, v, and w values, and I have put them into a vector called edge in the form weight and then the
nodes, the weight has been put first because I want to sort the edges on the basis of their weight. Then I sort it. Then I call the initialize function. Initialize function basically just initializes my DSU, sets parent I equals to I and size of I equals to 1 for each node, because at this point I haven't really added any edge, so each parent is going to be itself and the size of each node is going to be 1. uh, each connected component is going to be 1. So after initializing, I'll just tell you what I am basically doing here. I am calculating the answer for I'm trying to calculate the answer for the cases when I have just added the uh, weights till this particular weight, right? Let's see how do we do that. So to know what exactly is happening here is, let's see what this count map of W represents and what this UN function return. Generally, this UN function basically just takes the union between U and V, but in this case, I have just modified it a little bit to get to the answer. What I have done is, let's say before making this union, the size of the connected component of U was size of root of U, and the size of the connected component in which V was there was size of V of root of V. I just multiplied both of these values and returned them, and I added that value in the count map of W. Right, that's what I did. And count map of W is a map of int comma int, and now let's see what this count map of W will basically represent. I'll also be dry running this code for this particular case. Yeah, so let's see. Initially all of the size and roots value are going to be 1, right? Now my edges are going to be in the order 1 1 2 2 3 4. That is going to be the order of the weights, right? Let's say initially we add the edge between 1 and 2. While we do that, our count map is empty. Now I'll be referring to count map as CM. Okay, so count map is empty. When I add this edge, the sizes will be 1 and 1. I'll have my count map of 1 as 1, and now I would have added this edge and all of the other edges are still to be added, right? Then I add this has been added for now. This all of these are to be are yet to get it, right? Now after adding this edge, I go to this edge 2 4. While adding this edge, I know that the size of 2 is going to be 2 and 4 is going to be 1 only, right? So 2 into 1 is 2. Now after this point, my CM of 1 value will become 3, and I would have added this edge as well, right? Now after this, I'll add this edge, right? 3 comma 6. Now while adding 3 comma 6, I know that the values of both of these sizes are going to be 1 only because these edge hasn't been added yet. So what I'll do is, the value of CM of 2 will become 1 by this point, right? Now these three edges have been added. Now the second edge with weight 2 4 5. While adding this 4 5 wala edge, I know that the size of 5 will be 1 and the size of 4 will be 3, 1 2 3, right? So I'll say that the CM of 5 has been incremented by not 5, CM of 2, because the edge length is 2. It was initially 1, it will be incremented by 3 into 1, so it will become 4 now, right? So I've added this edge. Now I'll move on this to this edge. While adding this edge, I know that the size of one connected component is 2 and the size of the another connected component is 1 2 3 4. So 2 into 4 is 8, so CM of 3 will be 8, and I'll have added this edge. Now the last edge that I need to add is this. Now I know that the size of this connected component is 1 and the size of this connected component is 6, and this means the value of CM of 4 will become 6. Now let's try to see what the values of CM basically represent. CM of 1 represents all those pairs of vertices in which there is basically at least one edge with length 1 and
all of the other edges have length less than or equal to 1. Cm of 4 represents the number of pairs UV such that all Wi's that lie between the path from U to V have a weight less than or equal to 4, but they have at least one edge, at least one edge such that W of that particular edge equals to 4, right? We can also look at this by an example. While we were adding this third edge, the edge with length 3, we knew that what we did was we multiplied this 2 by this 8, not 8, sorry, this. Okay, I made a small mistake. It should have been, no, it shouldn't have been 5, it should have been 4 only, because this wasn't added by that point. Yeah, so we multiplied this 4 by this 2. Why did we do that? Because we want this edge of length 3 to be part of the path. So we want that one of the nodes of the path are going to be from this connected component, the others are going to be a part of this connected component. So we know that the both of these connected components will have the other edges less than or equal to 3 only, basically less than or equal to 3, because we know that we have just added the edges that are less than 3 before adding this 3. That is why we are adding the edges in the increasing order only. So this is why we multiplied this 4 by 2, right? So if I just replace these cm values by prefix sums, let's say if I say that cm of 1 equals to cm of 1 only, but cm of 2 equals to cm of let's say cm dash of 2 equals to cm of 2 plus cm of 1, and for 3 let's say it's equal to cm of 3 plus 2 plus 1, for 4 it's equals to, let's say, 3 plus 2 plus 1. Then we'll have answers for this particular qi values. If we have qi equals to 1, then our answer is going to be cm of 1 only. If I have qi equals to 2, then my answer is going to be cm of 1 plus cm of 2. For 3 it's going to be 1 plus 2 plus 3. For 4 it's going to be 1 plus 2 plus 3 plus 4, right? That's because I want the number of pairs such that each edge has a value less than or equal to QI value, right? I just add all of those pairs, right? So this is the basic idea behind the code. Now what I did is, while adding a particular edge, I calculated the sizes of both of their connected components and multiplied them and added them to the count map value of W, right? So the count map of W will store the number of pairs such that all of the edges between their paths are less than or equal to W, but they contain at least one such edge that have a path that have a length exactly equal to W. So to get the number of paths that have weights less than or equal to W, what I'll do is I'll have count of W and I'll add all of those count values which have the weight value less than W, right? Now by this loop, what I'm doing is I'm converting this count map to store the prefix sum values. I'll have the previous value equals to 0 initially, and I'll iterate in this count map. I'll say v dot pushback the first value that will tell me the weight value, and the second value will be el dot ss plus previous value, and I'll add to the previous value the current second value, right? So this will give me the prefix sum values. Now while iterating on the queries, I am taking the input of the queries. The query is ql, right? So I'm making a temporary pair ql comma infinity. I'll just explain it, what is the logic behind this. Now while answering the query, what I want is, let's say the query val is, it's given only query val. What I want is, I want the largest weight wi such that wi is less than or equals to ql, because I know while adding the edges I don't want any such edge to be added such that wi is greater than ql. I want only those edges to be added to the tree which have a value less than or equal to ql. So I'll want to get the largest wi such that wi is less than or equal to ql. To do that, what I'm doing is I'm making a pair called ql comma infinity, and I'll get its upper bound. If when I'm getting its upper bound, what I am going to get here is that uh, I'll get the first w such that wi is greater than q, right? Because the second part is infinity here, it means that it will just give me the next wi value. This is set to infinity and not some other value, because let's say I searched for the upper bound of ql comma 5, and if there was a value ql comma 6 present, I would have gotten this particular value, but I want the smallest value that is greater than q, right? So after getting the IT well, if it's equal to v dot begin, it means that all of the edges have a weight greater than ql. There is no such edge which has a lower weight. So in this case, my answer is going to be 0, because there is no such pair. There is no such weight that is basically less than ql. Else, I'll say it minus minus. It minus minus is done because the it value was representing, was pointing towards the smallest value w, which is greater than w ql, but I wanted the largest value w, which is less than or equal to ql. So the just, the value just to its left will going to represent that. So I'll say it minus minus. I'll just print it val second, because the second value is basically going to contain the answer. If I add all the edges that are less than or equal to it vals first in the tree, right? I hope the intuition behind the solution is clear. I hope the code is clear. It's possible that it went on and off and not all of the things are clear, but it's fine. It's not that easy. It's not an easy problem. It's fine if you even understood some part of it. You can go through it once again. You can this is the link to the problem. You can go try to implement the code for yourself and try submitting it. It's actually the last problem of a contest. You can see it was a div3 contest, and this is the last problem, which is G. 1 2 3 4 5 6 7 8. This is the 8th problem, so it's fine if you don't if you didn't completely understand. It was actually a hard problem. So yeah, this was it for this video, guys. Thank you very much. See you guys in the next one. Hi everybody, this is Pulkit from Coding Blocks, and in this video we'll be discussing this problem called kth path. This is a problem from codeforces.com. As you can see, I'll be reading the problem out, I'll be discussing my approach, and then I will be also discussing in brief what the code actually looks like, right? So let's get to it. The problem says that we are given a connected undirected weighted graph. Connected means only one connected component, undirected means undirected, weighted means that each edge has a weight associated to it, and consisting of n vertices and m edges. What we need to do is we want to print the kth smallest shortest path in the graph. Okay, let's say in other words, more formally, if D is the matrix of shortest paths, where Dij is the length of the shortest path between I and J, we want to print the kth element in the sorted array consisting of all dij where I is less than j. So we basically have to consider ij only once. It's not that ij has to be considered separately and ji separately, no. And we don't have to consider those pairs in which I equals to j, I should be less than j, right? So I think the question is clear. If it's not, you can pause the video and read it once again. The constraints are that the value of n can be up to 200,000 and m can be up to 200,000, and actually min of 200,000 and n into n minus 1 by 2, because the maximum number of edges possible are nc2, and the minimum value will be n minus 1, of course, because we have to make the graph connected. And the value of k can be from 1 to minimum of nc2 and 400. This is the key point here.
the number of vertices, the number of edges, and the value of k. So the first line will contain n, m, and k. Then there will be m lines, where each line will contain x, y, and w, where x, y will be representing the nodes, the number of the indices of the vertices that this edge connects, and w will be the weight for that particular edge. It is guaranteed that the given graph is connected. There are no self loops and multiple edges, right? Okay. So for the output, we just have to print one integer, the length of the kth smallest shortest path in the given graph, right? So this point onwards, I'll be heading into the solution. So if you want to think it around, if something is not clear in the question yet, you can pause the video, read the question again, think about the solution, and then continue watching. So one possible solution that we may think of without bothering about the constraints is that generate all the shortest paths, right? Generate the shortest path for all pairs using Floyd-Walsh algorithm maybe. But the problem here is that the time complexity that we'll be using there is going to be big of n cube, right? So that's not something that will pass within the time limit. We know that the value of n is going to 10 raised to power 5, and we can't really afford a time proportional to 8 into 10 raised to power 15. So we'll have to come up with something better. To come up with something better, what we can observe here is that we don't really need all of the shortest paths, right? Because we just want them, because we just want to know the kth smallest path, kth smallest shortest path. So we don't really need all edges. We don't really always need. We don't always need all edges. It's possible that we may need all edges in some cases, and we don't really need to calculate all the possible shortest paths. If we know that we need the kth kth shortest path only, the kth shortest path, let's have two possible cases. One possible case is that basically k is less than or equal to m. In this case, what I am basically trying to suggest you is that let's sort the edges on the basis of their weight. Let's say the edge 1 is e1, e2, and the mth edge is em, and these are the edges after having been sorted according to their weights. Now if I just basically consider the edges that have the smallest k values, basically the first k edges, and if I consider the nodes, if I consider only those nodes which are basically used in any one of these edges, what I claim is that I'll be able to get the kth shortest path out of only these edges and nodes. Because if you see, I don't really need to use any of the edge that has the weight more than the first k edges, because even if I see I'll be getting at least k paths out of these edges. One path can be from the vertex x1 to y1, the second will be from x2 to y2, and the kth will be from xk to yk. So the number of paths possible with these edges are obviously going to be greater than or equal to k. So I'll just use the edges and the nodes corresponding to those edges, and the number of basically nodes, that the maximum nodes that I can have, the maximum different nodes that I can have from these edges only are going to be 2k. Each edge can have two nodes, and if there is no overlap, if there is no edge that occurs in two of the edges, I'm sorry, if there is no node that occurs in more than one edge, in that case our number of different nodes are going to be 2k. So if k can be up to 400, then 2k can be up to 800, and if we apply Floyd-Warshall algorithm on those 800 nodes instead of the bigger value of n, that was 2 into 10 raised to power 5, it will be much better. 800 cube will pass in the time limit, because the time limit is 2.5 seconds, it will pass. You can see here the time limit is 2.5 seconds. Yeah. So the second case was that if k is greater than m, in this case we can simply consider all of the m values. We can consider all of the m values, and in this case, if k is greater than m, it means that the value of m is less than 400, right? The value of m will be less than 400 in that case. If the value of m is less than 400
and we know that m is greater than or equal to n minus 1, can we say that the value of n minus 1 is less than 400? We can, right? We know that the value of m is greater than n minus 1, and we know that m is greater than less than 400, then n minus 1 will also be less than 400. So in this case the value of n is less than 401, and in this case we would, if we directly apply the Floyd-Warshall algorithm, it will work. So if the value of k is greater than m, it means that the value of n, that is the number of vertices, is small enough that we can directly apply Floyd-Warshall in the time proportional to n cube, and the maximum time that we are going to take, it will be 400 cube, which will come out to be, I think, 64 into 10 raised to power 6, right? Yeah, it will work. And if the value of k is less than or equal to m, what we can do is we can just consider the edges, the first k edges in the sorted order of in the sorted list of edges, and the number of different nodes that will have will be just 2k. Make a new graph of only those 2k nodes, adding the corresponding edges, and you apply the Floyd-Warshall algorithm on those, and just get the smallest kth smallest shortest path, right? I think the things might be a little unclear for now, that how will we making altogether another graph out of those random vertices. It will be clear. I'll be explaining these things to you while we'll be seeing the code. So I hope the basic approach is clear how we are going to deal with this problem. Let's now switch to the code. I had already written it down. Let me just copy it to the Sublime. Yeah, so let's just go through the code. So I have two cases here after having taken the input of for an mk. If k is less than or equal to m, that is the case when we have to extract the vertices out of the smallest of the shortest k edges. Let's see this case afterwards. Let's first see this case, the else case, in which the value of k is basically greater than m. In this case we just discussed, I'll just write it down quickly again. We know that k is greater than m, right? So it means that m is less than 400, right? And we also know that m is greater than or equal to 400. If n minus 1 is less than or equal to m, then n is also less than 400. N minus 1 is also less than 400. So we know that the value of n is less than or equal to 400 in this case. So in this case we can directly apply Floyd-Warshall algorithm. It will give us the dij values in big of n cube. I will sort it, and we'll simply get the kth value. Let's just simply go through the code once. We have this dn plus 1 n plus 1 array. Apply basically set the dij values for Floyd-Warshall algorithm. Get the edges. While getting the edges, you can say that dij equals to dj I equals to w. Then apply the Floyd-Warshall algorithm's main code. Then have a vector v, push all the values in that vector if I is greater than j, because that was the condition that they gave us. Sort it and just simply print the kth value. The kth value will be v of k minus 1, as we know that the indexing will be 0 based, right? So let's now switch to the another case where k value is greater than or equal to, the k value is less than or equal to n. In this case, our first task is going to be extracting the nodes out of the smallest k edges. Let's just first quickly get all the edges ijw and c in ijw. Just push back all the edges into a vector. I have a vector of parent and parentant, pair of intent parentant. Basically, this second will tell me the node numbers, the vertex numbers of the vertices in between in between which this edge is, and this first will tell me the weight. I basically want to sort the edges according to their weight, so I have put weight in the first parameter as the first parameter, right? So get all the edges, sort them. I think I just had this initial a different constraint, like if k equals to 1, then I know that the smallest edge is going to be my answer. Let's just print it and return 0 from here on. I don't know if that's really necessary. Maybe this case is covered later on also, but I
just covered it separately that time. Now this MIS basically means map intent s. In this, what I'll be doing is I'll be iterating on the first k edges, and I'll be setting the s value of the two nodes that between which this particular edge is as one, so that I know what all nodes were basically the part of the smallest k edges. Now at this point I have the nodes, the maximum number of nodes that will be there will be 2k. So now what I'll be doing is I know from now on I know that the smallest, let's say the nodes were from 1 to, for example, let's say 500, right? And the value of k was, let's say, 5, and the smallest edges, okay, let's say 3. The smallest edges, 3 edges were the weight 1 and between the nodes 100 and 105, for example, and then the next one was 2 and that was between, say for example, 5 and 14, and the third one was, let's say, 5, and that was between the nodes 401 and 500, for example, right? Now the problem with these edges is that the values of the nodes are really scattered. They vary from 5 to 500, but there are a lot of nodes in between which aren't really a part of these edges. So what I'll do is I'll code them from 0 to not actually 0, from 1 onwards. What I'll do is I'll have the smallest node out of these. I know that the smallest node is 5. I'll code 5 as 1, then this 14 as 2, then we have 100 as 3, this as 105 as 4, 401 as 5, and 500 as 6. So that there is a continuity in the indices. I can simply apply Floyd-Warshall algorithm without any problem. This is why I need this coding. Now I have set my initial value as 0. Now what I am doing is I am iterating at each node in the S, and I am just setting the code of that particular value, that el.ss, as plus plus ls. In the first, for the smallest value it will be 1, then 2, then 3. So for example, s of 5 is going to be 1, s of 14 is going to be 2, s of 100 is going to be 3, then for 105 4, then for 401 5, then for 500 6, right? So then n is basically going, I replaced the old n by the new n, which is s dot size, because now I am having s dot size number of different elements. Now I'll apply Floyd-Warshall on these n nodes, right? So I just made d array, d of n plus 1, n plus 1, set the values, then iterate over the edges. By iterating over the edges, I am just seeing that if both of the both of the elements of this particular edge are a part of my new graph, then I'll add then I'll add this edge in my D array. I know I'm iterating from 0 to m minus 1. In this case, it would have been fine if I would have iterated from 0 to k minus 1 also, because I'm just worried about the smallest k edges, right? So after having done it, I'll just apply the main code of the Floyd-Warshall, getting the smallest getting the shortest distances for all pairs of these uh, of these nodes, and then I'll have a vector. I'll just push all of these values in a vector and sort it, then simply print minimum of vec of k minus 1 and vec of k minus 1 dot ff. Okay, so I don't really think that this was required. Had I just simply printed vec of k minus 1, that would have also been fine. So I've simply gotten the smallest. I've simply gotten all the possible distances from by just using the nodes which were a part of the uh, smallest k edges, and I'm just sure that this will give me the smallest, right? I hope the solution is clear. I hope the code
explanation is clear. I know it's a bit clumsy, but I hope you get the point. I hope what is basically tried to be implemented via this code. So yeah, this was it for this video, guys. Thank you very much. See you guys in the next one.